Hello there, hope you're keeping well. Welcome to the wonderful world of radio frequency and electronics engineering. On the bench for repair today is a Kenwood TS2000 all mode HF, VHF and UHF radio transceiver. We've repaired one of these before on the channel. This one's come to me from the island of Mauritius, all the way from there to here in the UK, where I'm based for repair. A gentleman that owned it has given me some intel that it's had some kind of a burnout internally. So because of that, when we get into this repair, I'm not going to power it up initially just to see if it functions and what it does until we've had a look inside, because obviously we don't want to exacerbate an existing problem further. So the Kenwood TS2000, for those that don't know, is basically a very wide frequency range radio transceiver, and it boasts about 100 watts RF output power. And they've been around a very long time. I think they were produced in the early 1990s. They're very sought after radio. There's got a bit of a cult following of these radios. There are options that you can purchase for them, or you can buy them with the option already fitted for 23 SEMS amateur band, which is a 1.3 gigahertz frequency allocation, or 1290 to 1300 megahertz. And it also boasts a UHF transmitter and receiver, quite wide range as well for receive, and throughout the entire UHF spectrum, VHF as well. And it also goes right the way down to the 6 meter amateur band, which is around 50 megahertz. The 10 meter, 11 meter bands on the 29, 28 and 30 megahertz bands, and then even lower than that, right the way down practically to zero. So this transmitter in this radio is very wide banded, so it can obviously work on different modes as well, being SSB modes, upper sideband, lower sideband. It does CW for Morse keying. It also does AM and FM modulation, both on transmit and receive. So it's an all mode radio transceiver, very versatile, and quite a large transceiver, very heavy as well. And if we just have a look round the back, I'm just noticing the condition of it as well is this top's a bit speckled, etc. But basically, if you had the 23 SEMS option, there'd be a coaxial cable coming out here with a type N on the end of it, because that's fitted in the end is a 23 SEMS module. So we basically got a VHF and UHF antennas on the back here, and which is basically these two, VHF, UHF, and then we have effectively two HF antennas that we can select 1 and 2. So you can have a long wire antenna, log periodic, something like that on one socket, or you can have a vertical on the other, or a beam, that kind of thing. So you can switch between them, and you can program that into the radio as well. Of course, on the rear we've got the usual external keyer inputs and outputs for a Morse key, RCA for audio output, etc., or for remote keying. And then we've also got tape recorder or AF inputs and outputs there for things like packet modems and other things like slow scan TV, facsimile. Various other modes of transmission can all plug in the back, radio teletype, things like that. And then we've got a serial connector on the back here as well, which enables us to drive a radio from external software if we need to, which you can get from Kenwood. So what we'll do, we'll just take the lid off the radio first and just have a look round and see whether we can spot anything serious before we apply power, because the last thing I want is for it to blow up even more. And the other thing about it is as well, somebody else has obviously been in this before me, otherwise I wouldn't have known there was a burnout in it. So we have to be mindful that perhaps somebody else has had a go at this. They may not have put things back properly, left leads hanging off, touching things, you don't know. So we'll have a look at that in more significant greater detail. But all in all, it looks reasonable condition. It's just the top of a radio which is a bit spotted, and it looks to me like as if other than that it's okay. It's in reasonable condition, it just needs a clean. So let's whiz it apart and have a look. Okay, so we've got all the case parts off now, and then there's just this plate here. There's a lot of screws holding this plate down. So we remove the case top and bottom. We'll leave a speaker in for the time being. So I just want to have a look in and see if we can see anything. This is the ATU, the antenna tuning unit, and we've also got the power amplifier here for VHF and UHF and HF. So this is the HF side down here, so we've got the power amplifier transistors there. This particular model is a FET one, whereas the other model that we did a repair of uses bipolar power transistors for the transmitters on both VHF, UHF and HF. So this basically is the 0 to 60 megahertz, if you like, power amplifier, and then this side here, which is just buried under this, and you can probably just see there these two transistors. This side is the VHF, and then the UHF is actually on the other side. It's actually a board sandwiched on the other side. So this does the VHF high band, if you like, the 140 megahertz upwards is done there with that power amplifier. Obviously this is the input transformer, that's the output transformer. These are the driver and pre-drivers there for the RF amplifier, and then we've got two signal inputs, one HF and the other one VHF there, which goes into the amplifier. There is a relay on the radio unit down here, which switches the RF path between this amplifier and that amplifier, depending on what bands we're using. And this also is part of the antenna tuning matching unit at the back here, along with this as well. So we've got two units there. Now I'm just looking for signs of burnout, anything that's barbecued, and I can't see anything at the moment that stands out. There's certainly no burning smell, and I can't see any ICs that have got any craters in them. These look okay to me. I'll remove that speaker in a moment to have a look. It looks like the flexis look okay. Doesn't seem as there's any black marks in them where they're burned out or anything. Looking at the inductors, various other components to see if there's anything on the PA board which is burned out, but I can't see anything there. This is a fan there which blows cold air through to the rear here for cooling. There's nothing obvious that's standing out there on that particular board that presents itself as being a burnout, but I will just remove that loudspeaker because there could be something under that. So we'll leave no stone unturned. So let's have a look and see if there's anything hiding under here which needs further examination. And let's just have a look at that a bit further. Now then, yes, this IC here looks like as it's barbecued, and yes, there's definitely a bit of smoky going on there. So we'll just try and zoom in on that a little bit more so we can see. And then we'll come right in. There it is, look, smoky. Yeah, so that's interesting. And it looks like as if that's something to do with supplies. We'll have to look at the diagram and have a look at that, see what that does. Interesting. So looks like we've got some fuse there, F1, which is this white SMD thing, and linking across, and I think that must be some kind of a main voltage regulator perhaps. And we've obviously got the main supply coming in here on that track going along, and with the power comes this way. Obviously there's a fuse there, and then it looks like it carries on and goes this way for other circuitry and things down there. So has something gone short on its output perhaps and blown it up, or is there something else that's happened? So that's what we've got to try and find out. We're going to find out what that IC does as well. So that'll definitely be something that we can we can have a look at. Everything else looks okay. Those transistors look fine. You never know, there could be something under the board as well that's gone short and popped it. Could be a myriad of issues that's caused that to go. But yes, looking around here, looks like everything's hunky-dory. Can't see any signs of any other damage that stand out at this moment. And all looks well. With a PA board. So we'll have to have a look. I think this is a voltage regulator that supplies voltage, probably for either the audio amp or perhaps the switching for the transmit receive. It could be one of those AVR voltage regulators. It could be for all sorts of different things. Okay, what we'll do now, we'll turn the radio over and have a look as well on the underside. And what we'll do, we'll just unplug this loudspeaker so we don't cause any damage to it, and put that to one side along with the screws for it in the little catchment thing. Right, so let's have a look. So this is where the 23 SEMS module would normally go. It would fit in there, that's where that goes, and this is where the Mitsubishi power amplifier brick would bolt to for heat sinking. So if it's got the 23 SEMS, that's where it would be fitted, on that side. So this doesn't have that fitted as an option. And then this ultimately is the receiver section, with the IF filtering, etc. So we'll just have a closer look at that. We've got the backup battery as well for the memory as well. And interesting. So we'll just have a look and see what we can see. So got all the crystal filter in the front end tuning there, the HF side of things, VHF, UHF, etc. All the different filters. So I'm just looking for signs of burning, anything that's gone a bit barbecued, and you know, I'm also looking to see whether these flexes are in straight, because that can actually cause faults. That to me looks okay. It looked a bit wonky at first, but if they're in cockeyed like that, the pins don't align up properly. You can blow things up. They've got to be in like that, and so often, sometimes you find them where the like that sort of thing, gone in at the wrong angle, and then fizz bang, you know, you turn it on and then boom. So that's looking okay, this board. And we'll just keep looking a bit further, see if there's anything there which is standing out. No, looks okay. Got a relay there, that looks fine. There's a mark on the board there, like a pen mark just here. Don't know what that signifies, if anything. Is it pointing to something maybe? I don't know. Might be just a little mark. And all's good at the moment. Interesting how the screws have got a little bit of blue on them, like a blue pen mark, as if a board's been out and somebody's marked the screws so that they know where they're going back in. Now that looks okay, is it? That looks a bit I'll have to look at that a bit closer. I don't know what that is. Oh, it's a socket. Okay. This looks like it's had signs of being in and out a few times, because it's got like a crease on it. It's difficult to make out on camera, but with a naked eye you can sort of see that there's been like a crease on it. It's weird. So I'm not sure if that can be seen on the camera, but there's definitely like a crease there. So I'm not sure if that's been in and out a few times, but it looks okay. Can't see anything there. Tried to have a sneaky view down there, just into the control head where the microprocessor is, down there, and That doesn't look like as if it's been removed. It looks reasonably okay. It looks very dusty down there as well. So I'll just try and have a look at the diagram now then to find out exactly what that voltage regulator does that we've seen, the one that's burned out here. And obviously that voltage regulator there, need to find some intel on it and what it does, what its function is, and then look at removing it, cleaning the board up, and then testing to see whether there's a short external from that which has caused it to go fizz bang. So that's the next step. Let's look at the diagram, see where we get. Right, so before we power the unit up, we'll have a look at this device now in more closer detail, and then obviously look at the circuit diagram and have a look and see what's what may have gone faulty around this. But it's worth noting this device is a FET. It appears to be a BUK 7635 FET. Now, I've done some testing with this particular device, just off camera with my probes on the meter, and it does appear to be electrically okay. So it just looks like it's got very, very hot. Now, it's not got the unique smell of burning PCB around it, because that's quite often the case when components like this really do fizz up. And in this case, there isn't the smell there off it, because I've had a sniff to see whether it's got that really unique sort of noticeable PCB burning smell. There isn't that, and I've given it a clean with some isopropyl alcohol cleaner because there's some like soot deposits around it, and it all seems to have cleaned up a little bit better than it was before. So I think what we'll do, we'll check these fuses out anyway, fuse 1 and fuse 2 there, those two. The fuse one's only tiny, it's like a speck of sand in comparison to fuse 2, and we'll just check those out, make sure they're okay, and we'll have a look at the circuit diagram together and walk through it. But it could be this radio has had one of the more common faults on there, which I'm going to explain in a moment, which I've had on these before. Now, the spec I've got, it's in this 1212 power 1212 package. 1212-8 means it's got 8 pins, and then this is a package style. This is an equivalent to it, I think. I found here, but there's some more data on it there. So that's like what the device looks like underneath, with the gate drain and source, etc., and the pitch of the pins. But it is like, I think, about 35 amp current rating on it. Now this isn't the same device, but you know, similar pin out and everything. But I did have, I can't remember where it was now, I did have some more information on these, which I've tried to find out, because going back to the original Kenwood TS2000, the model that came before this, the very first models that were produced, just here there was a relay where that FET is. So if we just look a bit closer there was a fuse, they weren't surface mount fuses, they were normal wire lead fuses. And then here was a relay which switched the power on and off. So when you press the power button on the front, it pulled down one side, the logic pulled down one side of the relay coil to ground, and then it pulled in the contacts, and then it connected the main power line through to the rest of the radio. And if I remember rightly, after this there was some serious voltage regulators as well in there, in order to 7/8 series and some more others elsewhere, some SMD versions on different parts of the circuit that powered up then the many supply lines to all the rest of the radio. So one of the problems that there is on these radios, which doesn't happen often, but it does on some of them, and I've not had many of these over the years that have exhibited this issue, in the VCO circuits on the other side here, we'll have to remove this board in order to get to it. There's a screening can and various traces that go around the edge of a screening can for different VCO modules, and what happens there is that the production of them, the clearances between the screening can and the PCB were too close, instead of having a nice air gap. And what happened, I think there's like, if I remember right, it's been many years now since I've had to do one of those, but there was a through hole connection that carries the 8-volt rail to the VCOs, and basically the screening cam touches the little printed land, the little through hole via. So basically what happens is it shorts it out, the supply rail, but it happens intermittently as the radio heats up and metal expands and contracts, etc. That's when the fault occurs. And there's some other weird things that go on with some kind of flux corrosion and things like that then go conductive and cause all sorts of little problems. So I'll probably need to do some research myself on that fault, because I've made some notes in a folder that I've kept for years, where as I find faults I document things in a folder which I keep in the workshop, that I've had for donkey's years. But yeah, so that could possibly be it. It may have been that some things loaded it, and obviously then cause that fault, because the supply rails for the radio frequency power amplifiers, the main PA devices, and obviously the pre-drivers as well, which are these and the drivers, the supply rails for those, these four, do not come from this. They're directly connected to the incoming supply rail from the external socket. However, the driver transistors, which we've had problems with before on other models of these Kenwood TS2000s on this channel where we've done repairs, some of these can go short circuit. The integral diode, which links between the collector emitter junction, starts to go short rather than the transistor junction itself, and then basically as the radio warms up, or the transistor starts to warm up should I say, then the current consumption of a device increases massively to such an extent where it's baking hot and it blows the fuse. So it could be something like that. But anyway, I think what we'll do now, I've got a little setup ready. So we've got the main power supply here on the bench, capable of supplying 30 amps. We've got a meter here that's on the 10 amp current scale DC in series with the main supply. So I've rigged up a power lead here. We're good to go. But before we do that, let's just have a look and test the fuses together, and then let's have a little walk through the circuit diagram just to refresh our minds on how the system operates. Okay, so what we'll do now, we'll just move this wiring loom out the way that I've unplugged, because that's always getting in the way, and we'll just check these fuses. So we'll have a look at the bigger fuse first. Just touch the meter probes together just to make sure everything looks okay. Yeah, there we go. Right, so let's just check the fuses then, just to make sure. So that fuse 2, I think it is, that's okay, no problem there. And if we just do a quick continuity to ground, there's no shorts there from what I could see. And this is the little fuse 1, a tiny little speck of sand, and that's okay as well. So we'll just check between that and the chassis as well, and there's no shorts there. So okay, at the moment then, this leads me to believe that the issue is likely some kind of loading, resistive loading that's taking place. We're getting increased current consumption on that device, which is this FET here, and it's causing it to warm up. So this could be after the supply regulators, because the supply regulators, if there's a short circuit for example, these are going to current limit, and they will only drag the incoming supply line down so far, and they will regulate the current. When they've been bolted to this big heat sink there, they could stand some significant time doing that before destruction takes place. So it could be that it's loaded this FET and it's warmed it up, hence the reason why it's not burned properly. It's not got an absolute, burning crater in the board and burned off the copper tracks, etc. And it doesn't have that horrible putrid PCB burning smell either. So it's just got hot, that's all. So I think what we'll need to do, because we've not got a presence of short circuit at the moment, I'm now confident I can power it up, or try to power it up and see what happens. But at least from what I can see with the test that I've done around that device off camera, just to make sure that it's functioning and there's no shorts on it, and also the supply rail checks that we've just done with the fuse 1, fuse 2, I'm confident we can power it up. So let's just have a look at the circuit diagram now before we power it up, and then we can see what that does and what it supplies, and indeed its footprint, because as I said, the earlier model had the relay. Okay, so if we just zoom in here a little bit, so this is a PCB layout on the earlier model. I don't think I have a service manual updates for this particular newer model of a Kenwood TS2000, where they changed these bipolar devices that were the PA transistors to FETs, and as well as that got rid of the relay. But if I just zoom in a little bit here, if I can click on the right bit of it and we zoom down here, you can see just here there's actually a circuit reference. I think it says K201. I'm about 2 feet from the well, about 3 feet from the computer, but I think you'll be able to see it better. But there's definitely a relay there which was got that reference K201 there. Now that is currently where the footprint of the FET is, because this is obviously the early model. So in the good old days, before Kenwood tried to make things better, that was a mechanical relay that switched on the power rail, the DC supply, to the voltage regulators and other circuits within the unit, which we're going to look at now. So if we just carry on zooming down here, and then we obviously at some point get to the oh, here we are. Look, I think this is it here. Yeah, I think this is it. Let's just have a look here and try and zoom in a bit as well. And there we go. Look, right, so we've got the incoming power supply on the left here. This goes to the rear connections on the radio, and what happens is, if I can just zoom in a bit more perhaps, this is K201, the relay, which has now been replaced with a FET. So we've got the transistor that turns it on. The red line above is the supply line coming in from the rear connections on the back of the radio, which is a power socket on the rear that goes off to our power supply. That comes in. Don't forget the power supply rail lead that's coming in fused as well, so although there's no fuse there is a reverse protection diode obviously over and a Zener over protection diode as well, rather, that'll clamp the supply line if you do any funny business. So the supply line comes along and we hit this K201 relay. Now obviously when the relay is pulled in, when we press the button on the front, it connects power then obviously to various supplies with these voltage regulators here, two of which of those are these two here. That's what they are, and the third one is somewhere else, which we'll find. But more notably, you will notice there is a fuse here. So the supply rail joins here, this junction, from the output to the relay, and supply rail goes that way as well as downwards, and then feeds these voltage regulators, and ultimately then it goes off to other circuits as well. Now these inductors that are in series with supply lines off to other parts of the system are only small current rated components, so if there were to be a significant current taken on the output of these inductors down to ground, then these would smoulder or burn out, and I can't see any evidence of that at the moment while I'm looking in there. We've got obviously the supply line going this way to another fuse, which is this fuse 2, I think it is, and then that goes out then to other parts of the system. So we checked this fuse and that was okay, so it looks like anything this way doesn't seem to have caused a problem as such, or at least an immediate short. And then we've got a supply to the TX-RX unit there going off. So this smaller current supply that's going via this L205, that comes right the way down here, and then obviously goes off to another part of the system. In addition to that as well, we've got a supply rail going this way to the right and joining this one again going down to other parts of the system, to other system boards, but immediately going across and then connecting to all these transistors one by one down there, this decade of transistors, and then it goes across here and then goes to some of these surface mount transistors as well. So Any of these that have gone short circuit or whatever, they would have frazzled and gone fizz bang with that kind of current. And we've obviously got the different switches there for different supplies and functions. So if we come back across here, we've obviously got these voltage regulators. These in turn supply another voltage regulator in one case there. So there's 4 voltage regulators, all responsible for supplying the supply rails to the unit. In addition to that, the supply comes uphill and then goes via this fuse. Again, we checked this and this was okay. However, on the previous Kenwood TS2000 repair, we had problems with these 2 transistors here, and these had the integral diode between the collector emitter junctions, which started to go faulty on just one device. So it sank all the current that was supplied to it straight to ground, and thus it sunk it straight to the 0 volt line and then drew mass current this way. And it was only later, as the fault progressed, this fuse actually popped. So initially, the current consumption that these transistors took was low enough not to blow this fuse, but as the fault progressed, eventually we got this fuse to pop. As well as that, there's more of a low current path, again via another series inductor, the type of inductor which is a similar size to a small resistor. So again, anything this way that may have sunk that kind of current would have blown this, and I can't see that here because I'm just looking at the board. Again, this transistor potentially could have a fault, these 2 could have as well, so it's possible there's an issue around here. Potentially, may not be either, so it could be on the outputs, the supply rail outputs of these devices, which is shorting out, causing these to go into current limit, thus drawing constant current from what is the FET, which replaces this K201, and thus causing it to heat up. Maybe it's a possibility, it's a hypothesis. Indeed, K201 being little relay, I don't know why they replaced that and put this surface mount FET in its place. I mean, it does make a click sound when it comes on and that, but that's about it. I can't say I've ever had a Kenwood TS2000 where that relay is blown, but maybe Kenwood thought that there was quite a high rate of failure on them, maybe, I don't know, and maybe they decided to modify the circuit so they didn't have that relay anymore. So yeah, there's a few little pointers we can start looking at. We've got some high current paths, some medium current paths, and then some low current paths via these small inductors, so we can start to look around and what have you. But of course the VCO circuit we'll look at next does actually have a supply rail from one of these, which then is a known issue where it can short it out and thus cause these regulators to start smouldering, or at least going to current limit. They're only capable of supplying 1 to 2 amps, that's all, very small current really. Okay, so we'll now have a look at perhaps powering the radio up and give it a full once over with a radio test set. So today what I've done is I've got the Marconi 2968 radio test set. We've got a breakout screen here which will allow us to look at the technical spec of a radio for receiver and transmitter testing, and we'll do that on this device, and we will just check to see whether the thing actually functions as well. Okay, so as stated earlier in the video, we've got the power supply and then we've got the ammeter on the 10 amp scale in series with the supply to the radio. We connected the VHF output socket on the transceiver to the radio test set, and obviously we've got the breakout screen here. So we'll be looking at first doing a test on 2 meter amateur band just on FM, just to see whether the radio transmits, and we've got a microphone connected in, so we'll turn the radio on. So far so good, no major current consumption, looking for around a 2 amp draw, and we've got only about 1.8 amps there, so it's not like as if we're drawing massive amount of current. We're on 145, the knob turns okay, which is fine there. So we'll do some transmit tests first. I want to just double check by using the power button on the front there that the power is set to 5 watts, because you can adjust it so that it does lots of watts. So we'll get it down to 5 watts. Don't want to start smoking things out. So now we'll just hit the transmit button, and we've got the radio test set screen up there on auto tune as well. So we'll just hit the press to talk button just momentarily. I didn't like that. They're drawing about 8 amps there on 5 watts. So just press the transmit button now. 8.1 amps. I can't hear the test set clicking in either, as if it's found something. So I'll just press the transmit button now, and there's nothing there at all. You know, I'm keying up the transmitter and we're not getting anything at all being measured on the test set. So what I'll do is I'll definitely some current draw there, and whether there's an RF fault there on that frequency I'm not sure. Let's just have a look. So if I put in TX frequency at 145.0 megahertz, and let's just see whether we can get the auto tune to work. No, it's not really. It's seen something. Let's just go to spectrum analyzer, and then we'll do an expand on that, and then let's just see whether we're getting something. So there is something there, just milliwatts though, with the look of it. Very low down in the noise floor more or less, but there is definitely something there. So the VHF antenna on the back doesn't seem to be working there. Now let's just go to the 434 megahertz band, and I'm just going to double check on the rear of the radio that it is in fact the VHF antenna that's connected, and we can do that purely by transmitting. And again, it's drawing some current, but I'm just verifying I'm connected into the right antenna socket on the rear, because it is labelled V and U, and then there's 2 HF sockets as well for antenna 1, 2. So I am on the right socket. It was just, I always check, you never know, because other people have marked it on the rear. So basically on the 2 meter ammeter band, there doesn't appear to be any transmit output power, although it's drawing 8 amps for only 5 watt transmission. I'm not going to adjust that to control up any IA. It could be that these bias pots for these VHF power amplifier transistors are being tweaked, and it may be that they need adjusting, or there could be a fault, but it's drawing 8 amps, so it's definitely doing something. Whether that's RF power that's drawing the 8 amps, or whether it's just the bias to those transistors that's too heavy and the transistors themselves are sinking the current through the DC conditions, I'm not sure at this stage. Okay, so let's move on to UHF, and then on the rear of the radio there is a UHF connector, which I've got on the back on the type N. Right, so we're in there. Okay, so basically on UHF, just turn it to 435 megahertz dead. 435. It looks like as if there's a backlight bulb out as well in the middle here, because there's 3 bulbs. I think there's 1 in the middle and 2 at the ends, but there's definitely a dark patch here, so that'll need repairing. Okay, so I've left the test set in auto tune. Just hit the press to talk switch, and we're not getting anything at all there. The test set's not locking on to the frequency or anything, and we're drawing 2.1 amps only, and unkey, rekey, so we're not getting any significant current consumption on UHF, and certainly no RF output power at all on UHF. Okay, so the next one to test is the HF section, or VHF. We'll look at the 6 meter ammeter band. I'll put it on 50.5 megahertz, got it on FM, 5 watts power, and that goes, the 50 megs band is off the HF antenna connection on the rear there, which I think is an SO239 if I'm not mistaken. So I think I can use the VHF RF adapter that I've got here, which has vanished just at the rear here, and I think lost it. There we are. So let's just have a look here. there. So we're on the, what would be the HF antenna connection. I heard a click then. I don't know what that was. Ah, the frequency just flashed on the radio. That frequency just flashed. It blinked, did that. Don't know what went on there, but there's something definitely flashed. It did say that I think there were some dashes coming up on the display, which indicates a VCO out of lock condition. So maybe that's something as well. Let's have a look. 50.5 megahertz. You see, it just went then. Just flashed. Let's have a look. It's an oddball, isn't it? Definitely saw it flash then. Like the... Right, well, I'll transmit. We're still on the... Right, we're back. The camera ran out of memory momentarily, just as the display went with all the dashes. But we'll get it to replicate it. So we've got it on FM, 5 watts, 50.5 megahertz. And when I key up the transmitter, it's drawing about 5 amps. And then the transmit goes off. And then it comes back. And we're actually getting 5 watts at 50 point. Not at the right frequency though. It's about 147 kilohertz off frequency, because we're actually transmitting on 50.5 and it's come up with the dashes now. Now if I press the transmit, now it's come back by itself. So the VCO is going out of lock, and as you can see, it's just flashed again. There's definitely something going off, but it was 147 kilohertz off frequency. Because if we go back and I'll press the transmit button again, so the test set's found some power, it's just locking on. Now the radio's gone off, now it's come back on again, and it's all over the place. It's keying up momentarily. Now it's on frequency at 50.4999, but then it was sort of going off frequency. It's drawing 7.2 amps and we're only getting 5 watts out of it. So there's something strange going on there. And what's happening is it's going out of lock on transmit, because I'm just keying up the radio now and the test set's on. It's displaying a frequency that's more or less near, although its accuracy is differing all over the place, but it's still nearer than it was earlier ago. I'll just keep it keyed. It's drawing 7.2 amps, and it's I'm just going to put my finger on that FET to see whether it's warming up. It's just lukewarm, is that FET. It's not even hot, so that's a good sign. Right, so trying 7 amps again on transmit. We're getting some frequency there, but we're getting some weird effects there. So let's just adjust this. That's strange, because the bandpass filter for the frequency is not switching in and out in there. So there's something strange going off. It's like there's a supply rail being lost, because as we're doing this, we should be hearing the clicks internally on the bandpass filter selection for the receiver, and we're not, because we definitely had one at 51 point something early in the video. So let's just look at the other frequencies. 29 megahertz. See, it's happening there, but it was not happening at the 50 meg band. Now we've got the out of lock condition. Yeah, not hearing the switch going there for that band, 50 meg. So that's worth noting mentally, because it could be that there's something strange there. That was switching a moment ago, around about 30 megs I think. Yeah, so it does seem strange, does that? Might be 10 meg wide filters, but maybe not. Let's have a look. 28, 24, and Just keep going down. 18 megahertz. Oh, there we are. Look, out of lock condition. Again, VCO going out of lock momentarily. Let's just flick that to FM. Just power set to 50, so we don't want that. We want that reducing down to 5 watts. Let's just key up. Let's try 5 amps. And then again, it's gone off, and I've still got the PTT button held down, and then it comes back. But yeah, it's not producing anything. There's no output power at all, RF. But it's drawing 5.3 amps when it does key up, when the radio display comes back. Let's see whether we can get it to. No, it's not keying up at all. So that band's definitely gone dead. 14 megs it transmits. Yeah, it's drawing 5 amps, but I'm not getting the RF output power coming out of it. I think that's for antenna socket number 2. Just make sure I'm on the right. Still drawing, yeah, I'm definitely on antenna 1, because sometimes the antenna can change with the band memory. So we've got 10 megs, and does that transmit on FM or with a power rating at 5 watts? That's gone as well now. So that VCO is out of lock, and we're not getting any TX. Pressing the transmit, there's no current consumption, and it's going out of lock. So yeah, let's try the 3 meg band then, FM. It may be as well that I was on the wrong frequencies earlier. I've just remembered, because if you're out of band, it won't let you transmit anyway. We've got the speaker disconnected, so it normally give like a double beep to let you know that you're out of band. So there we are. We've got 5 amps being drawn, but we're not getting any RF power at all or anything like that indicated. So yeah, there's something weird going on there. And yeah, it's not letting me queue up at all. Meter band, 10 meg. Just allow me to draw. It's drawing 5.2 or 5.3 amps, then it goes off. No matter what you do, it's not letting you. There's no output power. So yeah, it looks like as if we've got problems, obviously, with the yeah, it's drawing about 5 and a bit amps. I reckon that's the biasing me for the power transistors that's drawing that current, but there's no actual RF there at all. Okay, so let's just check the receiver as well on UHF VHF, because we seem to think that those were working okay. The UHF VCO, and we'll just check the receivers now and see whether they're working. Okay, plug the speaker in. We're on 435 megahertz dead, so we'll just check the receivers working. Now, interestingly enough, I'm not getting any squelch on the subband either, or on this, and I can't hear any speaker. That's a squelch off. And I'm not getting anything there. So right, so let's just set the test setup then. So we'll go to receiver test, RF gen frequency 435 megahertz, RF gen level. It's currently set at -80 dBm, and looking at the radio, we are getting a signal indication. Now, as I wind the RF signal level down, if we keep an eye on the on that, so just get it down to about that's -100. Oh right, I see. So that's -113 dBm, which in microvolt terms is actually 0.489 microvolts. So it appears to be wind it down even further, and the signal there, as you can see, is disappearing. And then that's 0.2 microvolts, and that's now 0.5 microvolts. So it is receiving okay with the look of it. So I'm just increasing the RF level now. That's 1.4 microvolts. So the receiver seems to be operating, but there's no speaker. So yeah, I'll have to look at that. Maybe the audio amp stuff or the supply rail to it maybe packed in, but I'm not getting anything at all. But it is indicating a receive, because if we just switch that off a second, you can see there's a green light, which that goes red. Well, it's not particularly bright on this radio, again maybe supply line issues, but that goes green to indicate receive and red to indicate transmit, and that indicator there is for the subband, which is when you press this in, and then you get the subband receiver and transmitter there. So we'll switch that off just for the time being, but so yeah, the indication's there. So if I key up, it should go red, which I'm transmitting now. Unkey, it goes green. So if I switch the RF gen off, obviously we've got no green light. If I switch it on, we have got the green light. So if I switch it off and then I back this controlled off here for the squelch, that goes green to indicate that now the squelch is open. But we've got no audio, so is this pot duff? I'm not sure, I doubt it. They're normally quite reliable, so I'm just going to have to check this speaker out and see whether or not there's anything which may indicate an issue. I mean, it does look, the radio sort of had a bit of corrosion on the lid and that, so whether it's had water on it or something at some point, I don't know, but looking at it, it don't look too good. We've got this copper wire there that goes to the diaphragm on that side, looks in reasonable nick, and then on this side it looks pretty bad. It doesn't look good at all, that. So maybe there's something wrong with it. As you can see there, it looks pretty corroded, and there's all this dust and fluff and goodness knows what else. So not right sure if that's stuffed, whether it's repairable, if it is duff or what, I don't know, because I don't think I've got one of these speakers. Let's just have a look in my parts bin, I think, and see what we've got, if we need to replace it. So I'll just measure it first, just unplug it while it's still on, and just make sure that that's it, they don't touch anything. And we'll just have a look now to see if this speaker's okay. So let's have a look, just verify that before we go any further. Put it on 200 ohm scale. Okay, so touch the probes, make sure that the resistance is there, and let's just go on there. It's open circuit with the look of it then. Let's just verify by going on the touch, just in case there's any tarnish or varnish on there. Yeah, it's definitely open circuit. I wonder if it's reading high, maybe something like that, high resistance. Let's just double check that. Yeah, so it's open circuit is that. Let's just have a look at the wire a second, just to see whether it's there. If we touch it there, yeah, that's okay, isn't it? That side, so that connection to that part of the speaker is all right. What about this side then? Let's have a look. Doesn't appear to be. Looks like this is faulty then. This is corroded, or maybe the coil's burned out. Maybe it's got wet and it's just got all manky inside. It's not getting no continuity at all on that bit of wire. So whether there's any shiny bits down there we can get to, and I should be able to go between this side, which is there, and there, to see whether we get any coil. So I'll just zoom out again so we can see that on the so if the coil is okay and it's connected there, obviously there's a bit of good copper down at the bottom there, so we'll be measuring from there around the coil and then back to this terminal. So if I just go there, let's see whether we've got any resistance. I can't seem to pick anything up. So that speaker's definitely open circuit, the coil. because there's a bit of good copper just down here where it goes into the diaphragm, and I'm not getting any continuity, and there's definitely no continuity between there and there. So not only is that wire corroded as well, it looks like the speaker coil's burned out or something. I'll just have a whiff. Nah, it doesn't smell burned or anything. Could be that there's DC volts being fed to it, because maybe the capacitor on the output of the audio amp, the DC block capacitor's gone short or something and put volts in, but I doubt that. They normally go open circuit more than anything on the audio level. But there's definitely this sort of hard, that don't clean off sort of thing, it can scratch off. So there's been something got into this, which falls into the category of what we were looking at earlier with the lid on the unit. It was like speckled and had some deterioration on it with the paintwork. So it could be that it's been somehow got wet maybe in the past, and water's got in and damaged that up. Right, let me have a look now in the, I'll just put that there, that faulty one. Let's have a look at my drawer here for speaker, see what I've got. I think I've got some collection of them here somewhere. Oh, here we are, look. Right, yeah. Now then, I've got this one. That's just about the size that I can get to. I think it's bigger. Let's have a look. Yeah, much bigger. I'm not sure if a picture of the... No, it's a shame that it's near it, but the magnet's quite deep. Might have to do some funny business with this later on, depending. I'll try and get one that's equivalent. I've no doubt got something that'll do. So we'll just leave that there a second, and we'll just connect this one up. So let's have a butcher's. Let's see whether we can get this connected up. It's more like it. Right, can't get that on there for some reason. Oh, sugar. Bent it over now. Ugh. Right, let's try again. Yeah. Right. That's more like it. Right. Put the RF gen on. And 435 megahertz. Right, so that's the dBm or the microvolt level. Nothing wrong with that. It seems okay. I'll just set the squelch. Check the squelch works. Yeah, there's nothing wrong with that. So that works okay on UHF 435 megahertz. No problem there. Seems to be okay. But we don't get any TX. Because if I go to transmit TX frequency, I could even put it into duplex mode, I suppose, as well. So go into duplex. TX frequency 435 megahertz. And if I now transmit, we're not getting anything at all on the right side of the screen. And obviously if I go into that and then select spectrum analyzer, expand, we're not getting any signal at all appearing, and we're only getting 2.1 amps drawn versus 1.8 amps on receive. So that tells me all I need to know. Right, so we've got a faulty TX on UHF, but okay receive. So let's move bands now and just check 145 megs dead. So we'll just move the aerial connector at the back of here from the UHF position to the VHF. I'll just have to rob that PL259 to BNC gender adapter. Careful I don't drop it like I did last time and lose it around the back of the radio. So we've got that. Connect the VHF port up. Let's have a look, see whether we can get this on. Okay then, so let's go back to what is the settings here. RF gen frequency 145.0 megahertz. So that seems to be okay. Yeah. On the transmit side, TX frequency 145.0 megahertz. And so when we look on the right side here, we should be getting TX power, and there's nothing there. But yeah, if we go to spectrum analyzer and expand on that, we are seeing just a smidgen of a signal at the bottom there. Well, we were earlier anyway, but we're not seeing it now. Now there's very little power there. There's just a little bit of something there, and then it dies off. So it's very low level, if at all anything there. But yet we're drawing 8.5 amps. Okay, so we'll go down to 52 megahertz, which is this, where it was doing a bit of naughtiness earlier. And just go down to 50.5 megahertz so we can transmit, because that's the allocation for the amateur band. Now we're getting that BB tone there, look. There we are. 50.5 if I key up. Yeah, keying up. I'll keep the press the torch switch down. Right, so if I go back to, yeah, it's gone out of lock again there. So let's have a look. Duplex test, RF gen frequency, 50.5 megahertz, RF gen level, and we're not getting anything. Have I put the right frequency? Yes, I have. So let's just back this off because we're on FM. Oh, I know why. Because we need to connect this up to the antenna 1 port, don't we? That's why. Like an idiot. Okay. Still nothing. Switching, just to make sure. We were definitely on antenna 1 before. 50.5 megahertz, we're generating 50.5. I'll just wind the RF gen level up, see if it starts to pick something up. Put like 10 microvolts in, 20 microvolts, 50 microvolts. Deaf as a barn door. So okay, we'll put TX frequency 50.5 megahertz, and so now we'll check that's the fan starting up in the power supply, not the radio. Okay, so we'll key up the transmitter now, and we'll see what happens. It's drawing current, and we're getting some power there. It's gone out of lock, so I'll just see whether we can get it back into lock. Now it's receiving. All of a sudden, it's come to life. RF gen level 1 microvolt. Turn the level down. So now the receiver's okay. So the received VCO must not have been in lock or trying to lock, and maybe it's racing up and down the band, you know, as it would do. It'll be going all over, trying to lock. or perhaps the reference oscillator was moved off frequency, and so the VCO was in lock but not on the frequency that we're displaying, because the VCO, obviously the synthesizer gets guided by the reference oscillator frequency. So if the reference oscillator drifts, the VCO drifts with it, although it'll still remain in lock. The actual receiver frequency that's indicated on the display won't be correct, so that could be what's happened there. So we'll just queue up the transmitter and just see what the transmitter's doing. So we're getting 6 watts there, that's okay. We'll just go on to the expand the TX screen, but we are significantly off frequency there, 97 kHz off frequency on the offset there, but we're doing RF power. So there does seem to be an issue with the VCO synthesizer stroke reference oscillator, so that's definitely confirmed that. Obviously on the other bands below it's just going out of lock now altogether. So I think now we've identified that, because the 50 megahertz band is the receiver, HF receiver, the 145 megahertz VHF receiver, and then obviously the UHF receiver and transmitter, so they're broken into separate modules. So I know if it doesn't work on the 50 meg band, it'll not work on any of the other HF bands either, which is what we're getting. We're getting that issue, and as we try and move the frequencies from time to time or transmit, then we're not. Yeah, again, it's going out of lock all the time now, so we're not getting anything really, are we? So again, 14.2 megahertz dead. If we transmit on that, we got it obviously on FM, the power 5 watts again. If we go to the breakout screen, go to duplex, RF gen frequency, 14.2 megahertz. That's again FM, that's alright, there's no problem with that. Receiver's working fine. TX frequency 14.2 megahertz on the right there, and then if we just look at that now and transmit, and again we're getting milliwatts. Oh, there we are, 5.78 watts, but again we're 94 kilohertz of frequency. So there's something strange going on with the reference oscillator or the VCO, so I think that's where we need to look next. And so yeah, we'll have a look at that back soon. Okay, just removing these screws now, and then we can get this board hinged up and expose the bits we need to get to. Well, that one's loose, that screw, and it's had some markings on it, the look of it. So we'll just remove all these, get this board to come up, and then we can see what else we can get to. Okay, so there's quite a lot of screws holding this board in, but I think I've got them all out now, so just carefully lift that up and just have a look under there just to make sure there's nothing. Oh, there is a cable at the back there, which is this, so we can unplug that for the time being. Nothing there which is going to snag or anything, so we can pull that back. Now it looks like we've got another can. It's about 20 odd screws holding this in, so I've just got to remove these now in order to get to the UHF section and the rest of it down there. Okay, so this is the board that we're interested in, this entire section here. So there's two boards in actual fact. The main VCO board, and then there's also a reference oscillator PLL board up here, phase lock loop board. We've got another VCO on this board as well. So there's 1, 2, 3, 4, 5, 6 VCO modules present on this particular board. Now in the middle here we've got a receiver section, which I believe is for VHF UHF, and then this is a transmitter board for the UHF power amplifier board. So on this particular range of radios, production range, where they modified the radio from being the FET version, I think it was, there was the models that were produced with bipolar power transistors, and as we saw earlier with the power switch on the main board, the older models were done by relays, as per the previous repair video that we did on one of these Kenwoods on the channel. So if you want to have a look at that. So these power transistors originally were bipolars, but then they changed them to FETs. They did all sorts of mods and things to try and better the radio, but then they started with these production problems, which I think they did manage to sort out. But Kenwood introduced, I'm not sure if it was an official mod or it was definitely a nod nod wink wink mod, that was on the VCO board, because there were certain production problems with the VCO boards. Now, one of the main problems is this can here, this one, and I've already removed the screw so I can have a look inside it in a second, but this VCO had a problem where it mates with the board, because when they assemble the radio and they basically dropped the board in, and the module here was soldered, you can see right down there are traces, and if you look you can just see them there. There's all these traces. Now those traces, obviously some of them go underneath this can, right on that very corner where you can see that little tile. Now somebody's already done this modification that Kenwood introduced, but basically Kenwood said that this can was butt up against the PCB and it was touching one of the through-hole vias that goes through the board. So in other words, it would look like these there, like that through-hole connection there, but it was right on the corner of that can. So basically the can was butt up against it like that, and then there'll probably be a couple of microns gap between the can and the board, and then when the radio heated up with use, it'll touch it and then cause out a lock condition, disturb the circuit, etc. So Kenwood introduced this mod where you add an insulating plastic washer underneath, and somebody's gone a bit overkill on this because they've put a square Captain tape thing there, and then put this plastic mat underneath which goes all the way under the module, all the way around and back again, like in a big square. And then in addition to that, there were another problem with this ceramic filter here. So this ceramic filter there, that had an issue where the pins that were coming through the board, instead of in just being a small protrusion, they were really long, and so ultimately then the pins were touching the chassis underneath, all this aluminium that's underneath there. So they introduced a mod to obviously trim the pins down, because they must have missed that in production, and then they also introduced a big plastic, the same material that this washer's made from down there, underneath to cover the whole board for some reason. There was a other issue as well, where when we look inside one of the VCO modules, inside the module itself, the individual VCOs plug in. There's a little socket there. You might be able to just see that socket there, that little white socket just at the bottom of the VCO, just there. So there were plug-in modules. Now what happened was there was a report of solder slivers in here, so some of the components in this board had solder slivers, and therefore they unfortunately caused problems, and it must not have been the finishing process of the board done more refined than it should have been. There's issues with these trimmer capacitors as well, which we'll discuss when we look at the circuit diagram as well, and the theory of operation of VCO circuits, that this sometimes gets dust and filth in it and suffers with erratic operation. So there was that reported. And in addition to all that I've just mentioned, there was a final mod that was done. I'm not sure if it was on this connector down there, but certainly one of these connectors, the sockets themselves have got some little satellite islands that come off the pins on the socket, and therefore you can solder other components on there to ground, if you like. And they introduced a load of 22 picofarad capacitors that had to be soldered across there to, I think, to sort of stabilise the VCO. Now, just incidentally, and we'll look at these on the diagram, these are two voltage regulators that supply a 5 volt and an 8 volt rail to the whole of this circuit. Now on this board here, there's the voltage controlled oscillators reference oscillator module there. So the VCO PLL system, if you like, has to have its reference. The heart of the radio is what's called a reference oscillator, which is sitting on this board somewhere. I think it's in under this can, and basically that produces a fixed frequency of either 12.8 megs, 15, 14, whatever megahertz it produces, and that then gets distributed around, and I believe that's distributed around on these smaller connectors here, these little ones, and it also goes off as well to the neighbouring board there as well. So that signal gets fed around for the VCO synthesizer circuitry. So that's something we'll need to look at, because if this frequency that's coming out is changing in frequencies, we'll discuss next when we talk about theory of operation, then that will also cause out of lock condition as well, because the VCO will start wandering off all over the place. There could be a supply line issue as well. Perhaps there's some issue with these voltage regulators being unstable. There's all sorts of possibilities on this board. It could be the amplitude of the reference oscillator is too low, it's going up and down in amplitude as well as frequency. All sorts of different things we'll need to look at. There's certainly some things to consider there, but at least that modification's been done already, so somebody's obviously been in and messed about with this particular thing. So with that said, because I don't think there's much else we can say on that, if we just move over to a piece of paper now, what we've got on this radio is we've got obviously, as I said, a multi VCO PLL. Most radios, PMR radios, LMR radios, etc., just have one frequency band of operation, but naturally this radio operates on multiple bands, multiple frequency bands across the VHF and UHF spectrum. So what we have on this is multiple VCOs, but each VCO has its own phase lock loop synthesizer IC. So basically, in this system, we'd start obviously with a reference oscillator, okay, and the job of the reference oscillator is to provide a fixed stable frequency, say for example at 12.8 megahertz. Excuse me, and that's outputted, that continuous frequency, all the time to what is a PLL synthesizer IC. And at one time of day, what we're going to discuss in this next was all separate components, but in these days it's all in one component. So this is a phased locked loop PLL IC, and this gets a reference in at that constant frequency. Now these are high stability, parts per million, if you like, accuracy oscillators, very stable. On some radios, the temperature controlled oscillators, and others are oven controlled oscillators, so like TCXO, OCXO variants, very expensive modules, and normally they just get a supply of say +5 volts, and then they give a signal out continuously. Often there's a trimmer capacitor inside, so you can adjust the frequency of the reference oscillator. We net that using our radio frequency test equipment to attain the correct frequency that it should be coming out with, and that is the heart of a radio. Without the reference oscillator, the radio would simply not work, and that frequency accuracy of a radio, both in terms of reception and transmission, is purely controlled by that reference oscillator. So on the PLL IC as well, we've got a control voltage line coming out, which is what we call tune volts, and that goes to what's called a VCO, voltage controlled oscillator. You could also call it a variable frequency oscillator or a VFO, but its true term is a voltage controlled oscillator, and in it there's a varactor diode, a variable capacitance diode, and that variable capacitance diode can tune its capacitance with a DC voltage applied to it. So it's a bit like having a tuning capacitor like we used to have on old radios, where there were vanes that went like that, interleaved between each other, and then as we turned the dial, then the vanes came away, and the capacitance varied as the vanes entwined with one another and left an air gap. There were air gap capacitors like vanes. So this is like an electronic version of it. So that line, that tune volts line, so I've got a DC volts that goes up and down in amplitude depending, and we'll discuss that, and also there's something called a loop filter in between, and the loop filter is this particular gadget, and this gadget here, if you like, the loop filter, is for filtering out the pulse width modulation, the PWM, that is present on this line here, which we'll look at very shortly. Now then, what we've also got then on the output of the VCO, we've obviously got the fundamental frequency, and the fundamental frequency is then also fed off to the TX and RX sections of a radio to form the transmit drive, if you like, for the radio's transmitter, as well as the receive local oscillator for the first mixer stage or second mixer, etc., in order to get the receiver to work. So if you like, the frequency that's coming out of the VCO is variable. It can change in frequency depending on the DC volts line here adjusting, and we're going to look at that very closely. And that then has to be sampled back in. Okay, then what we've also got is, in order to program this IC so that this VCO works at the right frequency, older radios tended to have like 8 data bus lines, you know, 1, 2, 3, 4, 5, 6, 7, 8. So you've got data bus bit 8, 1 to 8, and they went obviously off to the what was the microprocessor, and alternatively, or a diode matrix board, etc. It was a fixed frequency radio or whatever. But more often these days we have a serial data line. So if I write that as serial data, and then we add a serial clock. Now serial clock, serial data, and then obviously GND for ground, that programmed again from the MCPU. As we're changing the dial on the front of the radio, we're tuning to different frequencies. There's data going in there from the microprocessor to change the frequency of the VCO. So in terms of how this system works, what we have is we've got a comparison between, if you like, A and B, which is coming in here. Now this is a fixed frequency, this is a variable frequency coming in. So we've got here the output of the VCO being fed back in a sample, and that sample arrives back into the port B, if you like, of this phase lock loop IC, and thus B is compared to A. However, because the frequencies are so different, there's a programmable divider inside. There's two, one on the B port, if you like, what's coming in from the VCO, and then there's another one, if you like, internally within here, which is also for the reference oscillator. And these are programmed, these programmable dividers, by the data coming in from the microprocessor. So if we look at that more carefully now, what we'd have if we broke out this VCO PLL IC into separate components like it used to be, you'd have obviously your reference oscillator that we've discussed, which is often in radios, as I say, running, say for example at 12.8 megahertz, and this basically produces 12.8 megs in our case here, just as an example. It probably won't be on this radio, but we'll find out on the diagram when we look at that next. That's obviously the fixed frequency. It doesn't change, it shouldn't do, but as we say, we've got a trimmer cap, we can adjust it if need be. And then that essentially will go into what will be a programmable divider, which can be programmed by the microprocessor with data buses, and then we would go into what's called a phase comparator. And this is where the important bit happens. Now the phase comparator, if we keep it in true terms with this IC, is port A, port B, and again on the input to that phase comparator on B port as well as A port, we've got another programmable divider, again lots of data lines going off. And then what we have then here, we'd have a loop filter. Now the loop filter, which I'll explain shortly, normally has an RC network in there, and the way this works is that it's designed to filter out any of the PWM that's coming off the output of this IC, and then that is fed into a VCO, a voltage controlled oscillator. And then what we have is an output signal from that voltage controlled oscillator, which can vary in frequency depending on the DC tune line. So we've got a DC tune going in there, and then the output of this is then essentially fed back into the input programmable divider, and at the same time as well we also take a little sample off that and feed that to our TX/RX for the drive. So how that works then, when we analyse all those individual components now that are in this IC, is obviously we're programming these programmable dividers. Now this used to be called on its own in the bad old days a prescaler, and often they're divided by 64/65 depending on frequency, all the characteristics about the programmable ratios, division ratios, but they tended to be 64/65 division ratios. These are normally, depending on how the radio is designed, can be programmable dividers or fixed dividers. But basically what happens is we divide down the 12.8 megahertz reference signal to quite a low level, because these ICs, these comparators can only work at very low frequencies typically, certainly up until recently anyway. So say for example there was a 2 megahertz signal present on there, and that's after we've divided the 12.8 megahertz down, we get 2 megahertz just for argument's sake coming in on port A. And this VCO in the first microseconds of turning the circuit on could be anywhere on the frequency band. And say the VCO's bandwidth, operational oscillating bandwidth, is 100 to 400 megahertz. It could be anywhere in that point. So within the RS spectrum of 100 megahertz to 400 megahertz, that VCO could be, if it's a cold radio, for example, when you turn it on, it could be right down low in frequency, or alternatively it could be very high in frequency, or it could be moving about and doing all sorts of weird undesirable things. So what happens is the output frequency, whatever frequency it's on in the very first few microseconds of a circuit turning on, goes back into what is the VCO's phase lock loop programmable divider. The microprocessor has already programmed this particular divider to the frequency that we want the VCO to run at. So that's already been programmed with its data, and it's now dividing down whatever frequency is coming in from the VCO, and we're getting then whatever frequency present on port B. So let's say for example it's now 2.4 megahertz. Because this is stable at 2 megahertz coming from our reference, our internal clock if you like, and this is now off frequency because the phase is different between A and B, the frequency is different. So it's 2.4 megahertz, it's 400 kilohertz higher than port A. It means there's a frequency error in this VCO, and it's not on the frequency we want it to be on. So straight away this phase comparator, which is this device, changes its output. And the way these work is they give what's called a pulse width modulated output square waves, and these vary in amplitude and mark space depending on whereabouts the VCO is with regards to its steering. So if that's 0 volt, this will be plus territory normally. Anyway, that comes out as square waves. This loop filter here, which is in this section, which is an RC circuit, filters out that pulse width modulation, and so then present on the VCO tune volts line you get a nice steady state voltage. So if this is 0 volt and that's plus say 10 volts, what happens is then is that the output, whatever it starts at, will start to move. Say it goes into positive territory, so it'll apply a higher voltage then to the tune line to the VCO. This will then change the variable capacitance of the diode and thus steer the oscillator one way or the other. So first of all it'll try and think, right, okay, it's high in frequency for example, so I'll move it, the tune voltage low, and then obviously it'll then see the output change. Now once it sees the output change, it gets fed back, compared again in the comparator, and if it sees that it's going too high in frequency, then it'll change its state again, and thus it'll alter the voltage. So the voltage will steadily throughout the radio's operational range, and frequency will vary and go up and down all over the place. And there's two reasons that happens, because obviously depending on what frequency you want the VCO to go at, the tune voltage will need to change anyway. But in addition to that, temperature changes and mechanical disturbances and the physics of inductors and capacitors changing the physical sizes when the circuit heats up and cools down, and those influence the oscillating frequency. Indeed, even if you brought your hand near the VCO circuit, you know, and you would affect its stability. So what happens is the output frequency gets divided down, fed back in and compared between A and B, obviously. If a frequency draws very close, because we're steering this VCO to the right frequency, and as this reduces down this signal to the correct frequency of 2 megahertz, then both these are in phase. So this works out how to steer the VCO. It'll either steer it one way or the other, but it will know how to change its output depending on where the VCO needs to run, and it will then pull the VCO, it'll steer it onto frequency. And once it's on frequency, these two are said to be in phase, and that means it's phase locked, because what we've got a loop which essentially is going round from here all the way around and back this way through. So that's the phase locked element of it. Now if there's a fault condition occurs in this VCO and it can't be adjusted to frequency, or this phase compactor or this reference oscillator goes off frequency, then obviously it can't pull the VCO onto frequency. The frequency is wandered too far off, and there's only a certain range, what's called a capture range on VCOs, so PLL synthesizer circuits, where you can grab a VCO and pull it back with the steering voltage. And if there's obviously a component failure within the VCO, no matter what this does, this loop filter and the output of the phase lock loop, voltage can vary violently up and down to tune it. But if it's too far off frequency, or it can't be pulled back because of reactor diodes packed in or some other component failure in there, it will go out of lock. It means this synergy of lock there that's attained, where the tune volts comes out, the VCO is put onto frequency, the sample of the frequency is fed back, it's compared against A. If there's the frequency is the same, then basically there's little change on the output. In other words, there might not be any steering voltage coming out there, but if the VCO starts to wander off with temperature, or we change the frequency, or with a dial on the front, then these pulses will narrow or widen in pulse width in order to then create a more of a DC or a less of a DC voltage, depending on where we are. And often when we look at the output of this, as we bring his hand closer to a VCO, try and disturb it mechanically by sticking his finger on the board or something like that, then these pulses will get quite wide in pulse width, so that then this loop filter can produce more of a higher voltage and try and tune the VCO. And likewise, if we bring his hand away and the VCO is allowed to then resonate at the right frequency, then these pulses can often go to just little rakes or none at all, depending on where we are. And often as well, these VCOs can go into negative territory, so we can actually have negative going pulses as well. And there is a particular way that those VCOs can either be tuned in negative territory or in positive, if they've got a very wide swing tuning line on them, tuning voltage. So we can have both positive and negative going tuning voltages on some VCOs. Often the game is given away when we look at the loop filter. If these capacitors are polarised, if like tantalum caps that are polarised, then it's only in the positive territory, you know, in this area. However, if it's if these capacitors here are non-polarised, then sometimes it can go into the negative territory, can the tune volts, so it can go either way, and they tend to be on some radios. But the basic rule of thumb is, as long as a reference oscillator is stable on its frequency, and the VCO can be tuned, then it'll be in lock. It'll be a phased locked loop, hence the term PLL. So we're dividing the frequency of the VCO down, comparing it against the reference oscillator, which is also divided down. And if the two are in lock, they're in phase, obviously. The output, the tune line, keeps the VCO locked constantly. So within the first few microseconds of turning the radio on, all this happens instantaneously, and it locks it straight onto frequency, pulls it, the VCO grabs it wherever it is on the radio spectrum and goes yank. I want you on this frequency, and then the output of the VCO then is maintained on that frequency. However, if a VCO goes faulty, or the reference oscillator goes faulty, either or, and either of them can wander off wherever they go, then obviously it'll try and tune the VCO, and if it can't, it'll give up. So that's why on these PLL ICs we have an out of lock line. So if it's like out of lock, that goes then to the microprocessor, and sometimes they can be active low, active high, depending on the logic output of the device. So that'll go to the microprocessor to say, well look, I've tried to lock this VCO, I can't get the VCO into lock, something's wrong. So what it'll do, it'll then tell the microprocessor to shut down the receiver and the transmitter and prevent it from going into able to transmit. Because obviously if this VCO is racing up and down the radio spectrum and you're allowing it to transmit, then it can cause massive interference to the radio users and potentially transmit on frequencies it's not meant to transmit or receive on. So that's one of the reasons why we have this sort of lock line detect on the PLL. And in this particular case, a radio will display dashes. On other radios, it might give a warning, audible sound out, as well as prevent the transmit button from being pressed. You know, it won't go into transmit or it won't receive. So that's the basics of it, really. There is a lot more that goes on as well inside these, but these are just the basic elements of it. Now, these VCOs, obviously quite wide banded on this radio, so they'll have a quite wide frequency range, but there is a capture range that this circuit can work in. So what tends to happen is if a VCO has gone too far off frequency, it can't divide down enough or divide up enough in order to be able to get the comparison between A and B in phase. So what it will do then, it will not be able to grab, it'll not know how to do that. All it can do is just go from one range, its lower limit of tune volts, to its highest range in tune volts. And if it can't get this VCO to give a correct output back, then it'll just give up, and then the lock line will change and it'll tell the microprocessor there's a fault. So in order to try and help that system in those first microseconds when the radio's turned on, the VCO itself, the VCO module, has within it a little trimmer capacitor, and that trimmer capacitor is there to adjust its central frequency of resonance. So what typically happens is on the tune volts line here there's a test point, and that test point denotes in the manual what voltage there should be at a particular radio frequency. So it will say tune the radio to X frequency and then monitor test point 1, for example, and if test point 1 adjust TC404, the trimmer capacitor within the VCO, to attain a particular voltage. And so what happens is we're tuning, if you like, the radio spectrum, if you like, say that's 100 megahertz to 400 megahertz. It will say tune it to, say, for argument's sake, 200 megahertz. So we'll put a 200 megahertz frequency in, and we're expecting the center frequency there to equal 200 megahertz. And there's a reason for that, because that center of the oscillating frequency band of the VCO's characteristics. So although the VCO might be able to oscillate at lower frequencies and higher frequencies than that, its amplitude won't be of a correct level and it will be unstable. So therefore the trimmer capacitor that's in there is designed in the circuit so that we can tune that, so we get the radio's lock line, if you like, the tune volts line, to a particular voltage, which means that it's in its limits then, because this output of this comparator can only go between certain DC volt tune limits. If this VCO is allowed to go too far off frequency, in other words, it's gone out of the capture range of the programmable divider and the synthesizer, it'll be oscillating at a frequency that it can't influence then. The output of the phase comparator cannot influence the VCO. So it'll have wandered way off, and then the tune volts will go up and down its full range, and it'll just give up because it can't pull the VCO back to where it needs to be. So the idea is the tuning capacitor there, if we didn't have the tune line going to the VCO, it will be free running. So what we do is we tune this capacitor in essence so that it's within the centre of the band. When you first turn the radio on, in essence, those very first microseconds while the PLL's starting to run up, even before you've even able to touch the radio and the display's still doing its self checks, this thing is running off on a different frequency and it's trying to pull it back. So the trimmer capacitor is designed so that it keeps the capture range of the oscillating frequency of the VCO within the limits of where it can capture the VCO's frequency and pull it back. So often if these are maladjusted, somebody's been in and they've tweaked it right the way around and knocked it way off, and what happens is as we're going up and down the radio frequency dial on the radio, or trying to program at different frequencies, it'll go out of lock quite regularly because the VCO just simply cannot keep on frequency, and this tune voltage will be out of its limits. In other words, it will go out of lock. So this loop gets broken and the VCO starts wandering off onto frequencies it shouldn't be. Also, the reference oscillator, if this starts to fail because it's gone faulty and this wanders off frequency, that will affect everything else as well, and you only need very small changes in frequency at the reference oscillator in order for it to have a massive change here on the VCO, and that's simply down to the division ratios that are employed here, and it's like a multiplication factor. In other words, we only need a few hertz difference here to change many kilohertz or hundreds of kilohertz here on the output of the VCO because of the way that the dividers work. So if this starts to wander off frequency, then the reference for the whole system will start to move with it. So, you know, it's a bit like having a 1 kilogram weight, and if you then saw it in half and only have 500 grams, and then give that to somebody and say, well, that's a 1 kilogram weight, and it actually isn't, it's only 500 grams, and you weigh everything then against that reference, then that's obviously going to be wrong. It's only going to be half a kilo instead of 1 kilo. It's the same that applies here. This is the heart of the radio, and this is what everything's referenced against. So if a reference is wrong, everything else will be wrong. So we'll need to look at the reference oscillator, its frequency, its level, as well as the VCO, and tune that capacitor there so that it allows a central operating resonance of the VCO to be stable. And we'll need to look at all the voltages and everything that apply to all these ICs and parts in order to find out perhaps where the fault may lay. So that's why we have that little trimmer cap and that little hole in the VCO, because even with the lid off the VCO, like we took those 3 screws out and removed the lid so I could show you inside, even with the lid off, the VCO won't be running on the right frequencies. You put the lid on and the VCO will start to work normally at its frequency. Very sensitive, the VCOs. You only need to bring your hand near them, or temperature changes and they start to wander all over the place. So that's why alignments around the VCO are quite critical. So that gives you a little rundown, a basic overview, and it is a basic overview of how that works. So we'll look at this now on the circuit diagram more in depth. Okay, so where we're at now is we've got the radio connected up to the radio test set. We're using what I call the coax of truth, which is direct 50 ohm coax with 2 clock leads on the end. Great for doing measurements under around about 30 megahertz, because the risk of RF radiation and escaping from these exposed cables is very minimal at that frequency. Different case, of course, obviously at VHF high band and UHF and up in the microwave spectrum. These cables would be totally inappropriate for measuring those signals. However, in this case, because we're only interested in measuring 15.6 megahertz from the reference oscillator, which is on this board down here, we only need these sort of basic cable setups. So we have a Standard 50 ohm coaxial cable with 2 crock leads at the end. One goes to the chassis, the other goes to the pin on the connector that carries the 15.6 megahertz. We connect that in on the TNC high sensitivity port on the radio test set, and we've then got the spectrum analyzer connected up. We've put an input frequency in of 15.6 megahertz. So when we switch the radio on, we should be expecting that signal. Now, as far as the circuit diagram is concerned, our connection point is actually up here on this connector, because down here is the reference oscillator. It goes through a buffer amp, branches in all sorts of different ways, and as you can see, it goes up across and connects to this connector. So we've got a wire lead plugged into the signal line on this connector, which connects to that coax of truth. Now we're going to be measuring the 15.6 megahertz coming in before it gets to the doubler stage. So you can probably see that a bit more clearer now. So that's where we're at here, this connector at the moment. So we'll be able to see the front of the radio as well to see whether the dashes appear on there at the same time as monitoring the spectrum analyzer. So what I'm going to do now is I'm just going to turn the radio on and then let's see what happens. So currently we've got the frequency. Oh, now the dashes are on. Now the frequencies come back. So it's intermittent, but I could already observe the frequency and amplitude of a signal, which is there, 15.6 megahertz. It's bang on frequency, and when the dashes appeared on the display, I couldn't see that disappear. It stayed there and didn't move in frequency. Because I've entered the frequency directly, we've got the offset value, which tells us how far off this frequency of a reference oscillator would be, and as you can see, it's only 8 hertz off roughly. Now if I turn the band on this radio, see if we can get the dashes to appear again, because they were appearing. Right, just have a look, see if I can get it to fail. So far so good, the dashes haven't appeared yet, but they may do at any time. But it's looking good at the moment. Yeah, looking good. I'm just going to tap around this board, see whether I can get anything to change, but staying pretty concrete at the moment. Yeah. Oh, dashes are on now. Yeah, dashes are on. Yeah, so that's not changed. So it's not, so far the reference oscillator's 15.6 megahertz frequency, although there is obviously a doubler, which we can see there, this doubler circuit here. So I think I'd like to be able to check that, because some parts of the system run directly off of 15.6 megahertz, as we can see the ref in there for this VCO, which is here. That PLL IC that deals with that VCO just gets 15.6 megahertz in, and obviously that signal as well splits down here and then obviously goes into this reference input on this PLL, which deals obviously with this other VCO. So different frequency bands have different reference oscillator frequencies, so when it's not till we get onto this board after the doubler, so it obviously doubles it up, that then the frequencies on this board are obviously higher. So we'll just need to check, I think after the doubler now on this circuit, just to see what frequency that is and whether the levels change. Now I can, because this is a buffer amplifier here, the signal that's been doubled comes down here and goes into this amplifier and comes out, and then there's another connector there which will be easy to connect on. So I'll now move a spectrum analyzer to this port and we'll measure the frequency and level while seeing whether the dashes appear on the display. That will tell us if there's a problem with this amplifier or this doubler circuit. Back soon. Okay, so I've moved the coaxial cable connection now from the W501 socket and moved it over to what is W503, which just sits below here. And this particular pickup point is actually after the doubler now, so 2 times 15.6 is 31.2 megahertz. So what we've done is we've selected the transmitter frequency now, the transmitter monitor frequency, to 31.2 megahertz. So we're going to do the same test over again. So I'm just going to switch the radio back on. So here we go, switching the radio on, and we've currently got a frequency readout on the display at the moment. It looks to be only about, you know, tens of hertz off there, for about 17 hertz thereabouts off frequency. So I'm just going to mess about with the radio now, see if I can get it to display dashes again, and so far so good. It's not displaying any dashes, and I suppose I just have to wait and see if it comes up with any dashes, but it isn't doing at the moment, so that's strange. Let's just keep trying, see whether we can get it to do that. So far so good, no frequency dashes coming up, we're out of lock. Seems to be fairly stable at the moment. Oh, it just blinked then, did the dashes. Let's see. Sometimes it blinks really fast, you see, does the dashes. Oh, there we are. Right. So I just saw the dashes briefly appear for about 2 seconds, and while that happened, the spectrum analyzer out measured level didn't disappear. So it wasn't as if there was sudden collapse in level or frequency inaccuracy. It seemed to work fine. So just having a look, see if I can get it up to there. Yeah, it seems to be rock solid at the moment. We did have a brief period where the VCO was showing dashes, but only just for a couple of seconds. And of course, you know, this is always the case when you get near to tracking a fault down. This is when you actually start to, the radio starts behaving itself. It's just typical, isn't it? You know, when you're trying to measure a signal to prove a fault, then the damn thing starts behaving itself. But I'm fairly confident that it isn't the reference oscillator or the doubler, because the dashes did display just for a brief couple of seconds on one of the frequency bands, and the output amplitude for the spectrum analyzer they're measuring didn't show any degradation or frequency inaccuracies. So I'm fairly confident it's nothing to do with the reference oscillator. And would you believe it? It is actually working okay at the moment. So one begs the question whether putting pressure on that pin with the measurement coax on it, whether that's actually forced a dirty connection or a dry connection, because the thing's rock solid at the moment. So just shows you, doesn't it, you know, how you can't get these things to go faulty when you need to, but this is the way it is. So we'll keep persevering and see whether or not, you know, we can get the dashes to display. But so far so good. It's definitely been alright, is that. Well, what I do, I cannot get those dashes to appear on the display now, which is unfortunate, but maybe giving it time. We will just come back and confirm as and when the radio warms up and the dashes appear again. But yeah, just seem to be behaving. Oh well, we'll be back when it comes up with the dashes. Okay, so what I've done, I've terminated the UHF TX output into the radio test set on the end port, and although it's not selected, it it is terminating the RF power into the radio test sets 50 ohm load internally, but we're still on the high sensitivity port, connected obviously down there to the double circuit on 31.2 megahertz. So we're still observing a signal there. However, when I go into transmit, obviously the transmit VCO goes out of lock sometimes, so I'll key up, and currently we're drawing 7 amps, and then what happens is it tends to go out of lock after a few moments. It's still drawing 7 amps at the moment, but every now and then it packs in, and it doesn't seem to be going out a lot right now, but it does momentarily every now and then. So I'll let you know when it goes out a lot, but I'm just keying the transmitter up at the moment, and that's obviously going into the 50 ohm load. There we are. And it's just unkeyed momentarily, then it went unstable, did the VCO. There we are. It's now gone to full 5 amps there, and then jumps up 1.8 amps, so there we are, and it starts transmitting. There we are. It's just clicked in fully again when the VCO went into lock. So as the VCO is going out of lock on transmit, it's having no effect at all on this this frequency here, which is a reference oscillator. So it's not like as if there's an issue with that. However, with that said, because we're on the main radios on 14.2 megahertz, if I just switch over to the high powered port now and introduce a higher reference level so that it can read the TX power. If I do a TX frequency 14.2 megahertz and then key the transmitter up on there, you can see we've got some RF power there, but look how far off frequency it is though. It's 4.139 kilohertz off frequency. It's doing 4.85 watts, which is fine, but its actual frequency is way off, and the reference oscillator frequency is actually quite good. So, but it is drawing 7.3 amps at the moment, while it's only doing 4.8 watts on transmit. So I think the biasing for the PA might be off as well. Somebody might have had a tweak at that, but we've got 14.2 megs there, but it's 68 hertz off frequency, so it's more or less on frequency, give or take a few hertz, which is a big difference from where it was just a few moments ago. If I unkey and then key up again, let's see how stable it keeps itself. And while that's happening as well, I'll just tap the VCOs to see whether, you know, there's anything possible that might get it to go off. So whether it's the lock voltage, and you can see my mod there on the spectrum analyzer, but I cannot get that now to fault. Just unkeyed momentarily and just keying back up again. There we are. Look, it wouldn't key up in time, it wouldn't get the lock. I'm keyed down now, my fingers on the button, and then suddenly it comes up, unkey and key back, still, yeah, now it's off frequency. Do you see it just then? That's that first time it just jumped off frequency. Now it's on frequency. I just unkey, key back up. Sometimes it has a delayed transmit. There you are, look, then it's just kicked back in, so that were a delayed transmit. That, pressing the button down, still nothing, now it kicks into life, but it's more or less on frequency. Let's just have a look. No TX now. It's trying to come up. Oh, there, look, so you got a burst way off frequency, and then there it is, it's there. So there's something weird. There you are, look, it's off frequency again. Look, 2.5 k's off frequency, roughly 1.8, and then suddenly, you know, it won't come back to frequency. But if I unkey, because obviously it's, you know, 1.7 k's off frequency or thereabouts, if I unkey and then rekey, it's back on frequency. So there's something strange there. Unkey, key back up, nothing, and then there's a bit of a delay there, about a second. Now it's back every time. Nothing. There you are, look. Now it's back on, but it's off frequency. 670 Hertz, and it's 67 Hertz off frequency. So every time it keys up on frequency, like now I've got the PTTL down the last 5 seconds, and there's a burst of power there on off frequency, another burst. Anyway, it's 68 Hertz off frequency. Keyed up, now it's 4.1 kilohertz off frequency rather there. And it will remain like that whenever I'm held down on the transmit button. The moment I unkey and then rekey again, then it will come back to frequency, it only being 69 Hertz of frequency. So it's trying to get locked. There you are, I've got the finger down on the PTT. It took about 4 or 5 seconds there for the transmit to come back. So all during this time, of course, the reference oscillator was running okay. So I think next job is to look at supplies now from those voltage regulators, measure those and see what kind of deviation they're giving in supply rails. Right, so I just want to have a look at the voltages now that's present on this VCO module. As we can see on the diagram, I'll just get rid of that a second and then we zoom in. Each, well, the whole system first of all is supplied by these voltage regulators here, so we'll check these input and output. There's a 7808 8 volt reg and a 7805 which is a 5 volt there, so we'll just check these are running okay, noise free. And in addition to that as well, what we'll also try and check is these AVRs, these ripple filters. So basically you get this supply line coming in and every VCO has got one of these separately. And basically it's the capacitor that acts as a multiplier, so that it prevents ripple from the supply lines from disturbing the supply obviously to the VCOs, because obviously if there's any ripple on the supply line it'll affect the frequency of oscillation. So what we've got to do here is we've just got to check to make sure that we haven't got a, say for example, a short electrolytic that starts to go intermittent or starts to load the base and switches this off. Now I would have thought if that was the case, because there's one of these ripple filters for every VCO, and we'll see that as we're looking here, like there's one there, look, a ripple filter there, and then there's more ripple filters here as well. There's another one there for this VCO and what have you, and then there's another ripple filter there as well. So there's ripple filters absolutely all over the place on this. Now I would have thought if one of these was faulty, then it would just affect one frequency band, and obviously we're getting multiple frequency bands where the issue is prevails. So it's worth checking these though. I don't suspect a fault, but I just want to have a look and see what happens to the supply line going in there to the VCO. We can check them all just to see what's going off, because obviously we've got HF reference VCO here. And other VCOs as well further down, so we can check that. Again, the VHF Very Cap diode oscillator there, and then the VHF reference VCO. So we've got all these different VCOs, so we can just check the supply rails are running to them all. We can go on the sockets as well, you see, on the VCOs themselves by removing the can and touching the pin number 4 in this case on each VCO, so we can check this voltage is getting there while the dashes are on the display. So that's one thing we can do, but I think first of all we'll just check these voltage regulators here and see what's going on. So what we've got the multimeter set up down the radio test set, and we've obviously got the our friend here, the radio, which is switched on at the moment. So I'm just going to turn this round just so I can see this voltage regulator, so I can get on it with the probes. So I'm just going to go on to it with the probe and just measure one of the voltage regulators first. Just got to be careful obviously we don't short things out, because the last thing we want is a big fizz bang and then we're back to the drawing board then, aren't we? So right, so that's obviously the output of the 5 volt reg, which is fine. Okay, we'll just go on to the 8-volt reg now. We'll have a look and see what side we're on. This could be the input. Let's just have a look, just verify that quickly and just get on. It's one of these things where we just got to be really careful we don't short things out. It's so easily done, you know, if you're not careful. Okay then, so that's the input to the 8-volt reg, and this then will be the output. So that's okay. So those two voltage regulators that are on that diagram there, there's nothing wrong with those volt regs. They're functioning. So I think it's time now we whip the lids off of VCOs, and we just went on to these AVR circuits, and then the little ripple filters, and we'll have a look at that to make sure the voltages on these ripple filters here are working, and we'll go on to these pins on all the VCOs. So we'll just take the lids off these VCOs down here, and then we can get access to the sockets then. Back soon. Okay, so what I've also done on this radio to aid the users, I've done a modification with the select resistors that are here for the different options that you can enable or disable on the radio for different radio markets around the world. There are 3 resistors, one there and then 2 here, which needed to be removed. So the radio's upside down with a fan on this side. So basically, if we zoom in, the ones that are removed to enable crossband repeat between both VHF, UHF, etc., or any band, to be honest, and extend the receive and transmit capability of the radio on all bands, is to remove this resistor that goes here across those 2 pads, and there's a resistor across there and there. There are details about this on the internet, which is quite freely available, and that then will allow you to make the radio go to frequencies outside of the amateur band as well, so that aids us with our measurements to do testing on some of the frequencies which is only accessed through the alignment side. Now, one of the things that I don't like doing on these radios is trying to load the firmware for the alignment settings, which is what I detailed in my other TS2000 repair video, because if the data comms to the radio gets interrupted, or there's some kind of a problem with the data transfer, it can brick the radio. So rather than risk bricking the radio through trying to load alignment firmware in there, which is what it suggests in the service manual, what I do is I carry out the mod here to allow extended frequency ranges so that we can get it to the 152, 153 megahertz band, which is where we need to do some testing, because that's some of the frequencies that are used to align the VCO, and the lot voltages are outside the amateur band frequency allocation initially, and then you go back to the AM frequency allocations then to check the voltages again. So rather than try and load all that alignment software in and then end up, you know, bricking the radio, which can happen, and it has happened to quite a lot of people, it's unrecoverable if that's the case and you've stuffed the radio. So it's not worth that risk. So we've done this mod here to allow extended frequency coverage and crossband repeat as well. And what we'll do now, we'll reassemble the front panel and carry on. To share an observation as well with this radio, in carrying out this modification to aid us with the alignments of the VCO, I've disconnected this connector here which plugs in there. And again, another sign of a radio being used in a damp atmosphere. If you just zoom in on that so you can see a bit further, you can clearly see, and I've just cleaned this as well, some isopropyl alcohol. You can clearly see there the discoloration on those pins. So we're going to have to shine those up with a contact lubricant and a abrasive rubber in order to try and shine those up a bit more. But it makes me wonder what the other flexes are like that are on the radio as well. You know, are they, some of these, in that condition as well? So I might unplug them and inspect them to see, because that obviously could cause potential issues, and we don't want, you know, get into a situation where you know, we're noticing again here discoloration on there on those pins, signs of corrosion. See it, clear signs of corrosion there that's going off. So again, is this actually causing the VCO fault? Maybe there isn't actually an issue with the VCOs themselves. It could be these flexes that are, you know, the voltages are not correct, get into places. I've just wiped that with some isopropanol, but that's in a bad way. That's not in a good way at all. So I think I need to pay attention to some of these flexes, because clearly there's an issue here with the radio having some kind of water damage, etc. At some point. So as you can see, you know, that's just this one. What about the others? What are they all like? So I think we're going to have to start inspecting those as well. Again, we're leading off down another garden path here then of looking at those, because if they're not right, that's going to cause problems all over the radio, you know. So we're going to have all sorts of issues. So continuing on this theme of these flexes, this flexi here goes down to what is the VCO assembly synthesizer. So this is quite important. So let's just walk this one out and just double check to see what this one's like. Is this got any corrosion on it? It looks quite nice, that does. Can't see there being any problem with that, so that's good news. Right, so we'll give them all a clean anyway and see what condition we can get them to. But it's not a good sign, that, you know, when you see things like that. It's very unusual on a radio like this. It must have been in a very, very damp atmosphere for that to occur there. So makes me wonder, it really does. Okay, so that's those pins cleaned up as best as I can. I mean, it's obviously when we look at those pins more closely there, I mean, it's obviously not ideal, but it's better than it was before. It's just one of those things where the copper's now exposed rather than the chrome plating, but that's the best I can get it. At least there's contact there. Although that pin there on the far right, and indeed this third pin in from the right, looks like it was starting to eat in. You can see those little points where it's eating in from the left and right to the pin. So pretty soon, if I'd have been allowed to continue, it'd have corroded it all together. But what I'm going to do now, I've disconnected it from the radio because it plugged in down there on that board, is I'm just going to do, because that end's okay, I'm just going to do an end-to-end continuity check now between the two and see whether or not we've got continuity there and that there's no breakages, because it could still be corroded right underneath where that white area is, and thus it could have eaten away the connection up there even as well. So I'll just double check the continuity is fully there now. Well, they're not looking too happy either, are they? Let's face it, you know. That's definitely not good. Is that, especially these pins there. I sprayed some switch cleaner down there already, but I'm just wondering if I can I've got this diamond file there which has got two sides to it, but I've already put some switch cleaner down, which you can see. So I'm just going to give that a bit of a contact cleaning, just to make sure that the contact surfaces are nice and clean up, and that way then, you know, should make a better connection. Just turn it round the other way so that it cleans the other side, and give it another spray out. Do it with them all. Yeah, pretty bad, this connector. So this is where some of these problems could be happening, you know. You can get led off down all sorts of garden paths with this, and before you know it, you're exploring all sorts of problems from one thing to another, and then going back and forth and this faffing about, you know. So let's just spray some switch cleaner on that, some contact lubricant switch cleaner, and then give it a soak for a bit, and then I wipe down with the old cloth. But oh, it's terrible, is that connector. It really is very bad, is that. So yeah, awful. Some serious problems with water. I mean, these are rusty as well. Makes me wonder, you know, if this radio's corroded in other places. That, you know, we've got these screws for the fan, obviously, screws for that PCB that's rusted. We've got these flexi circuits that are rusted. I've cleaned that connector and put it back in already. So goodness knows where this capacitor is. Got a bit of muck on it. I think that's dirt, or is it corrosion? No, it's just dirt, that. So yeah, it's looking better now, that connector, but I think it still might need a bit of a rework with a bit of cleaning with a brush that I've got, and then just test it electrically. I mean, looking at the connections as well on the PCB, those solder connections, they don't look too good as well down at the bottom, which you can't see from here, but this camera angle right underneath there, there's some connections down there which are looking a bit manky, so might have to do something with them as well. So yeah, that's the socket there that goes off to the other thing, and that don't look too bad. There's a bit of green on it and stuff, so I'll have to give that a wash as well. There's one or two pins there that are a bit manky. I'll have to clean them up as well. But it makes you wonder, you know, it really does. Yeah, so this control head flexi just there, I've cleaned that up nicely as well, best I can. That was severely corroded, was that, but we've done the best we can with that. It looks worse than it actually is, but when you look at it under the magnifier, you can see that all the copper's exposed, and the other, I've been careful not to try and rub all the chrome off, you see, on as much as I can, but only the pins that were heavily corroded have actually got the chrome removed, because obviously it's been eaten away by the corrosion, but the connections are all good. You know, there's no problem with that. That can go back in, and I've been very careful to make sure they're nice and clean. But the socket on the other hand here, I'm just that flex we just looked at plugs in here for the front. So I'm just in the process now of just putting the diamond edge file in, and just literally just cleaning it, that's all, making sure these pins are nicely cleaned up, and that way then it's only one side of this diamond edge file, so I have to turn it over to get to the other side. Just give it a nice clean, and then wash it again with some more switch cleaner lubricant, just to get any crud out that's in there. So we'll just give it a wash, and hopefully it should be okay. If I can get the bloody switch cleaner to work. Right, so yeah, a lot of rubbish comes out of it. Yeah, that seems a lot better. So I think we're ready to reassemble now and test. Fingers crossed it'll may start to work. Okay, so we'll just test this flexi, the one that was more severely corroded, and it was this end pin there right at the end that was really bad. And looks like the technical manager is going to join us in a minute. He's meowing in the background, no doubt giving his technical input at some stage. Right, so just go on to this end pin. I'm trying to do everything just like it's impossible, absolutely impossible. Right, I'll just try and get on this end pin. Right, let's just have a look here and see what we can do. And I can't get a reading there, so is that knackered? It could well be, maybe it is. Unless it's me not being able to get on the pin properly. Oh yeah, we've got a connection there, that's okay. So we'll just check the others as well, just see what we've got. Just trying to get onto them. Yeah, that one's okay. Move on to the next one. And that one's alright as well. So yeah, they look okay. I don't think there's a problem there. It's not a broken connection. That's what I was most concerned by, because if the connection was broken then we'd be stuffed. So I'm gonna connect that back up as it was. It went into there and to that bit, and then we'll reassemble, and Bob's your uncle. Okay, so what I did just before I took this VCO board out is I powered the radio up, did a reset, which is where you press the power, well, you press and hold the A equals B button, press the power on, and then it comes up on the display. Press A equals B again, so you do that and it resets the radio. So I've just double checked the display at the front. It's a lot better. The backlight bulbs for the LCD display, 2 of them weren't illuminated earlier and they were coming and going, and I was beginning to think the filament in the bulb was the suspect, and I was planning later on in the repair to replace those bulbs as well, but it turns out obviously that fault was caused through those corroded connections on the ribbon cables heading to the front. Anyway, I've just done another test on transmit off camera, and it's still going out of lock intermittently, but the transmit and receive LEDs are a lot clearer and brighter. The display backlight bulbs are all fully illuminated now, where they weren't before. There's only 50% of them, and they seem to be quite dimly lit. So that's improved that no end, and no doubt countless other things. But anyway, what I've done is I've taken this out, this VCO board, just to have a look and see what's going on. I can see there's been a lot of resoldering work done here. There's a lot of residue around it. But the Kenwood modification was to clean the, there's like a film on these ground connections here. It was to clean those, make sure they're all nice and shiny and conductive. And that meets this this chassis down here, and as you can see, there's been a bit of cleaning going on, and there's this thing being cut. This, like, you can see it there, all this sort of like insulating mat somebody's put in, and this is all, you know, plastic insulator that somebody's fastened in there. This is this Kenwood modification. Not sure what those blue marks mean, but one of the problems was these pins for this ceramic filter that's just there, that came through and touched down here. So I think what I'm looking to do is just give it a bit of a clean up. I'm going to give it a very close inspection using the magnifier, and see whether we can see anything together. But it was just that with somebody else having a go at this beforehand, I just wanted to be 100% certain that there's been no funny business going on underneath, or any corrosion or things like that. So this is that VCO that's got that insulating mat there. Look, you can just see the plastic washer thing there that goes underneath, which is that Kenwood modification. So they've had that screening can off. We've obviously soldered these, and they all look okay, and then reassembled the can. Again, looks like there's some residue around there. We'll clean that off. This does feel as if it's a bit filmy, does this gold connection there, this copper connection. Again, quite a lot of residue around, but it possibly could come conductive in time, but I wouldn't have thought that's happening now. It don't look particularly dirty, and all the pins look like as if they've been reflowed at some point on those sockets on the VCOs. I can't see anything that's looking bad here. Nothing there that I can see. That looks a bit odd. Just being soldered normally, that. Can't see anything. A lot of residue again around those pins, and again you can see what they're on about in this modification. You can see the glistening there of the residue on these copper connections. You know, when you look there, there's like a big spillage island round it, and it coats all this up here as well. You can just see it in the light as I'm shining it. Same up here, all this residue, and this stops a decent RF ground connection for the VCOs. So we'll give it a right good clean, I think. And again, somebody's resoldered this. Again, another socket for a VCO. All these sockets have been resoldered. So we'll have a look at that, and see what's going on before we then reassemble it and measure it. Obviously at this stage, with the screening cans off these VCOs, essentially means that they'll be quite unstable, but we can certainly do the adjustment. The test points are down here. There's one there, there's another one there, and another one there, look. So all the test points are there, and of course there is another board up here as well, which is just hidden there, which is where the reference oscillator is, and there's another VCO under here again, so there's some more bits and bobs going on around there. So I'm interested in measuring the supply voltages to all these VCOs first, to check all the supplies are there before we then start doing the alignment procedure. And that way then the alignment procedure will be to adjust these trimmer caps, that red one there for example, when we tune to a particular frequency to get a particular voltage on this test point down there, as an example. I'm just doing a further analysis of this board just to go over the soldering, just waiting for the soldering iron to warm up, and I've noticed a little issue down here. I'll just put the magnifier on and then we'll go in right close to the board. You might be able to see it in a moment when I get this thing to work. There's a planet-sized solder blob right in the middle of the screen there on that track. You might be able to just see it, and there it is, that giant blob there. So I'm not sure what that's doing there. We'll have to get rid of that, but that's just an example of the sort of thing that we're dealing with. Now I'm not sure if we can see that better on camera if I try and zoom in, see if I can get this camera to zoom in a bit better, but don't think it will. I think it's going to struggle because of how small that blob is. But basically there's a blob of solder there, look, we can see. So that's just there. So yeah, a bit of a weird one. Obviously I've just got the end of like a scalpel thing here, so it's just there, look, that blob. So we'll have to remove that. So I wonder if for any more blobs. We'll have a look, see what we can find. Okay, so we've got the VCO pinouts here, which we can see. So I'm looking for 8 volts on the third pin in, basically, according to that. So sort of a third pin up from the end here, that way, 1, 2, 3, which should be the 8 volt rail. So what I've done, I've set up the scope on the bar chart on the radio test set so that we've got DC coupling on our test lead with no filter. So the radio's on, and we're just going to check to see whether the voltages to this VCO are correct. It should be around about 7.6 volts to 8 volts DC. So there we are. We're getting just over 7 volts, so it's just a tad low, but it's still okay. So that's on that third pin on the VCO down there. So that's where we're at. So yeah, it looks like as if the voltages are getting there anyway. So that's half the battle. Of course, next thing to do is look at the lock voltages for the VCO. So that means putting the cans back on the top, the lids, fastening them down, and then going through the alignment procedure next. So at least we know that the supplies are getting to the VCOs. There's no issues there with that, so that's good. Okay, so I just wanted to demonstrate that TP test point 505 measurement, which tells us to do 24 megahertz on FM, which we've set it at now on this HF VCO. And this particular measurement that's going wrong is for the HF LO2 PLL. So basically at the moment we've got the frequency there, it's in lock. But the moment I go on to test point 505 there, then I'm starting to read a voltage, which is in this case 1.41 volts. But what I found is occasionally I'll touch the test point and it'll go off like that. So I'm on the test point now. Once I remove a probe, which is now, the frequency comes back, and then when I reintroduce the probe again, I'm on there now, 1.41 volts, and it disappears off. So it's currently measuring 1.41 volts at the moment, and obviously out of lock while measuring the test point, remove the probe, which I've done now, and the frequency comes back. So the mere influence of just putting the probe on the test point causes that out of lock condition. So I think this is where we need to look further now at that board and see what's going off. Okay, so this LO2 we've been measuring, which is this VCO down here, I've removed the can off just so we can get onto these pins on this white socket here. Just want to measure the supply to this VCO, because this is the VCO that's going out of lock when we go on the test point. But I thought we'd have a look at the block diagram anyway, just to explain things a little bit insofar as obviously the transmit and receive paths are concerned on here. Now we've got the block diagram up now of the functional diagram, if you like, of a radio transceiver. And if I just move this screen a little bit this way, we've got here the HF basically range, or 0 to 50 megahertz. This is HF antenna connector for antenna 1 or 2. Then we've obviously got an aerial tuner here, an antenna tuner, and then we've got a transmit receive switch. So basically the TX path comes from below. Obviously down here we've got the power amplifiers there for the HF transmitter, and then obviously the filter for detector for VSWR, etc. And then it arrives here, so it switches between transmit receive. The receive path comes this way, and we've also got another switch here for the HF receive antenna for a different antenna, so you can have vertical, you know, long wire, beam, all that sort of thing on different antennas. You come in here then into this attenuator, through down all this filtering again, amplified front end, and then we hit the first mixer. Now we've obviously got on this particular radio we've got a HF reference VCO, a HF1 main VCO, a HF2 main VCO, HF3 main VCO, and a HF LO2 PLL. And it was HF LO2 PLL which, when we touched the test point 505 with our multimeter, it just went out of lock, which it shouldn't do. Now when we look at this diagram a little bit more intently, we can see that there is effectively two mixers here. There's one for the receiver path and there's one for the transmitter path, and we've got HF LO1 VCO there, okay, and we've also got HF LO2 VCO here, and this is the VCO that was going out of lock when we touched the test point. So as we can see here, we've got the transmitter signal coming this way, if you like, into this mixer, mixes with the LO2 to produce both receive injection for local oscillator for the second mixer, and also the transmit mixer, if you like, for creating the transmit signal. Obviously that gets filtered and then passed to another mixer, which is mixed with the output product of HF LO1's oscillator, and then we obviously get a 1.8 to 54 megahertz signal, which gets passed through this filter, if you like, and then comes out, gets amplified again, goes through, and then arrives at the power amplifier before going out, filters again, and then going to the transmit path. So we can see there that without either of HF 01, and if we just zoom in a little bit, so without that oscillator running properly, or this oscillator running properly, we're not going to get any transmit signal or receive signal properly on HF right the way up to 54 megahertz. So basically 0 to 54 megahertz path basically does not work. So then the next oscillator is this one, LO3. Again, we've got this continuation of the receiver path. So we've got the first mixer, the second mixer, and then what's essentially the third mixer. And again, there's a local oscillator for that, which is this phase lock loop, LO3. So that's that. Then we have here another oscillator there, which generates a low frequency of 467 kilohertz. And then we've got a few other oscillators as well, down here and there. So there's quite a mix of them, and these are all those, you know, 4 or 5 oscillators which we've been doing the measurements on, and all seem to have inaccuracies in their measurements, so they obviously need readjusting anyway. But the VCO we're looking at here now is LO2, and this obviously would explain the reason why we're not getting the transmit burst properly on the right frequency, and also it's going out of lock on receive and as well as transmit when we touch the TP505, which is the lock tune volts for this oscillator. So it could be the supply rails to this are dicky, it could be there's some component failure around this oscillator, it could also be it's just out of adjustment and it's just right on the fringe, on the very edge of going out a lot permanently. But obviously when we introduce a measurement instrument over the tune volts line, we're essentially loading it a little, although it's a very high resistance is the multimeter, high impedance. It's not actually meant to affect it because it's a digital voltmeter, not an analog voltmeter, so it shouldn't be disturbing it, but it is. So we need to do some checks around LO2, but in addition to that as well, if we look at the other side to it, we weren't getting any UHF transmit either, if I remember rightly. I think VHF transmit worked, but if we look again, this is the VHF antenna there for 144 megahertz, 2 meter emitter band. We've got receive transmit switch. So if we just have a look at the TX path, again we've obviously got the power amplifier there for the VHF 144 megahertz. We've got a switch which is a relay which either switches between HF, which is the HF amp there, or the VHF amplifier, which is this one here. And again, that's driven from what is essentially the same source. So although that we're looking at the 1.8 to 54 megahertz signal there, in actual fact, when it comes through here and down to here, it also delivers the 2 meter signal, which also comes from below as well. So this is the 2 meter signal generator, if you like. So we've got TXLO1 here, we've got another local oscillator there, another VCO which is producing a signal. All this mixing goes on then to produce the VHF 144 megahertz signal, and obviously then coming out of that as well, this also produces gets a signal as well for UHF. So both VHF and UHF get connected off here. UHF goes downwards to this power amplifier section, and for transmit that is, but for receive, a UHF receive comes in here. And again we've got other local oscillators, mixers, which are prevalent here. Both the VHF and UHF paths for receive join here in this area before it goes into the first mixer. And again, RXLO1 is responsible in essence for generating the receive local oscillator frequency for both VHF and UHF. So that's important to note, is that RXLO1 would affect the receive of both VHF and UHF, whereas on transmit, TXLO1 is the main culprit for that, and LO31 as well, because these signals mix together in order to produce both the VHF and UHF signals for transmit. And obviously the VHF signal goes upwards, vertically up, enters in the same power amplifier pre-drivers as the HF, gets switched with this relay that's here, and then ultimately then selects the transmit power amplifier for 144 megahertz 2 meters before it's amplified and sent out. Likewise, at this juncture here, from that VHF transmit VCO output, we've also got the UHF filtering here, and amplification for the 440 megahertz band. That's buffered again and sent down this way, because these are obviously pin diode switches, and then amplified by these pre-drivers and final before being sent out. So we didn't have any UHF transmit, if I remember rightly. It did receive, if I recall. We did have transmit on VHF, but not on UHF. We had receive, I think, on both 2 meters and 77s, which is VHF and UHF. So again, there's something must be going on around here, where perhaps one of these local oscillators probably, that's LO1 I think is running okay, and according to the diagram I've got here, the UHF LO1 is, it talks about here, it should be 6 volt. It was reading 5.91 on 449 megahertz, and on 420 megahertz it should be 1.5 or more, and it was getting 1.76 volt. So that'll explain why the UHF received PLL was working okay, but the transmit side wasn't. So that could be ultimately what this TXLO1 could be. So TXLO1 might be a failure on this, or dropping out of adjustment, and thus it's interfering with the transmit for UHF. So there's various things, or it could be this power amplifier's got a fault. It might be we've actually got UHF drive, which we can check coming in here. But the main thing at the moment is I just want to have a look at this LO2 oscillator, which is going out of lock, this, to see if there's any voltages that are fray around this. If we're okay, then it's probably just a retune, you know, adjusting the capacitor and getting it to the right lock voltages and doing it on all of them, and then seeing where we get to, but it might just be maladjusted. So that's where we're at. Obviously the UHF VHF side's working to some extent, sort of half working. The 1.2 gigs bit is a module that goes in the end, the edge of the radio in the space, and that's not fitted on this one. We've also got the subband as well. There's a subband receiver, because we've technically got 2 receivers on this, so that's why there are some additional VCOs down here to allow 2 receivers as well, so it can manipulate the mixer frequency, so you can effectively be mixing 2 different frequencies together in order to get the receiver subband to pick up a secondary signal. And here again on the output of this receiver mixer, we've got all the filtering and discrimination, and obviously then it goes off through these bandpass filters and everything to then go into the what will be the FM discriminator and the SSB demodulators. So that's all there. But yeah, so we'll just have a look at the diagram now for the LO2, because I'm interested in what's going on around this oscillator here, which explains all the problems we're getting with the problems on HF right up to 50 megs. Okay, so we'll just measure this voltage on these pins here. We've got the breakout there for the socket, and it's 8 volt rail. Its supply rail is the 3rd pin down from the top, and then we've got the test point just below it, which is this TP505, which goes to that HCV2 line. But we're just interested in the supply rail at the moment, that 8 volts that should be there. If I remember rightly, when we measured the other VCOs, we didn't actually get 8 volts. It was actually a little bit lower, so that's also an issue that we might need to look at. But right, so we set up the voltmeter on the test set now, so we should be able to see what voltage is there. I'm just going to go onto that 3rd pin, just get my magnifier and just go onto that 3rd pin. There's a little lug that stands off that allows the screening cam to screw down, which is near that 3rd pin, so I've got to be really careful not to touch that, otherwise we'll get the 8-volt rail shorter to ground, and that would not be good. So we're just got to keep an eye on that and make sure that we don't do that, otherwise we're really up the creek without a paddle. Right, so we've got 6.96 volts there, so that's a little under 8 volts obviously. You know, I mean, it's 1.04 volts off adjustment. That if that's meant to be 8 volts, we're not actually getting 8, are we? We're just getting under 7. It's a volt off, which could make all the difference when it comes to tuning. And I've noticed this is a common thing on this VCO issue here, that the voltages that we're reading on these so-called 8-volt pins aren't actually 8 volt. But I think the voltages will lower anyway on the actual diagram, so I'll just find that and then we'll look at this VCO more closely on the diagram just to double check. But it seems that although the pinout is signified as 8 volts, in actual fact in the diagram it's less than 8 volts, the voltage that's pinpointed on the actual supply rail on the circuit diagram. So yeah, I do find that a bit odd. It can be a bit misleading, but we'll see that next. Okay, so this is the issue that we've got here. We've got the VCO that we've just been measuring there on the 8-volt rail, but as you'll see as we home in on that, you can see there, look, the level coming in is actually 6.9 volts. On there, sorry, that's it, 6.9 volts coming in, so it's not actually 8 volts, and this is a problem that we've got. You know, we've got an 8 volt indication there on the pins, and yet it's only 6.9 volts. I mean, obviously, you know, that's going to be a bit of an issue, you know. But if we just zoom back out again, so the voltage is correct then, what it should have. Now if we look here, we've got this ripple filter, which uses the multiplying effect of a capacitor there in the base junction to, if there's any variances on here, then this capacitor smooths those variances out via this essentially an RC network, and then the output remains stable, even though the input may vary. Obviously, as we're going to transmit and we're drawing current, or the supply line goes up and down, variances in the supply voltage, minute changes, can have a big effect on the output. So it uses this electrolytic cap in the base in conjunction with this resistor, and then obviously we've got a capacitor there on the output, which ultimately then smooths it further, and electrolytic there and electrolytic there. So yeah, this is obviously producing the 6.9 volts down to this rail. So that looks okay, to be honest with you. I can't see any problems there. So it looks like it's getting the voltages that it should need. Obviously the tune volts line we're going on to connects to this varactor there, the varicap diode, to tune the VCO, and we're obviously going on to that TP505, which is essentially this HCV2 line. So that's knocking it out of lock. So it could be that this trimmer capacitor, which is just C402 there, that is out of adjustment and obviously needs that sorting. We've got some switching going on here as well. When we enable this VCO, we've obviously got a 4-volt DC coming in to bias this transistor on, which ultimately pulls the ground path for this oscillator down to ground, so this then begins to oscillate. So that's obviously and something that we could check as well. But again, yeah, I'm looking here at possibly a retune on this, to be honest. What I think I might do now though, just before we start doing the alignments, we've not had this board out yet, so what I'm thinking of doing is removing this board altogether now and inspecting it underneath, just to make sure that there's nothing under there like water corrosion, because we've had the corrosive effects on the flexi strips. There's something could have got in here as well. So it's worth, we've had that board out, so let's take this one out and just have an inspection, visual inspection, give it a once over, and then from there we can go put it back in if it's okay, and then start doing the alignments throughout the whole radio. Right, this is the board removed now. Just for information, in the middle here is a reference oscillator for the radio. That's the one that works at that 14.4 megs or whatever it was, and that's the trimmer cap there right in the middle to net the frequency of the accuracy of the radio. Now I've given the radio, this board, a once over and had a real good look at it visually, both on top and underneath. The ribbon cable that plugs in there, I've had a look at that as well, and the connections are all nice on both sides of the print, so there's no problem there. But then I did find underneath, when I did a visual inspection, the solder joints on these two VCO connections here, these pins were quite bad. They were a bit crusty and it didn't look too good under the magnifier, so I've just sucked all the solder off and I'm just going to resolder those, and ultimately then that should resolve any issues around there. I did try removing the can on this particular VCO just so I could have a look underneath it, just to make sure that, you know, the solder connections under here were all you know, soldering onto the bottom of this PCB that's held captive inside this module. But it's very difficult to unsolder these, and I think it'd be a bit overkill to try and get that out, considering the problem that we've got isn't probably mechanical failure, it's probably something else. So just going to resolder these connections now, and then we should technically be good to go then. So just get my solder and my Metcal soldering iron, and then we're good to go. Now I use the standard solder sucker pace desoldering station to remove the solder from these. We just put some more sort of flux on there as well, just to give them a nice rework. It looked like as if somebody else had been into this as well and been messing about, because I did find one or two little solder slivers. Obviously the flux has not been removed off the PCB either, and that was still there all over the board, so it's not being washed off using alcohol cleaner, which we'll do when we've done this resolder job here, and restore it back to how it should be. But yeah, just one of those things, I'm afraid. But the nice thing about it is, of course, we remove the board for a visual inspection, and we'll resolder one or two components, give it a wash, and then put it all back together, so it's all nice and ready then for doing the alignment process. And we may also carry out the additional 27 picofarad capacitor fitment as per the Kenwood modification for this issue with the VCO out of lock, which solders onto one of the sockets that this board connects to on the other VCO assembly, and that in itself then will help stabilize the VCO's lock voltages, because that modification, that's what that was for. So yeah, I think we'll just try and resolder these again, these lugs, because I tried sucking the solder off these lugs earlier, but you just can't do it, you know. I think I might need the bigger iron on actually, or change this bit just so I can get this solder flowing, because I don't think it's going to like that. I might be able to start some of it going, but it's struggling, is this Metcal with this tip on. Oh, yeah, look, it's not doing too bad, just needs to warm up. Let's just see whether we can get it going. Just getting the temperature to go through. It's not really the best iron for the job, is this? I can feel it warming up from my fingers, but it's obviously not not the right thing, so I'll just flick the other iron on, I think, the ST45, and see whether we can perhaps get the rest of them soldered, although we're making progress, albeit slow. Should have changed the bit really to a more watty Metcal soldering bit. This is meant for small component repairs really, resoldering, rather than the big metal screening cans. And that should do that. But yeah, it's interesting, and when we find these issues, I'm just warming up the other so we can just go over them. So we flip the other soldering iron on. That should make short work of this. Once we've this will just like warm the board up really, this iron. That's the other thing with the Metcals, if we're ever changing the bits in the end, because the temperature gradient, the profile's all part of the tip, you know, you don't have an individual control like you do with the pace irons. With the pace irons at least you can adjust the temperature. You can adjust, obviously, remove the bits as well, but really it's not meant for the job like this, doing these sort of things. The ST45 from Pace makes short work of all this. The Metcal's good, but yeah, I find the Pace a little bit better to use. That can there is quite hot to touch, burning my finger. So, but yeah, physically on top the socket there looks okay. There's no dirt, corrosion, no crusted solder joints from what I can see. That all looks fine. Although I will look at it under the magnifier just to make sure there's no problems there. And then we'll just give this a clean. But I think the soldering iron's warmed up now, so might be able to make a better job of that screening can. Let's have a look. That's a bit better. There we go. Look. That's it. It was just that end one really that I was trying to get to a little bit more. Yeah, they're all okay now, happy with that. No problem there. Okay. Right, we'll give it a wash and put it back in. Back soon. Okay, so let's do some measurements now with this first VCO here is per the alignment instructions, which is HF ref VCO, set the frequency to 2 MHz, which I've done, TP501, we should be getting a reading of 1.5 volt, and so we'll just double check that, just make sure. Let's have a look, see if we can get on the test point. 1.5 volts bang on. So, but we can adjust it if we want to. I can put this inside the trimmer cap, and if I just adjust it off there momentarily and then put the probe back on, then as you can see there, it's very difficult to get on both at the same time. Another daft idea, whoever designed that. Right, so let's go to 1.5 volts. We can give a wiper a bit of a turn there, 1.5 volts. So that's where we're at. That's where we need to be when we get on it, 1.5 volts. So that's correct. Then it said next one is 12.990 megahertz. So enter frequency in, enter 12.990. That's 12.990 megahertz. We'll go back on that test point again. It's 1.5 volts. Now it's interesting there because it actually says that we should be getting 4.6 volts or less. And earlier when we did the measurement we were getting 4.82, and now we're only getting 1.5 volts, which I find strange. So there's already an anomaly there. Okay, well we'll progress on. We'll go to the main PLL now, which is TP502. Now TP502, if I can find that, I think it's hidden away somewhere. I'll have to try and find it. It's down one of the edges down here somewhere, so I'll just have a look at that. TP502, we should display the frequency of 30 kilohertz, so we'll put that on now. Change the frequency to 30 kilohertz and come back. Okay, so we've got 30 kilohertz now selected. So the measurements we're going to do now for HF1, HF2 and HF3 oscillators, which is HF1, HF2 and then HF3. So those three holes, 1, 2, 3 oscillators. So the first thing we're going to do now is go on to TP502 and we're going to check for 1.45 volts. If we don't have that, then we adjust the capacitor under this first hole there, which is TC408, to try and get 1.45 volts. So let's just put our probe onto the test point so I can see it. It's way up, it's 3.5 volts roughly. If we have a look there, 3.5 volts. That's not good. Definitely want it more than, well, less than that at 1.45 volts or whatever. So according to this, that capacitor down there is the adjustment point for it. So let's just try and get on and see if I can feel it. There we are. I'm on it now. I can feel it adjusting with me. I think it's not making a blind bit of difference. It's doing nothing. It's not as if I can remove my trimming tool and turn it round either and then it making a difference. It's doing nothing at all. Nothing. There's absolutely no effect whatsoever, that capacitor. So that's not good. There's something wrong there. It's still on frequency though at 30 kilohertz. The next one is, the next measurement is HF2, which is at 17 megahertz. Display 17 megahertz. So we'll enter the frequency in of 17 megahertz and 17.0. Enter. That's it. And then yep, 17 megahertz FM. And this time it talks about looking on that same test point again, and if we need to adjust it, it's the next hole on, which is a different capacitor, TC410. So we'll go on to the measurement now. 3 volts. It should be reading, according to this, 1.45 volts again, and we're getting way over that. Now if I try and adjust this capacitor there, I can get on it. Let's have a look. There we are. I'm adjusting it now and I can feel it turning and it's doing nothing at all. Is that so? That HF2 oscillator is not making any difference. So the next one is HF3 oscillator, which is the main PLL, obviously. Display a frequency of 27 megahertz. Okay, so sorry, 37 megahertz. So we'll just enter a frequency in on the top here, 37.0 megahertz, and we're getting 3.93 volts. and then this capacitor at the end here would adjust that, and it's making no difference whatsoever. I'm turning that trimmer cap, I can feel it, its resistance in the with the trimmer tool there, and it's making no difference at all. So that HF oscillator thing is not running at all. Okay, so we'll plough on with the next measurement then. So that gives us some information about HF 1, 2 and 3 oscillator not running. It's interesting how it's all contained in that one module. So whether there's something in there that's failed or something, I'm not sure. We're going to have a look at that. But let's just see what we get with the others, because there's something strange going on there. There's a VHF reference PLL, display frequency of 142 megahertz. So let's enter that in then. Enter 142 megahertz, 0.0, enter. And then this time we need to go on to TP512, which I believe TP512 is somewhere around here. TP512 is in between there, and that's the oscillator for the VHF. Now, according to this, we should be getting a voltage of 2 volts on that line. So let's just go on there then and see what we're getting. We're getting 1.9-ish something or other. So let's just go in, just adjust it. Now it might be that that's not adjusting either. Nothing's adjusting. I don't know what the hell's going on here. Unless it's a different trimmer tool, it might be this one. No, it is one of those. It's like a little grub screw type trimmer capacitor from what I can see. Let's just have a look. Yeah, it's a full size one like this. Ah, that's better. It's biting. There we go. Right. So let's have a look at this then. Right, so that's definitely adjusting now. So it needs to be, according to this, 2 volts bang on. So let's just adjust it. Get it to 2 volts bang on. There we are, look. 2 volts. So that's adjusting. So why won't the others adjust then for the HF? Are they definitely those little, yeah they are, the little, yeah, the tiny little, the difference between these capacitors in there and these are larger capacitors that need this to twiddle it, because obviously it's got a bigger end on it, whereas those are tiny little capacitor things and they need such a tiny small end on them. But as I'm turning them, you can actually feel them turning, and when I look through the hole there, when I turn one and then look at it, it's actually moved the flat part of it. So I know this has physically turned it, so that proves that. And then it said there on this one, move a frequency to 151.990 megahertz. So enter a frequency in of 152.990 megahertz, and let's see whether it'll allow me to enter that in. Sometimes it's not like the way this radio works is the VFO can get you to 152.990, but if you try entering it in, you know, entering it in yourself, it won't let you. So there we go, right, 152.990, and we'll go back onto that TP512 again, and there we go. So we should be getting a voltage, it says, of 4.6 volt or less, so on 151.990, 151.990. 990. Enter 151.990. Enter. That's it. So it's my mistake. I entered the wrong frequency in. So 151.990, and we should be getting 4.6 volt or less. It said check. And again, that seems off. 2.78 volts, but yeah, the VCO's in lock. So that's strange again. That's totally wrong. So it does seem strange, I must admit. And again, TP503, 142 megahertz for TP503, which I think TP503 is down here now. So it's this VCO, and we now need to change the frequency to 142.0 megahertz. 142.0 megahertz. So we're on that now. Let's double check. The voltage it says that we should be getting there on that TP503, it says we should be getting 1 volt at that, and if we don't get that, then adjust TC405. So we'll get 1 volt. We'll just get on this capacitor in a second. That's if we can see it. This might again be one of those little ones. Let's have a look, double check. Yes, it is. This is one of those tiny little capacitors now that needs this trimming tool on it. So we'll just go on there and try and adjust this then for 1 volt. See, again, that's not adjusting, and I'm giving that a full turn, and there's no adjustment there whatsoever. There's nothing there at that 0.76 volts. See there, if I touch the thing to the cam, now we're getting something. I wonder if these caps are duff. I wonder if there's something wrong with them, or maybe they need a resolder. Now it's adjusting, you see, because I put some physical strain on it. Now it's adjusting. I wonder if I need resoldering or something like that, 'cause I was turning that like that. Can you see there? The voltage is going up and down now, but until I actually put some physical strain on it at an angle, it then wasn't adjusting, and then it started to adjust when I put some strain on it. So that definitely wasn't adjusting that. So let's get it back up to 1 volt then, and then we can just gradually. And it did make a little click sound when I put some strain on it. So it does seem strange to me. I wonder if I should resolder them all internally. And it's funny, those other capacitors on the HF VC, all 3 of them didn't work. So it makes me wonder if there's something wrong with the capacitors themselves. Now it did say on the Kenwood bulletin that they can go intermittent, and I thought, anyway, that's near as damn it there. So that wasn't adjusting at all, that, and I could physically feel it, because it's hard to describe it. When it's in the slot and you turn in the screw in the capacitor, you can physically feel the resistance, and because it's like slightly loose, you can feel it bite again and then bite again this way as you're turning it, and you can feel the resistance to the capacitor plates as you're moving it. And that was not adjusting until I went like that at an angle and put some strain on it, as if that was a capacitor, and I put my trimmer in and like forced it like I was going to try and move it on the board, you know, and then suddenly it started adjusting. So I might go back now to these VCOs here and see whether they adjust. Those capacitors do the same with those, put a bit of strain. It could be that they've got they need resoldering maybe, or something like that. Maybe the dry joints on them all, and this is the production problem perhaps. I'm not sure. Let's just have a break a second, and then let me just review things, and then let's go back to this VCO and see whether I can force it to align. Right, I'm just going to go back to that earlier step now, which is the 30 kilohertz one, we were doing earlier on TP 502, which is down here now with this VCO, and it was TC408, which is under this hole here, this first hole. So let me just get back onto there. It's 3.5 volts. I can feel the capacitor when I put my trimmer tool in there. I'm on it now and I'm turning it. I can feel the screw in the capacitor turn, but it's making bugger all difference on the thing. Now if I jar it, now it's making a difference, look. Now I can adjust. I just jarred it there, the capacitor. Now there's a bit of adjustment. Now all of a sudden, look, there's adjustment there. These bloody capacitors are on the blink, and now I can adjust the voltage, look. I couldn't do that earlier, and all I've done is put a bit of vertical strain on it. If you imagine that's the capacitor there, I put imagine this is a trimmer tool, right, but it's just magnified 1,000 times. That's gone inside the capacitor to turn the screw so that the capacitor turns. And what I've done is I've just literally got the trimmer tool and then against the case above I've jarred it. I've gone like that. I pushed it, and then I've started to turn it, and as I've pushed it, it started to respond. So I think there's a production issue on these where all the trimmer capacitors are dodgy, and I think they're probably either not soldered to the board properly, or there's a physical failure within them. And now I've got that adjustment at 30 kilohertz, and I should have an adjustment there. It says here at 30 kilohertz, 1.45 volts. So let's adjust it then for 1.45 volts. So go back on now that we're getting it to adjust. It's at 2.6ish. So let's just get this to 1.45. So turn it the other way then, and it won't go down to 1.45. It'll go down to 2.6. 2.6 is the lowest voltage it'll go to there. Let's just see if there's two. Sometimes capacitors have two sweet spots on them, so let's just keep going. So that's 7 volts. Now there's no adjustment. Now it's starting to adjust again, and we're getting it down to 2.59 potentially, but not anything lower than that. Okay, so the next frequency that it said to check, which was 12.990 megahertz, and we should get 4.6 volts or less. So let's just enter the frequency in of 12.990. Enter. So that's 12.990, and we should be getting, according to this, 6.3 volts or less. So that's what we should be getting, and we're getting 4.34 volts. So as long as it's less than 6.3, that's all that matters. So that's okay, I'm happy with that. So there's something strange here. So now that I've proved with two oscillators, this oscillator and this one, by jarring the capacitor against the frame here, and the trimmer tool has brought the capacitor into alignment, I want to now lift these lids up and have a look at these capacitors, probably on this one and also this one. I want to check these capacitors. I want to see what the hell's going on under a microscope or something. Now I've got to look at these caps really carefully and perhaps solder them, resolder them all, because I think this is where this problem is, this out of lock issue. These capacitors are not adjusting, they're out of adjustment, and therefore the voltages are all wrong, so it's going out of lock. It's obvious, we just proved it, you know, we've just seen it with our own eyes. So there's something strange going on here. Back soon. Okay, we remove the can off a VCO now, and we can see that little trimmer cap up in the top there. So I'll just put the magnifier on, and we'll just go right in and then see what we can get to on that. But it does look to me, I don't know, it might not be soldered right, that, but I've just put some flux around it just to give it a solder. But that's the capacitor there that I jarred, and then it sort of it became right then. So if it resolder them all anyway, and then readjust the lock voltages. So give it a resolder. Right, I'll just get my Metcal on. And I just need my little magnifier. And let's just see what I can see here. Let's have a look here. Yeah. See if I can get on this cap and give it a bit of a flow there. Does seem a bit rough and ready, does that solder joint there, I must admit. And same on this side here. Just give it a nice warm up. See whether it adjusts now. Does seem a bit strange, does that? Let's see whether I can get some solder on there. A bit more solder. Let's see. Get it warmed up, because that's the RF ground side of it. Yeah, that seems okay. I'll give that another twirl. I think we'll do this on all of them. Take all the cans off and just give them a bit of a redo. See what happens. Okay, so I've got the cans off the rest of them now. Obviously these red capacitors down there need that size trimmer to get on them. I don't have a problem with those, although I probably will resolder them anyway, but it's these little ones. So I've just put some more, we've closed this one up now because we've done that one. I'm just gonna go in and just solder this one. It seems very dry around them. They don't seem to be, the solder seems quite difficult to warm up. It's like it's very old corroded solder. Let me just give it a little bit more. And then on the other side as well, warm it up, and that seems okay. So that's that one done. And then it's these three down there. So let's just have a quick look at that. Yeah, we've got, again, I might just have to try and bend the camera around that way a little bit so that it perhaps picks it up a bit better as I position it for soldering. And let's see what see whether I can get that to focus a bit better for you. So it's going in. Right. Let me see now, see if I can get in. It's always difficult with these cameras. Let's have a look here. Just resolder that side first, and then this side. Again, just a little bit more. Once it's warmed up enough, just a little tad more, just to give it a. It's not doing very well, that one. It's not doing well at all. It's as if the solder's very old and it's aged and gone all tough. Let me see if I can get on it. Yeah. I'm gonna have to focus on that more intently and come back. Yeah, just continuing on, just putting some more flux round. I just added a bit more flux to this end capacitor and it made a big difference. I'd be surprised at just what a difference it made. It just flowed beautifully when I did that. So just water-based flux, it dries off quite quick. That's why you got to be quick with it. So let me just see what I can get in and show it a bit in a bit better light. But let's see what I can get to it. So let's just have a look at this one. That's soldered okay on this side here, the live side, but the ground side again. This solder always on the ground side's always a bit. So I can move the capacitor there, just get it warmed up, and then get some. If I can, just keep the soldering iron on it, and then can barely bloody see it. Right, that's nice. That's nicely done. That's lovely. So that's a nice job. And then the last capacitor, of course, down here. Again, very difficult to get to. That's a live side soldered. Just slip with the iron then. Yeah. This feels like it could do with a bit more solder on it as well. Got some thinner solder somewhere. That's it, that warmed it up. There. Now then, that should do it, I think. And so we've soldered all those. I need to do this other board then as well, and a bit further up there I need to do that. So, but those caps are done now. And yeah, seems a bit strange. I must admit all this, but I just need to get this VCO done under there, those as well, because I think one of those was with a little grub screw thing on it, but then we've got these flexes and things that can burn quite easy, so I'll have to be careful round there. Back shortly. Okay, so we're just on this one now, and I think I'll move that flexi out of the way. I just need now to get on to it, and hopefully, so that's the live side of the cap done. Again, got this thing where we need to the ground side of the capacitor. It's like there's hardly any solder on it, or it's non-existent. I'm just sorry about this. Just got to get in quite close in order to solder it. If my head's in the way, but let me just double check that and make sure that looks okay. I don't want any big blobs on it. Just got to reflow it, and then it'll look alright then. That's okay. Then we just need the rest of them soldering, and just go around some of these transistors as well. Some of the solder on them not being too good. So that's a lot better now. I'm going to check the capacitor under here because it's on this side, on this one. I can't remember if it's one of those red ones or the one of those little grub screw ones. Let's just have a look. Just have to move a radio over here while I have a look. Oh no, it's okay. It's one of those big big capacitors. So like these red ones. These red ones are all soldered down properly, these red ones. So there's no problem with those. it's just these little grub screw type things. So I'll put it back together now and then we can start the alignment process again. Okay, so this is the HF LO1, 2 and 3, and then we had the little test point down there which was TP502 I think it was. That one was testing the 3 oscillators, and we weren't getting the lock voltage correct. Indeed, when we press the transmit button, when we were getting the lock voltage, then the radio went out of lock, and then it would intermittently come in and out of lock on receive, and then when you press a PTT again it would sometimes lock and then go unlock. So something happening with this VCO here, these 3 VCOs that are inside this one cam. And anyway, we'll have a look at the diagram now, because sort of where we're at now is the next stage. These radios have got problems with them where there's little solder blobs and little bobbles and things that when they've not been finished off properly with the production line, and it's been photographed and documented quite well that these radios suffer with dry joints on the connectors for the VCO underneath, which is hidden inside the little cans. So I might have to take the can off and then inspect the board underneath and that. But we have some voltages to measure as well, and we'll certainly be doing that. So if we just zoom in here just to show you what we're looking at currently, these are the 3 VCOs. So we've got here for this frequency range, which is written in red there. If I just zoom in a bit more, we might be able to see it a little bit better. So basically between about what 0 to 16 megs or 30 kilohertz to 16.9 megahertz, this switch comes on to enable this oscillator, which is HFLO1. And then when we get to another frequency which is 37 to 60 megahertz, then this switch comes on, and obviously this oscillator switched on, you see. And likewise here on this particular oscillator as well, again we have another switch here to switch it on and off at 17 to 36 megahertz, so that ultimately gets switched on as well. Now if we look carefully where TP502 is there, that test point where we're measuring, this lot line, or this tune volts line rather should I say, goes to all 3 VCOs. So it comes up here as well and goes to this VCO. So all 3 VCOs are supplied by this one tune line, and that's the tune line we were looking at earlier. Now when we looked at the 30 kilohertz oscillator and we inputted the frequency in for 30 kilohertz, the lot voltage on TP502 was correct. However, when we moved in higher frequencies, bringing in these 2 other oscillators in, the lot voltage wasn't going to 1.45 volts. I think it was 4.6, something like that, and we couldn't get any lower than that. So there seems to be something wrong with these 2 oscillators more than this one, because we could get a lock condition and a correct voltage as per the service manual in this particular oscillator here when we were operating at 30 kilohertz. But with that said, there was a measurement on this one oscillator as well, with a higher frequency of around about 14 megahertz I think it was, or 12 megahertz, and yet we were not getting the correct voltage at TP502, so it still suggests there could be a problem still with this oscillator too. So there's something strange going on here. So we could do as we've done with the other oscillators, we could look for this 6.9 volt supply, which is here present on this pin, and this obviously supplies the oscillators. It comes up here, goes via these inductors to supply that FET. Likewise it also goes up here to supply this FET and that FET there. So all 3 oscillators are provided power from the 6.9 volt line here, on that pin number 5 on this socket. So we could look at that as well, but there are other things on here as well. We've got an active low pass filter, which obviously interfaces between the output of the PLL and the tune volts line, which goes up to the varactor diodes on each oscillator. So obviously that there is dealt with by this amplifier as well, so the tune volts. As well as that, we've also got this up here, which is a ripple filter. So this is where the main power supply, if you like, rail on the top here. The 8-volt rail, if you like, is supplied via this inductor through this ripple filter, and then ultimately it comes right the way down here along, and then supplies a 6.9 volt line. So we can check for 6.9 volts on this socket, both in receive and transmit, because it could be getting disturbance on transmit as well. Then I think after that we really are getting into the darkest depths of having to strip it down and have a look at the PCB more carefully. Now on the surface here, when we look down here, all these components that are in the oscillator, I've resoldered most of them, like the FETs and some of the chip capacitors and other things that look quite dry. I've actually resoldered them, so there should actually be no dry joints there on those oscillating transistors and other things that I could spot. And I did find a ball, a solder ball, on one of the pins on the underside, because on this socket here down at the bottom, that goes through obviously to the underside of the board, this white socket, and I'd had this board out already and I'd resoldered. Not when I did the capacitors for each oscillator that we had problems with earlier, I turned the board over and I've resoldered the sockets underneath. I first of all sucked all the old solder off the pins using my solder sucker, and then I've reapplied new solder to all the sockets on the VCOs to rule out any dry joint issues or any problems. And I did find some tiny little baubles of solder that were between the pins on one or two connections, only one though, and that was held there by some of the leftover flux, which has now been all washed off the board, and it's very nice and clean underneath. So I don't suspect that problem, but apparently from what I've been reading up on some of other people that have experienced this issue, underneath these cans here, under the board, there are also signs of the solder mask that's bridged connections and touching things, and little baubles of solder as well that's been found, and it's under this can, which means removing this can, removing the board, and then inspecting underneath, because there are circuits underneath. So that's something that we might have to do, because we're pretty much clutching at the straws now. I am going to get the coax of truth on, I think, just to have a look on the spectrum analyzer, because when we trace the RF signal path, obviously the output of the signals from all three oscillators is combined on this line here. So we've got the output of this oscillator, the output of that oscillator, and ultimately the output of this oscillator as well, all coming down to this junction here before it goes to an amplifier, and then the output of the amplifier is fed then out on what would be pin number 6 on that little white socket, and then it goes off up here, and ultimately then it goes all the way up here, all the way along there, and it junctions then with another feed point, which ultimately is the frequency sample of the oscillator's output is fed back then to what is the PLL chip on F-in port there, which is on pin number 6 of that PLL IC. So where this junction is here, it gets amplified, the RF output, which then ultimately gets filtered. There's a pin diode switch, because we can see here between 1.8 to 40 megahertz, this switch is brought in to switch in different filters, to obviously get rid of any harmonic or spurious rubbish that might be on there. And we've got some pin diodes in there as well, which are these D439 and D440, which then switch the output filtering on and off, and ultimately then it comes out onto what is HF01. So I want to get the spectrum analyzer on CN502 with the coax of truth, and let's have a look on the spectrum analyzer and see what this oscillator is doing. But again, I could do with checking the supply to this IC, which is supplied via that inductor there. But the problem I've got is this IC is buried underneath, I believe, right on the underside of this module that I can't get to. So it's very difficult to inspect the supplies here, unless I can find this L515, is it? I think it is. It looks like it to me from here, 2 foot away from the diagram. So it could be something as simple as a bad supply to that, although I doubt it, because the supply for this IC, as we look here on the line coming up, that goes all the way along here. But this is what we need to research when we get it stripped down, and then it comes down here, this red line. Ultimately, we've also got some electrolytic there across the supply line. We've got another supply rail coming off here, which ultimately goes all the way down this bit and feeds in different points here, and then obviously the supply for this. So that one supply is supplying multiple PLL chips, and ultimately it comes down to this junction here, and it goes right the way down to our regulators that we're looking at earlier, which should be outputting, you know, according to this, 4.97 volts. So may worth be looking at this regulator as well to see if it's producing a lot of noise on its output. Although we're reading a DC voltage there on the DVM, it doesn't necessarily mean that it's not producing a lot of noise on its output if its regulator is going faulty. So that's something else, and that's the job of these capacitors, is to suppress any noise coming out. But we can check that on the oscilloscope. So there's a couple of places that we can look, and of course if a supply is varying wildly in high frequency, which the DVM can't read, it'll only read the DC content, not the AC, it could be disturbing, upsetting these PLLs. So, you know, there's a few little things we can look at, but before we start whipping the cans off and pulling the boards out and unplugging them from the main PCB just to inspect underneath all these modules. But there's definitely a case on these historically of contamination with solder contamination on the underside of the boards, shorting things out, blobs of solder being found short in between pins and on sockets, as well as on the actual PCB itself for the oscillator. So there's a few little things down here, but it means a major strip down of this module, which I want to avoid unless I have to. So we can start doing some measurements anyway and take it from there. Right, we've got the coaxial truth connected up now to the high sensitivity port on the Marconi, so we can look at the spectral output of the HF VCOs, the LO1, 2 and 3, and we've also got the purple cable here at the end, this one connected into the back of the antenna socket here on the radio for the HF power amplifier. So when we transmit on the radio, it goes into a 50 ohm load, even though it's not selected currently in the test set to measure that port. It will dump it into the internal load to protect the transmitter from getting damaged with high VSWR. So if we just have a look at a brief moment at what frequencies we should be expecting out of this this radio. This is a block diagram that we were looking at earlier, and if we look just here, we've obviously got HF LO1, we've got LO2, and then over here somewhere, if I'm not mistaken, we've got, I think it was LO3. So if we just zoom right in and have a greater look, so we've essentially got a TX path and an RX path. So the TX path is going out and the RX path is coming in. So for example, HF LO1 produces a signal which then in essence produces the first local oscillator frequency for the first mixer to produce an IF output for the receiver. But likewise on transmit it produces a frequency again to mix with a transmitter mixer, and again there's another signal coming this way which mixes together to produce the 1.8 to 54 megahertz signal. And again LO2 here, that obviously switches on and produces an output frequency to mix with it, and then ultimately we've got what would be LO3 here as well, which produces a frequency there for the receive mixer. So there's a few oscillators about, as you can see, and ultimately depending on whether on AM, FM, SSB, you know, digital modes, things like that for FFSK and what have you, and FSK signalling, RTTY, etc. It will depend on what mixers and oscillators are brought in. But basically the FM oscillator, there's an FM modulator there, which is just a VCO that's modulated with audio, then produces a signal which then mixes here with LO2. There's a reference VCO as well. So what we're interested in, obviously, is going on what is the output of these, which is what we've got that micro coax connected to, and ultimately what that will do, that will give us then the ability to see what's going off. Now we've got some further mixers down here. We've got RXL01, we've got TXL01, which again in those other cans. We've got quite a few little oscillators dotted about as well, so these all ultimately produce signals out which then go up here and further mix again and provide signal feeds onto these lines, so we get more signals fed this way as well, from below, from down here, as we can see. And so therefore these circuits down here feed signals up, and ultimately they get switched with these diodes onto the right lines to mix again. So when we look at this, we're looking at the output of these HF oscillators. We're not going to be getting the transmit fundamental, so if we've got it set to 10 megahertz, the radio for example, we're not going to get 10 megahertz from these oscillators. We're going to be getting other frequencies that mixes then with other signals to produce a 10 megs output on transmit. Likewise on receive will always be either a high side or a low side injection for the mixers, for the first mixer and the second mixer, and then obviously we've even got a third mixer here as well, so it's like a triple super heterodyne receiver, and again an oscillator that provides obviously you know, a BFO for that, a beat frequency oscillator as well. So there's quite a bit to it. So what we need to do now is get the spectrum analyzer enabled on the test set, and then analyze a signal that's coming off that connector down here, which I've got the coax of truth connected to, which is this 50 ohm coax. So let's have a look at that next. Okay, so we selected the high sensitivity port on the radio test set, and now we can have a look at that on the radio. Now I've set the radio to 10 megahertz frequency on FM, and I'm going to turn it on, and it's now switched on. So the test set's found a frequency, it's locked onto it, and we're currently getting a signal now coming out of those three oscillators, if you like, 79.08123 megahertz. Now it seems to have found a frequency. Now what I'm going to do, I'm going to transmit on the radio, but what I'm going to do is I'm going to switch to the high power port now on the radio test set. So now the radio test set will auto tune to what is the RF output on the back of the radio for the antenna socket, and so we should see 10 megahertz signal. So I'm transmitting now, and the test set's found a signal, it's locked on, and there we are, just over 10 megahertz at 4.775 watts. So at the moment the VCO's in lock. That might not last for long, but we can see there that the output signal is, the fundamental is at the correct frequency, roughly, give or take 960 hertz of frequency. But we can see the mixing process is occurring, and we're getting that reading there on the output. Now I'll unkey and obviously go back to what would be the output of the VCOs, and let's see what happens. Now it's picking something up again with no dashes on the display. If I move the tuning control on the radio and just vary it, and let's see, now it's gone out of lock, then it's back. Apparently it's back a little bit there, 79.014, and I'll move it up again just above 10 to 10 megahertz exactly, and it's back at 89.713, and then it's dithering about, wandering off all over, coming back. It's got the dashes on the display at the moment. Now the frequency's come back on the display, and now it's back. It's pulsing up and down. As you can see, it's trying to lock, and I'm not sure if it's racing up and down the band, so I'll just increase the resolution and widen the band up, and let's just see whether it starts dithering about. And I'll just move the frequency a bit. So there, it's gone down to there, and that's so that's out of lock at the moment, and as we can see the frequency's moved higher in frequency. There it is, it's jumped up there. Now it's coming back to where it needs to be, which is roughly near where that dotted line is in the middle of the screen. So at 10 megahertz display, so that's accurate. But if I try and move the frequency up, now I'm on 10.6 megs. It's gone out of lock, then it come back into lock. So as the frequency jumps from there upwards, when it gets to here, it's out of lock obviously, because it should be here. So it's trying to capture it as the PLL and pull that oscillator back to frequency. So I'll just whiz the tuning control up higher again, and as you can see, it's now out of lock. I've got the dashes on the display. It's still out of lock, and as you can see, it's trying to pull it. I don't know, it's wandered off, way off, and then now it's pulled it in, and we've got the frequency on the display, so it's in lock. So whiz the tuning control up again. Again, it's now out of lock. We've got the dashes on the display, and then the dashes have gone, and the frequency is being displayed. So it seems like even just small adjustments there, it's only a few hundred hertz frequency error that I've created there on the tuning control, and it's going wild. You know, it's right up here, which is where it shouldn't be. It needs to be where this dotted line is, nearly round about there. So now it's in lock again. So just increase the frequency again. It's behaving itself now. 12 megs. Now we're on 12 megs. It's out of lock. Now it's back in lock. So there's a bit of a delay. So that's 12 megahertz. But even if I just vary it by about 250 hertz, you know, it makes a big difference to the tuning. Going down in frequency, now it's out of lock again. It's reporting out of lock, which I find interesting. Now, what frequency is that then? It's roughly about 89 megahertz then, is when it's out of lock. Now currently it's in lock there, roughly around about 80 megs, 81 megs. So it does seem to me as if, yeah, move it a few hundred kilohertz again, thereabouts. We're on 11.7 something megahertz. It's gone out of lock. It's dancing about all over the frequency spectrum. It's going up and down everywhere. So you can see the oscillator is trying to be tuned. The PLL is racing up and down with its tuning voltage, trying to pull that oscillator in. And now we're in lock again. So let's just turn the frequency back down to roughly 10 megahertz again and see what happens. So this is nearly at 10 megahertz. It's in lock at the moment. Now what I'm going to do, I'm going to go into transmit while we're still monitoring the output of the oscillator. So I'm going to hit the transmit button, and I'll key up the transmitter, and that's there, that frequency is still there. Unkey the transmitter, key it up again. So that's remaining fairly constant at the moment, and we are getting a transmitted output signal still. So that looks to me like it's remaining in lock there, but if I press the transmit down and then turn the frequency dial at the same time, it's staying in lock. I'm just keeping my eye on it. Yeah, that's keeping its frequency more or less. Because on these radios you can actually turn the the dial for the frequency and change it while you're transmitting. A lot of radios don't allow you to do that, but you can on these. So I'm moving the frequency of the dial while I'm transmitting still, and now it's that's 8.9 megs roughly, 9.3. So it's working. So yeah, it's working, but it's obviously only going to work within certain limits. Like there, I've got it right down to round about 11 megahertz, 10 megahertz, 9, 8, and now it's gone because we've obviously got something's happened there. So that's like 9 megs, and then 8 megs there, 8.9 megs. There's no signal at all. So even if I increase the total, oh, is that something? What's that then? Let's have a look at the marker. What frequency is that then? So there is something there then, 83 megahertz. The dashes are on the display. Sorry, the dashes have gone and the frequency's still there. So let's go back to what is the transmit monitor for the RF output of a radio on the antenna socket and key up, and let's see if we now get the 8.96 megahertz, and it's off frequency. It should be 8.960 megahertz, and it's actually 7.34. so there's some fancy work going on here, because that's off frequency by a fair way. So that's strange. Right, so I'll go right the way down to about 5 megahertz, and that's 5 megahertz dead. We'll key up and let's see if the so all we're getting is a load of spurious output. The test set's not locking onto it, but if I adjust the marker, so this is the RF output from the radio and the antenna socket. So we've got something there obviously at around about 10 megs, which is like the harmonic of the 5 megs. We've got a 6 meg signal, and then down here then we suddenly got something around about 3.3 megahertz there, 3.38. so the actual RF signal I'm wanting at 5 megahertz just isn't there. I'll unkey the transmitter, now key it back up. There's no 5 megahertz, but yeah, it's showing in lock is the display, and it's allowing some kind of RF output there on transmit. I mean, we've got plus 35 dBm roughly coming out at 3.38 megahertz, but it isn't on frequency. So that shows you. Right, so we'll go back to the high sensitivity part now on the radio test set, and we'll just increase the right, just need to put the markers on. So that's 0 megahertz right in the middle of the screen, and that there is 80 megahertz roughly. As I adjust the frequency up in frequency, it may jump back into life. 10 megahertz roughly. Not getting anything there, and that's 20 megahertz per division. So there's something not right there, and the reference frequency is 7 megahertz there for that. So I'm not getting anything at all, even though currently it's showing as being in lock. So let's go back to the high power TX port, check to see if this radio is coming out with something. Key up the transmitter, and as I thought, there's no RF output. Oh, there it is. It's come back. There we are. 10.4 megahertz. Okay, so I'll go back to the high sensitivity port. Now we're back in business, I think, because it's picking something up, and we're now back at 79 megahertz, and we lost that earlier. So we've definitely got the output of this oscillator wandering off all over, so that's a roundup of that. But if I increase the frequency, that's 11.35, that's 12 megahertz, 13 megs, it's gone. At 13 megahertz it's gone, and it's right up the top end of the band, look, right up here at the moment. Now it's still in lock, so it might have just shifted frequency. It'll switch one oscillator off and switch the other on. So if I reduce the frequency, there we are, that's 12.8. So right up to 13 megahertz it basically stays at what would be, you know, 79 megahertz. But once you go and jump to what is 13 megahertz, then suddenly it jumps right the way up, which is probably what it should do at that frequency then, to 83 megahertz. So it can mix with another oscillator then to produce the right receive and transmit frequencies. And then if I keep going up in frequency right the way up, and now I'm at 15, 16 megahertz, now suddenly at 17 megahertz, that's 16.9 something, and now that's 17.02. So if I widen the bandwidth of the spectrum analyzer up even further, we can see then another signal, and that is down at 93 megahertz. So the oscillators appear to be there at the moment, but the out of lock line have come on now on the radio, and yet the oscillator frequency is there. So that suggests to me that in some regards this oscillator's got a fault, but yet there's something else which beyond this has also got a fault, because we've still got the dashes on the display to say it's out of lock, and that's at 93 megahertz there. Now earlier on we also had the oscillator on the lower frequencies at 10 megahertz going out of lock, so I'll reduce the frequency now. So now we're going down to 16 megahertz, so it's jumped to that other frequency there, and it'll stay there until we get down, I think, below 12.9 megahertz or 13 megahertz. So we're coming up to that now, so it's 14.5. Now it'd be 13 megahertz, and then I think it round about the 12 megahertz mark, 12.9 megs. Then it jumps again, do you see? So that's like the 13 megs, it jumps up, and then below 13 megs it goes down obviously, and then when we get to 10 megahertz as well. So that shows that that LO1, 2 and 3, insofar as that is concerned, are working. So as I increase the frequency now, we're at 10 megahertz, we can see that we've got an oscillator frequency of roughly around, you know, 79 megahertz. So I start to increase the tuning frequency now, and we'll see the oscillator jump shortly to the next oscillator, the LO2 frequency. So here we go, it'll come to us very shortly. There it is, it's jumped there, so that's roughly you know, 83 megahertz. Now keep increasing the frequency, we're currently at 13.5 megahertz, so we'll just keep increasing the frequency now till we observe the frequency jump again. So here we go, very shortly, because we're now at 16.48 megahertz, and very soon, there we go, wham, it goes straight up then at 70 megs. Now it's gone out of lock now. The out of lock but we can still see the oscillator is there. Now if I decrease the frequency now to there, 16.7 megahertz, it's in lock and it's on that frequency at 83.2 megahertz. If I increase the frequency up again to 17 megahertz, it's now out of lock. So the 17 megahertz out of lock condition is displayed. Bring it below 17 megahertz to 16.9 megahertz and it's in lock. So it seems to be that anything above now 17 megahertz is out of lock. But we're on 16.9 megahertz at the moment. If I go then to the high powered TX port, we've got auto tune on. If I keep up the transmitter, as we can see, it's doing 4.7 watts at 14.183 when it's actually 16.9 megahertz on the frequency readout on the radio, and we can see there we're getting lots of interfering signals. So you know, obviously if I expand that further and then we look at those signals, we can see there's a little bit of harmonic there, 20 megs, something at 14 megs, and then that's obviously the starting frequency of the spectrum analyzer. So we've only got the fundamental at 14 and a little harmonic there at 20.7 megahertz, but I haven't got the 16.9 megahertz that I'm wanting to achieve. So this at the moment looks to me like as if there's another oscillator somewhere else that's mixing, and that frequency of that oscillator isn't correct to mix with these three oscillators. So we've still got a problem with these three oscillators, mainly the LO3, I think the last one, because that's the one that generates the higher frequency and it went out of lock. So I find that quite interesting, and yeah, so I think there's something strange going on there. There is something strange. Now I've lost the signal altogether now. I'm looking at that port still, that high sensitivity port connected to what is, you know, the HF oscillator output, and I'm not getting anything now, unless I've got a mistake here with the spectrum analyzer, but I'm on 100 megahertz per division there and I'm not getting a thing. So let me just turn the frequency down. So the VCO, the radio thinks it's in lock still, but again I'm going right the way down here in frequency and I ain't getting anything. 10 megahertz. So I've got it set to 10 megahertz roughly. Now if I blip the transmit button and then unkey, I'm still not getting anything. So I don't understand what's going on there. It's 100 megahertz division. Oh right, I've got marker 1 set to 146 megahertz there obviously. So between there and right the way down to there, that radio signal should be in there somewhere, and it's gone altogether now. There's nothing on the display to indicate that it's out of lock, but there again we've got no RF signal at all, because this in the middle here is the start frequency of the spectrum analyzer, so there's nothing there at all. So that's gone now, that signal. If I switch the radio off and then switch it back on again, let's see whether something comes back. But I have nothing. So where's that gone then? So it's out of lock now completely. The dashes are on the display. So if I go up in frequency bands, then come back down again to the 10 megahertz, it's out of lock. So yeah, it confirms that this obviously is not reading any obviously signal, because the VCO has gone out of lock. I think it's like a delay before the synthesizer or the microprocessor puts the dashes on sometimes. But yeah, there's no RF output now at all from that LO1 203 oscillator. No matter what frequency I put in, no matter what frequency I dial in now on the radio and what band I select, there's no output at all now from that L1, L01, L02, L03. There's nothing coming out, so it's stopped dead now. So yeah, there's something strange going on here, something very, very strange. I'll just put my fingers on the oscillator and press down and give it a tap as well with the see whether it comes back. But it isn't, it's still out of lock. It only comes back into lock above 18 megahertz. Now that's a 14 megahertz. It's out of lock. So basically all the other bands are out of lock that's lay between those frequency ranges we were looking at earlier, and it's got the out of lock condition on there. So that's strange, isn't it? Very, very strange is that. So we've still got the dashes on the display and we've got no output frequency. So can I get on those pins on that thing there? Let's just have a look, see if I can get on those pins, because I've got a funny feeling now that we've forced it into that condition. We might be able to get some information now as to what's going on. So I'll just put that there. We'll just put that there to there. Let's just measure some voltages and see what's going off, because I've got a funny feeling. I've got my eye on the spectrum analyzer as well, so if it suddenly starts playing ball and it starts playing ball and comes on, then that's fine. Right, I've just got my magnifier nearby, so I think it was pin number, it was that pin there that the supply voltage should be on. There's nothing there on that. There we are, 7 volts. I think that was the supply. I think it was pin number 4. Yeah, there's nothing there. 7 volts pin. That was, I think, the 4th pin. Let's just have a look. So I can't. Yeah, 1, 2. Yeah, I think it was that pin there that had the supply on it. 7 volts. So the other lines got nothing on them. Got a 7 volt supply, but then there's nothing on the rest of them. Just a bit worried about getting onto that first one, because that's near that lug. Again, another stupid place to put it, but there's no other supply, no other voltages on there apart from the 7 volt rail, which is on the 3rd pin down from the top. So yeah, interesting. Let's have a look at that a bit closer, I think, on the diagram. Okay, so I've got the diagram back up, and it says here pin number 7 is ground, pin number 6 is the output frequency, pin number 5 is the 8 volt rail, or what would be 6.9 volts in our case. So if I just have a look at that, so I think that's 7, 6, 5. Again, the 6.9 volts there on pin number 5, pin number 40 volt, 0 volt, and then 4.6 volt should be on pin number 2. So pin number 2 is down there, pin number 2, and it should be, according to this, 4.6 volts. So there's 4.4 there, and that looks like it's the selection switch for the different oscillators for what will be for the HFLO1 VCO3, which is for frequency range 112 to what is 129, 112 to 129 megahertz, and that's obviously to enable that oscillator as well. So that's reading correctly the DC voltage there at 4.6 volts. So the voltages do look correct for the DC kind of level. Now the test point 502, which is down there at the bottom, test point 502 is right down here. If I can just stick my head down there, that's the tuning voltage, and it's already gone to 6.98 volts. So that tuning voltage is actually on this line here when we look at this in more detail. So it's just this line here, that's where I'm on now, that TP502. So this is 6.9 volts going to all these tune lines on these oscillators here. And yeah, we're getting the 6.9 volt supply, and we're not getting any DC volts or anything else as per the red indications here. We're on the output of all three oscillators, and there's no oscillation at all. There's nothing coming out, because this is where we're at now. We're on the output there with the spectrum analyzer, so there's nothing coming out. So it does make me wonder if the PLL's lost the plot, the PLL chip, and it's not able to pull it to frequency for whatever reason. Whether there's a problem with the chip or what, I don't know, because we've had these oscillators running. They do run, because we proved that earlier, and we changed the frequencies, and each oscillator got switched on in turn, albeit I think the last oscillator didn't run, which I think is this one. We certainly got, I think it was this one going, which was, if we zoom in a bit further, we got this one, the 75 megs to 86 going. We definitely had that one going, didn't we? And I think we had this one going as well, which was the 92 to 106 megahertz. But we didn't have a third one, which was this 112 to 129, I don't think. Don't recall ever getting this one running. When we increase the frequency to bring this oscillator in, then it just didn't appear, the signal from this one. So yeah, it does seem a bit strange to me. I'm just going to put my thinking cap on and see where we go next with this. Yeah, so just a quick one. Obviously we've got oscillator 1 control, oscillator 2 and oscillator 3, and obviously these lines go up to the different transistors which switch the oscillator on, like we've got there, and so they're actively working, they are, and I should be able to see that now on the on this, because if I were to go on to pin number 2, we saw 4.6 volts there, but if I go on to pin number 3, and that's always more difficult than you think, and ultimately then pin number 4, we should technically be able to see a voltage as I increase the frequency on the radio. So if I just go to that oscillator, so 76543, so that's pin number 3. We've got no voltage, but as I increase the banding on the radio, we should see that. So I'm just increasing that frequency now. There we are, look. So that's where it would switch in oscillator number 2, and then if I advance the pin on to the next pin on, which is there, that's obviously when we should see the next frequency oscillator brought in. So I'll just decrease the frequency now, because obviously it was for the lower echelons of the frequency band, and we should see very shortly that gets switched on. So that's like the oscillator selection switch, if you like. So I'm just reducing the tuning range now on on there, and we should see that. There we are, look. So that's the next oscillator. So they are being switched on by the logic, you know, on these lines. That's definitely occurring. So each one of these enable lines is getting switched for the different bands. But yeah, on the spectrum analyzer, I've been keeping my eye on the spectrum analyzer as each one of these select lines comes on to turn on each oscillator in turn. There is no output at all on the on any of the three oscillators. So it's as if I would have thought they'd be free running even when the tune volts line here on that test point was at any voltage, high or low. I would have thought there'd be something coming out of these oscillators no matter what. It wouldn't be the case that there'd be zero RF output coming out, and that's what we're getting. We're not getting anything out at all. When we look on the spectrum analyzer, as we can see, there's nothing coming out. This signal here is obviously the start of the spectrum analyzer, but that entire radio spectrum there, and I can increase it, you know. So with a mark I can go right up there, in that case right up to, you know, even higher than that obviously. So this is like, you know, huge part of the RF spectrum. That's right into the UHF spectrum now at 500 megahertz, right the way down to what would be, you know, 0 megahertz. So this portion of the screen, if you like, is 500 megahertz bandwidth, and as you can see there's sod all RF output coming out of those three oscillators. So even if a tuning voltage, which it is at 6.9 volts on that TP502, I would have expected some loads of RF spurious coming out. You know, it lit up, it looked like an hedgehog. You know, it had loads of spikes all over. But there's nothing coming out of that oscillator at all, no matter what frequency band we're looking at. And I wouldn't have thought that would be the case. Now, you know, these tuning capacitors that are in the oscillator, which are these here, these variable capacitors, that's one and that's one, would at least allow the oscillator some free running action, and that's not happening. We're not getting any output. So is it the case that the fault is the amplifier here? What I could do with perhaps now trying to measure an RF signal here at this junction, because if these oscillators are free running, which they are at the moment probably, or should be, there'll definitely be a signal present here. And ultimately we're measuring after this amplifier, because ultimately the amplifier's output comes out, goes down, it goes up across here, all the way then again to another amplifier, so that could be faulty, all the way down, and we've got the coax of truth connected here to the spectrum analyzer. And as you can see, we're getting sod all RF signal at 500 megahertz bandwidth, nothing there, zero. So either these amplifiers have stopped running, maybe the supplies have gone to them perhaps, I don't know. We've got a pi attenuator there obviously, but we have got absolutely, that's something different anyway there, look. But that there, this amplifier might not be running. So if I could find where this capacitor is, now it could be under one of those other cans, because there are other cans here with some amplifiers on them. I've got a funny feeling though it's probably all contained on that PCB, but I'm not 100% certain. I think the PLL chips are actually under these silver cans, which are soldered down, which is not very helpful. But if I could find that capacitor that's on this diagram, and we might be able to stand some luck of getting on this junction somewhere and seeing what the hell's going on. If I can get there with the coax of truth. The problem is, of course, even if the oscillators are running, when we load it with the 50 ohm port, or even with the capacitor in series, it'll stop these oscillators dead. That's why we've got the amplifier. But what I can do is I can just drop a little loop in into the cavity like a little pickup loop, I can just drop it in, a bit of coax with the loose end inner conductor bent in a little loop, bent back, and just touch round inside to see whether we can pick something up, and that'll give us an indication as to whether the oscillator is free running or not, because that amplifier should be running. Now I wouldn't have thought in an out of lock condition, although you never know, that those amplifiers will be switched off, and I don't think they are, because obviously they're picking up the supply rail here, look, from L502, the same supply that supplies the FETs. So with there being no output at all on the spectrum analyzer, as we can see there, I'm suspecting that there's some weirdness going on around those amplifiers potentially. So it could be this capacitor's got a dry joint on one end, for example, and it's just lifted up a little bit, but I don't know. I'm going to have to try and find that capacitor on the board there. That C808, is it? 1000 puff capacitor. Now if I can get on that, once this side of it probably, or either side, or near it with a sniffer, just sniff to see if there's a signal around it, and that'll tell me a lot. So let's try and get something hooked up for that. Okay, so we've got the coax of truth connected now. This is a different coax of truth. This is a one that I've just made here, just a little loop on the end connecting to the spectrum analyzer, and we just got a little loop so we can put it in and probe around. But what we've done to aid ourselves is we have here the spectrum analyzer's reference level, which are these here, these two up and down. We've made the sensitivity of the spectrum analyzer able to pick out signals around about down to noise floor of neg 100 dBm. Before the RF level, reference level, was set quite high, so you had to have quite a high amplitude of RF signal for it to appear on the scope. But now what we've done, we've lowered that right to the noise floor nearly, and marker 1 is currently around neg 82 dBm. So we're sort of into the microvolt territory, really. So what I'm going to do is I'm just going to drop my I've found on the diagram where that amplifier transistor is, and it is up here, and that C808 is there, look. So that's the amplifier transistor, the first amplifier, and that's the decoupling cap there, that's C808. This diagram is inverse to what it is on the board, so in other words, this inductor's actually on this side and these two are on the other side, so it's like back to front if you like, but I can see where I need to be. So what we're going to do now, we're just going to drop that coaxial cable onto what is the into the cavity, and we're going to just hold it near, and we are, look, we're getting loads and loads of signals now. So let's have a look and see what frequencies these are at then. So this is a sort of free running part of the oscillator, and if I just use the marker and let's just have a look. So we've got a signal there, and the rough frequency of that's just alter. That's what, 430 megahertz there. So it's all over the place. And multiple harmonics, 286, and then the biggest one, the fundamental, is 146 megahertz. So we've got something there. Now it'd be interesting to see as I adjust the frequency on the radio and it switches in different oscillators to see what that does. There we are, look, so that's the next oscillator that's been switched in, and then if I just go back again, that's the other oscillator. So that's one oscillator, and that's actually in lock, that, and it's funny, by touching the circuit board with the actual probe, just laying it on there, down there, as you can see, just doing that has caused the VCO to go into lock, and now we're getting a frequency readout on the display. So there's definitely something strange going on around there. So let's just keep going up in frequency then. So let's keep going. Now it's gone out of lock there. Just keep going up. Keep going up in frequency. It's still out of lock. And let's see what when it fetches in the other oscillator, what frequency is that doing. So there is that free running there, and but the amplifiers are not amplifying it. So there we are. Look, so that's the one oscillator that we had. The next oscillator gets brought in there, and again it's still out of, well, it's in lock actually now. It's just come back up. So go down again, and then now it's out of lock. So that to me looks like as if there's something very strange going on. Now what I will do, I will connect up the coax of truth that comes from the output connector now up to the spectrum analyzer to see whether there is actually some output there. But with them being amplifiers, whatever output the oscillator was running at, even when it was free running, should have been quite high level. So I would expect something to be there now, but it depends on what's coming out. Let's just have a look, because this is after two amplifiers, and let's just see what we get coming out. So that's what we've got coming out. So if I just adjust the reference level, so we do have something there that's coming out which we didn't have before. So it does seem very strange, does this? Now I'm putting my finger on the board inside to see if I can manipulate it, the frequency of oscillation. I'm physically touching the board with my finger to see what's going on, but we do have something there. What frequency is that then? That's about 30 odd megs. But I've no transmitter, I've no VCO lock on receive or anything like that. So yeah, it's there, but it's not being read by the PLL chip or referenced properly. So it looks like as if there's some signal there now which there wasn't before. So something's changed since I last touched that circuit board with the pickup probe. Physically touching the components on the circuit board has brought back the signal, and me putting my finger on the oscillator itself, the transistors, the oscillator FET, should massively affect its oscillation frequency, and it isn't. It's not doing that. I dare say by adjusting those trimmer caps we might be able to get it to slide about onto different frequencies, and I might try that next. But it is producing an output there, but it's not the right level it should be really, but also earlier on we didn't get that signal, so there's definitely something weird going on. We were not getting that signal at all in the output socket, and now we are. We're getting something, even though the VCO is out of lock. So if I just widen that a bit more to there, then look at the frequency there. And yet we're still no frequency on the display. So there's something really fishy going on here around this PLL IC, I think, which is going to be the issue. I think we might have to take this off, because looking at the PCB for that module there, which is what we've been looking at, if we go up here and have a look, this is the oscillator itself as it stands in the board. We've got two chips. We've got this IC which is on the underside of this module, and we've also another IC in red there which is actually soldered to the PCB that the module itself solders to. So the main motherboard has got an IC on it, which is highlighted in red. That's what these components are that are in red, you know, like these there as well. However, this IC is on the underside of that PCB. So basically, the PLL IC is on the underside of that PCB, facing, if you like, the face of it will be facing downwards, and the leads will be soldered underneath this removable board. So there's something strange going on, very, very strange indeed, with this module. So, interesting. Okay, so we remove this VCO module now from the PCB, and we've got what appears to be on this. When we look really far into it, you might see there's some pins coming through the board just under that white socket. I'm not sure if it's seeable from that direction, but you might be able to see right down there. The pins themselves are not soldered on the top of the board. They are underneath there, but obviously on the top most of them are not soldered. You can actually see the little islands. They're just almost like a hole just going straight through the board, and then the pin just emerges without any solder on there. Before the track then goes off, you know, at an angle to where it needs to get to. So it makes me wonder whether they do need soldering, but it's got a plated through hole on these, like that little through hole there, right at the top. They're all plated through, so it shouldn't really matter, to be honest with you. But I have found underneath quite a few solder globules and things where they've gone over the mask on the PCB. Like, for example, here there's a bit of a solder sliver when I can point to it. It's just there, look, just there, solder sliver there. There's a couple of balls as well, like there's a ball just there. Although it's on the earth thing, it's still a ball, you know, and it's part of the resin. There don't look to be any contamination between the pins with balls and things. There's some more little bits and bobs, but as you look round you'll find these little balls that are sticking to things and creating a bit of havoc. So I don't know, that could be an issue there, that little solder sliver that's stuck on that track, and I can't shift it. There we are, look, we've got it off now. But yeah, I think it's definitely, you know, these little bits of solder that have definitely contaminated that bit, and that's obviously from a fresh. I might try and remove a solder on these with the solder sucker and then renew those solder connections, and we'll get all the flux residue off, resolder what we can, because we've definitely had signs of contamination there with solder blobs and that. But down there, I just want to try and zoom in on that. If I can get this magnifier to work on this, and I can try and get the PCB up to the magnifier, you might be able to just see down there, if I can get this thing to focus, there's some little islands. It's so difficult to see with this magnifier, but there's those little islands there that the pins go through. It just seems that there's no solder on them. I can't get it to magnify any better, I'm afraid. It's about there, optimal. I'm just going to see if I can get the light to be better. Perhaps if I move the light this way, and then I can perhaps hold it up. It may be I can just hold it up to this. Yeah. Yeah, you can see better with this, can't you, now that the pins are going through and there's no solder on those holes. Can you see at the very top? There's just no solder there. So with that, I would say that it's unusual that those wouldn't be soldered through, but it might not need it, you know, because as I said, that they are plated, those holes, and there's obviously no I just can't get it to focus now. Always awkward, these cameras, pain in the backside. You just back the focus off, let it resync, and then let's go back in. Yeah. Now to just see now, look, like those pins on the left. But basically those islands, if you like, there's nothing there. There's no solder on them whatsoever on the tops, and that could be an issue. Just go straight through, but soldered underneath, soldered there, and then obviously we've seen all that contamination, little solder blobs and things like that. So is that the cause? Maybe. Possible. I don't know, but it's worth a try. Resoldering things, sucking the solder off these and then reapplying solder so that it goes through to the other side and gets onto these lands at the top there, and that way then let's see if I can get it to focus in a bit better on it. Let's have a look. Trying to see best I can. You can see there, look, there's just no solder on them at all. Yeah. So worth a go. As for the PCB, the main PCB itself, where the module goes, that goes here, and again I'm looking for contamination, dry joints, solder globules, things like that, but there's nothing that stands out. I've had a look already with the eyeglass. That's the PLL chip, that IC414, but all the components look okay. I can't see any contamination on this side of the board really, but I'll give it a clean and a wash. Might try and resolder things, just run the soldering iron round with a bit of flux, then wash it all off. The islands there that are for the solder joints look okay. There's nothing that I can see shorting anything or any globules, but you can see there's a lot of flux residue left on the components as well, which could do with washing off, because as it gets older some flux residues start to conduct, so that would definitely be worth washing off. Maybe resolder the pins on that IC as well. So there's a few things that we can do there, but certainly not as bad as the VCO module itself, which had the contamination as we saw on that track. It was well and truly stuck on, wasn't it? It took some prying off, and then there's other little solder globules like that there that I might be able to point out, and ultimately these could be sort of floating around, these things, and again that's well and truly stuck, you know, is that. So there's quite a bit to work on, but sort of clutching at the straws really, but yeah, best start somewhere. Right, we've done some resoldering. As we can see now, the solder's flowed through onto the top where the island is, so might be able to get a better look under the magnifier shortly. I think it's better viewed from that angle than before. So let's just put the magnifier on again, and let's see whether we can get a decent shot this time. Try a different magnifying glass. So let's just hold this up and see whether we can. So now we can see there, look, the solder has come through to the top on those pins. So that's the case on with all of them there. Not sure if you can see from the other side. Let's just have a look at that. See there, look. And before, the one at the end there on the far left I'm not too worried about, because that's actually the earth, the RF ground if you like. But with the rest of them, they carry signals and voltages. So as you can see, they're all soldered now at the top. So I'm happy with that, very happy indeed. We've just got to remove some of this contamination. You can see there's bits of stuff stuck all over the place in that flux. Now that we can look, more globules there, look, and other bits. So we'll just wash it and then come back and see where we are with it. Okay, so this is the finished article now, much cleaner and nicer, and all the pins are all nicely soldered and cleaned, and there's no sort of solder slivers or any contamination now anywhere on the board. It's all been washed and ready to go back in, and so that's a good result as far as I'm concerned. Okay, so this is the finished article here with the components underneath on the circuit board here that I've been resoldering. I've resoldered this IC as well, and all the chip capacitors and resistors and transistors. I've resoldered a lot, so hopefully, and now the board's been cleaned as well, so hopefully it will be good enough now for the reinsertion of the VCO module back in, now that that's all done. So fingers crossed. Let's see what happens now. Okay, so we've put the board back in the radio, and we've just been doing a few little tests off air with it just to see what happens. It's still not working, I'm afraid, even though we've reseated the VCO module down there that had VCO 1, 2 and 3, and it's still not working. So we've got to look at this a bit closer, but we've got some more ideas anyway, which I'm going to go through now with you in this diagram. But we're basically on 9.2 megahertz there, 9.280 megahertz. Now I'm not getting the right frequency on transmit. If I go to transmit now, and then we look at the transmit monitor, as you can see it's reading 6.344 megahertz when it should be on 9.280 megahertz on transmit. Likewise, when we also go to the receive, and I type in RF gen frequency 9.280 megahertz, we're not getting any receive signal indication at all on the screen there. So if we just keep an eye on the signal meter area there, if I turn the RF gen off, that's on rather, there, we're not getting any signal. If I turn it off, which it's off now, there's no indication, so it's not actually receiving on that frequency, which goes in line with the fact that, of course, the transmitter frequency, if I key up again on what should be 9.280, if you notice as well, the TX power is quite low. It should be 5 watts, it's only 1.6 watts, which indicates perhaps it's spreading a bit on transmit, or it's not doing the right thing. So let's just have a look at that on the spectrum analyzer and see what it's doing. It doesn't look too bad. I'm just going to open it up, and as you can see there, there's a few other signals occurring on other frequencies there, so that probably explains the low power. It's sort of out of spec. So I've got a few hypotheses now of what may be going on, and it's something called a reference VCO, HF reference VCO. So I'll explain what that does. But basically, under this module here, this is the HF reference VCO, and what that does, it provides a reference signal that lies between 31.130 megahertz and 32.834 megahertz, I think it is. And that mixes with a signal from the 3 different VCOs that are on this module here. The 2 mix together, and then there's another mixer after these, which is from the other reference oscillator, the other VCOs rather, that mix a second time, and we'll see that on the block diagram in a moment that we'll look at. So depending on whether we're working on HF, VHF, UHF, different oscillators are mixed with other oscillators to produce an IF frequency, which is used for both the receive local injection for the receiver front end as well as a transmit signal. And what we're getting here, the characteristics are, if you remember earlier, no matter which VCO we went to, because as we move a frequency in the HF band of the radio up and down to different frequencies, these VCOs are switched on and off. So one VCO is responsible for one part of the radio spectrum in the HF range, the other VCO is responsible for another, and so on and so forth. And we saw there were 3 select lines that get switched as we go through the different frequencies to switch the different oscillators on. Now, in hindsight, if there was a problem with an oscillator, one oscillator, it's likely to be, the other 2 would work, but we're not getting that. All 3 oscillators are not working at times, and it's going out of lock, showing the dashes on the display, which indicates all 3 oscillators are out of lock, VCOs. Now, strangely on this, what it does, it uses not just the reference oscillator frequency that's from the reference oscillator here as a reference for the PLL, the phase lock loop circuitry. It also uses what's called a HF ref VCO, and the job of this is to provide a frequency between 31 and 32 megahertz to the PLL ICs at certain parts of the HF band. So it uses effectively 2 reference frequencies. It uses a 15.4 megs, the 15.4 megs that's doubled up, and it also uses this reference VCO as well to provide a reference signal separately to the phase lock loop which runs these VCOs. Now, as we've just seen there, the transmitter frequency, although it should have been on 9.280 megahertz, when we look at it, it's actually off frequency. So we're keying up the transmitter now, and we're actually going to be getting a frequency that's about 6 megahertz or thereabouts. So obviously when we look at that, it's on 6.31 something megahertz, 3233. It's not stable, it's moving continuously, which means to me, looks to me, that that reference VCO may be off frequency. So if we look at that on the schematic diagram now on here, and this is the offending article that we need to look at that's under this CAN, or at least measure its frequency. So what we've got here, we've got the reference VCO here. Now if we look at the architecture carefully, we've obviously got the oscillator circuitry with the trimmer and the varactor diodes there, the varicaps. Then we've got a buffer amplifier, and it comes out, and as we can see here, it breaks into 2 paths. One path goes into this PLL IC here, this phase lock loop, and then the other path carries on, obviously, down here and goes into this PLL IC as well. So there are 2 PLLs, effectively ICs, that reference VCO provides. Now if we further analyse this PLL IC here, and we look at that, its input frequency is an OS1 from the HF ref VCO, and then this is a frequency that comes from the VCO itself. So basically we've got here the RF going this way, we've got it coming down here, along there, into there, buffer amplifier, and this is where, if you remember earlier, we've got the HFLO1 VCO, HFLO VCO1, VCO2. These are those three holes that we're referring to earlier. So that's hole number 1, if you like, on the VCO CAN we were looking at, which is down here. That's like hole number 1. And then, if you like, there, the next VCO in the circuit, which is below it, which is VCO3, and then there's also a VCO 2 somewhere, if we can find that. Where the hell that is? Here we are, look. This is VCO number 2. So we've got VCO, sort of 1, 2, 3 VCOs here. All these 3 VCOs are referenced to this PLL IC here, which is provided with its reference frequency in the OSC1 input pin, pin number 8, all the way along from our little friend, the UHF reference VCO. So if this VCO is off frequency and it's wandering off, unstable, then all these VCOs are all going to be off frequency, these 3 VCOs here in this part, because they're tied to the PLL here, which gets its reference from that HF ref VCO. Likewise, if we look at this one, this PLL IC, that also gets its frequency as well, I believe, or am I wrong? Let's just have a look. That goes down there. No, that's fine. Yeah, oh, that's fine. So this HF reference VCO just supplies a... Oh, it doesn't. Yes, it supplies both PLL ICs, because it just junctions there, look. That one goes, that path there on the left goes to the PLL IC we've just been looking at for VCO 1, 2 and 3 on the HF VCO. The right hand path down here goes into this PLL IC, which is for a second lot of VCOs. So if we look at these, what would be the again, there's something else here, an OSC from this, what is this, DES or DDS malarkey, and then we've also got that looks like it's some kind of an oscillator as well for pulling this chip, because it's coming in on the there, the OSC1 input, and then of course we've got the reference oscillator, the HF ref VCO, actually coming in as the F in, as if it's like a VCO itself. So that's compared with this to then produce an output up here to control the reference VCO. So again, all these 3, this reference VCO, this DDS chip, which we'll have to read up on and find out what that does, and this PLL, all keep this in abeyance, all in lock. So I think there's something going on here. So one of the plan of attack that I'd like to explore on this is to go on to lift the lid off this can, off this VCO, and go straight on to what will be, I think it's pin number 7 on that connector, just there with the coax of truth connected to the spectrum analyzer. Put the radio on a stable frequency and then just see what's going off here. Is this racing up and down? Is it off frequency? Should it, you know, is it not outputting a frequency in this range? So we'll need to verify that. If so, is it a tuning issue with this? Is it something else? So if we remember earlier as well, when we were looking at these 3 VCOs here, which is obviously VCO 1, VCO 3 and VCO 2, the lock line for this PLL circuit was actually, when it was going out of lock no matter what, because it's got one PLL lock line, which is this TP502 there, that went straight up to 6.9 volts or thereabouts and just stayed there no matter which one of these 3 oscillators was switched in, because we've got the oscillator select there, which is obviously, as you can see there, there's HS W1, 2 and 3. These actively change the state depending on which oscillator we want to be brought in. So the microprocessor switches the VCOs on and off as it needs them. So because no matter which voltage controlled oscillator was switched in, this TP502 remained at 6.9 volts, means the whole reference situation must have been out of lock. Because if you've got a fault with one VCO, it wouldn't be on all 3. You'd only have a problem on one, you know, a component failure on one. It would be unlikely, very unlikely, unless it's bad luck, that you get a failure all at the same time on all 3 VCOs. So I'm now hypothesizing that the problem that we've got here is the phase lock loop circuitry, this one that controls the HF reference VCO, because this ultimately provides a reference oscillator frequency for all the other VCOs. in the HF frequency range, and it uses HF VCOs to mix with the other VHF VCOs to produce VHF and UHF frequencies. So it's really quite a critical thing. So we'll have to look at this more carefully. There's a buffer amplifier going in there, microprocessor clock, M clock, and that's going up to there. So that gets a 15.4 megahertz signal. I think it's 15.4, isn't it? Let's just refresh ourselves. And it is, if I remember rightly, I'm sure it was a 15.4 megahertz signal, or thereabouts, something like that. I've got another one, LO2 VCO, coming out. There's that many VCOs on this, it's unbelievable. That comes that way. So there's the LO2 VCO as well. That provides a signal this way, and that then goes through this circuitry, gets buffered up, passed across, double a circuit. So again, looking at this, yeah, that's an input into that. Yeah, that's the reference oscillator frequency coming into that PLL. It actually comes from below down here, that's it. So your 15.6 megahertz is doubled. It's buffered and passed out across here. It gets doubled up, obviously, for double 15.6 megs, 32 megs or thereabouts. Comes down here, arrives at this point, goes into this, but gets buffered into this. So it actually does get like a 32 meg reference signal coming in there on the M clock line, and then ultimately then the output of this is fed through this ripple filter, obviously, and that is then passed off to this OSC1 here. Now we do have, obviously, as part of this DDS, I'm going to have to read up what this DDS does, but it's a slightly different chip to a PLL IC. We'll look at the pin out. So that to me would indicate that this is some kind of special thing, whether it's a doubler again or whether it does something else with the frequencies, I'm not sure. But obviously we've got the 30 odd megs reference oscillator frequency coming in there. On the I out we've got some kind of a buffer amplifier before it then gets fed back into the OSC-in, what is the reference oscillator input frequency for this PLL IC, which ultimately has its frequency control from this HF reference VCO. So I'm interested in seeing what frequencies on here. I want to know what frequencies are on there, and then we can trace back from there to see whether this reference oscillator frequency coming in might be changing. It might be low level, it might be something wrong here, it could be there's a supply issue around this IC. We've got a supply rail with inductor capacitor supplying power to it on VDD. There's another supply rail going in there on AVDD. There's a few little amplifiers and some bits and bobs around here that might pack in. So we just need to check all this area. The problem is these ICs are buried underneath. They're actually underneath the, as we were looking at earlier, when you remove the VCO modules, they're actually on the circuit board under the module. So it makes it incredibly difficult to try and do any measurements for the ICs unless you remove the VCO out the circuit altogether, in which case once you remove the VCO you can't do any measurements because you need the VCO in order to do the measurements. So, you know, it's chicken and egg syndrome, but you can see where I'm coming from with this now. I'm just trying to narrow down. So let's get the lid off this VCO, this HF ref VCO. Let's get on to this pin number 7 and let's see what frequency is coming out. Be interesting to see. Right, so I just dropped the coaxial truth in loosely coupled into the middle of that coil there, just so that it can pick up a bit of RF. We're just going to tune that trimmer cap now on that HF ref VCO. Now I've got the spectrum analyzer hooked up, and bearing in mind the frequency should be, as it says, between 31.130 and 32.834. We're actually getting the frequency way off. I've got the marker 1 set up there onto frequency, and it's 38 megs, as you can see there, 38.080. So I'm just going to put my trimmer tool in the trimmer capacitor now. The radio's out of lock still, the dashes are showing on the display, and I'm just tuning that trimmer cap, and so that's like half a turn there. The lowest frequencies it'll go is around about there, and then as we continue turning the capacitor it starts to climb in frequency, and then it literally gets to a maximum, which is there, 38 megs, but then it won't come down. So there's something wrong. It's definitely not being Varactor tuned, because if it was I wouldn't be able to adjust it with the trimmer cap much. You know, it would give some effect but not much if it was in lock, but it does look like as if there's an issue somewhere there, definitely. Very interesting. So that IC, that DDS IC, might need to just have a look at that, but I cannot tune that any lower. You see, I can't get that down to where it needs to be. Now if I tune the radio to different frequencies, let's try entering a frequency in of say 17.0 megahertz. So I've got a frequency there, 17.2 megahertz on the front, and I'm just wondering if I can adjust that. Yeah, I can still adjust it, but it's not where we need it to be, because when it gets to 17 megahertz it doesn't appear to need it with the look of it. Let's have a look, get it right way down now to 11. Anything below sort of 17 megahertz or thereabouts, it seems to go out of lock. So once it gets below 16.8 megahertz, then it immediately goes out of lock. So to me that would indicate that obviously anything higher than about 17 megahertz probably works from a different VCO, as in being able to stay in lock because it uses a different VCO to operate at higher than 16.8 megs, whereas the other three VCOs are used for the lower part of the radio spectrum and the HF band. So as I say, it's got all this mixing going off, you see, in different VCOs in order to produce that sort of signal. So I'm just looking at this DDS IC again, and now it's still in lock on 17.1 megahertz, and if I just TX, yeah, it's drawing a bit of current on. Let's go back to transmit and then put the N type on, and let's see whether we get any output on auto tune. We've got something there, but it's quite low level, as we can see. Found key, it goes key back up again. Let's just put auto tune on, see whether it's doing any RF power. It isn't. So it's 17.110 megahertz there on transmit, but it ain't locking on. There's not enough RF output power there for it to lock on, which is interesting. So let's just go to TX frequency 31 megahertz, and then expand on that. So that signal's there still, but it ain't locking. That's let's just try 18 megahertz then, see if that will be picked up. Maybe we can auto tune 18 megahertz. If you look at the bottom end of the spectrum there, right down at the bottom end there, we've got a signal picking up with some kind of wide band shenanigans going off down there. So expand on. Let's have a look at that in greater detail. See what that is. Yeah, there's something going on down there. Something quite wide banded. It should be transmitting on 18.380 megahertz, and as you can see, it's definitely not transmitting on 8.30 megahertz, because that would be right down here, in below that, so it will be around about there. So 10 megs, that's it there, look, roughly in there, that's where it should be. So it's not mixing right. So that's in receive mode, that's in transmit mode. So there's definitely something going on with that HF ref VCO. It's definitely not tuning, because we're adjusting this trimmer cap there, that trimmer cap, C403, TC403, we're adjusting that, and then we're getting this oscillator to move frequency. Now there's something strange going on. I might measure the supply rails. We've got a piece of coax obviously into the inductor as well on there, and that inductor, the coil if you like, for the former, we're just loosely coupling, you know, RF. But there's something weird going on there. There's definitely something weird. I think I'll just have a look, see what supply volts we've got coming in on pin number 3. See if we've got you know, the 6.87 volts coming in, and that might rule out any supply voltage issues then to this VCO. So, because that's obviously supplied by that transistor, and we can take it from there. But there's something weird about this, because that inductor's there, that where we've got the coax just in sort of near it, you know, it's only picking it up, it's not, you know, touching anything electrically or having an effect on the oscillator frequency, because it's such a low frequency oscillator anyway, it's not going to be affected by it. But right, I'll get my voltmeter set up and let's just test this this pin here to see whether we've got the supply. Okay, so I'm just checking supply voltages now, and of course on pin number, let's just have a look here, see if we can get that in the picture at the same time. On, I think it was pin number 3, there should be 6 volts. So just in a little magnifier so I can go in. That's pin number 3 just there. Because there's a mounting lug, so we're getting 6.9 volt supply. Then there's a switching line, the RSW line it's called, which goes to the switch, which is pin number 2. So it's this switch there that puts the ground path in for the oscillator, and that's connected to the supply line and then goes straight to the switch to constantly enable this oscillator. So let's just have a look at that to see what voltage that ends up being. So that's pin number 2. It's going to be more trickier because it's under this lug. We don't want to short it out, so I'm just going to try and get onto that at an angle without shorting it. And we're getting 6.8 volts on that pin 2. So that proves that the 2 lines that we've got there coming in, the power supply line and the switching line for the switch, are both operational, these 2 coming in. But yeah, this is sort of free running all over the place, and then when I adjust that trimmer there, it sort of nets the frequency. Now, interestingly enough, this TP 501 is just to the right of it down here. Now if I just try and get that in the picture again best I can, and we go on to what is that test point down there, which if I can just have a look without shorting it. So we're getting 4.8 volts. If I then go on with the trimmer capacitor, adjust that, obviously as you saw on the spectrum analyzer it was altering the frequency, but as you can see, as I'm turning that trimmer capacitor all the way around, what's happening is the voltage isn't moving. So let me just do that again. So I'll just get back on that trimmer capacitor and turn it fully sort of clockwise, and as you can see I'm turning it fully now, completely round 360 degrees, and it's not making a blind bit of difference to the tuning voltage. So it's as if it's not in the capture range, the VCO isn't in the capture range of the PLL. It's as if the PLL is not able to control its voltage. So that TP50 on this tune volts line doesn't seem to be altering the capacitance of these reactor diodes. So we're moving the frequency of the oscillator by changing that capacitor there, which, as we can see, if we loosely couple back onto the spectrum analyzer and we go back on just in the area, we don't have to touch the coil altogether, that's just hovering over the coil. If I now adjust that trimmer capacitor, we can see that it starts to move the frequency of the oscillator when I get on the trimmer capacitor properly with my trimmer tool. It's a pain in the ass, this trimmer tool keeps slipping off as usual. Right, so as you can see there, I can move a frequency up and down, change it, so as I'm turning the trimmer capacitor it's adjusting the frequency. So that suggests to me there's no tuning going on, there's nothing there. So I'm just going to see if we can pick up this inductor here, because that's on the amplifier circuit in this. See what's on pin number 7 on there. So pin number 7 should have a pretty big signal on it, which then goes out then obviously to the PLL IC on through that little white socket. So if I get on pin 7 and let's see what what kind of RF level we're getting there, it should be blowing the back doors off the radio test set when I put a cable onto there, the coax of truth onto pin number 7. So we'll see what kind of RF output it's got. So let's just have a look and see what we get. So let's see if we can get onto pin number 7 without shorting anything out, because that's the big problem here, trying not to short things out. And right, so that's pin number 7 just there. Oh, the coax has moved. Just bear with me a second while I steady things, and let's see whether we can get on it. So we have got quite a high level there, minus 80 something dBm. I mean, it's touching the copper, but whether that's, just need to trace. Just trying to get it on the pin because it's only microns is this pin, such a tiny little thing. So what I'm trying to do is just trying to get the centre of the coax to touch the pin, if you like, and then once it's on I can take a true level then, because I've got the braid touching the chassis of the can, if you like, and of course everything's sub-millimetre level, so I'm just trying to get on this coax the best that I can. So that is definitely that level there we just saw before the coax slipped off again. That was definitely the full level that's coming out. So there. Right, I'm on pin number 7 now. So it doesn't look as if there's quite a lot there, to be honest. It looks like as if it's pretty flat. quite a low level. We're talking neg 80 dBm. I would have thought that'd be that would be piling in with a signal. That it will be about 0 dBm upwards, you know, just maybe plus 10 dBm or something like that. I'll have to look at the level diagram, but that's fully on there, and it's the output level's really poor. If that's pin number 7, which it should be, yeah. It looks to me like as if the output level's quite low. Let me see if I can trim the end of the coax a little bit sharper than it currently is. Because if I can trim it down a little bit, just so that it's got a bit of a point on it, on the end, as opposed to a blunt chisel-like thing. And again, all sorts of microscopic level sort of thing that we're doing here. Let me see if I can get on now. I've got more of a pointed end on the end of the coaxial cable. So I would have thought that signal would be romping in after the amplifier. That would be quite a large signal. That wouldn't just be a little insignificant signal. Yeah. Yeah, it looks to me like as if that amplifier might not be working. I'm getting more signal, more or less, picked up when I'm not touching the centre of that thing than I am when I am touching it. So it's like as if the RF level's pretty poor, you know. So I don't know, it just seems very, very poor to me, does that. That signal level's very weak, considering there's meant to be an amplifier there. Now there's an inductor there, L470, I think it is, which is just here, and that inductor might be able to help us if I can get on there. Now I have done a quick measure of DC conditions around this this transistor, and I'm getting that 6.5 volts there on this top side of that, bottom side of the L460. So I'm not sure what's going on here. It's like as if this amplifier's not running properly, or there's no RF output. Maybe these FETs have gone, maybe. There's a problem with these FETs. I don't know. It seems a bit strange. But I've just gone on there with the coax of truth on pin number 7, and the RF level's abysmal. It really is. It's shocking, is that. The problem is, of course, this circuitry round here, this is actually underneath this lug. It's just right under there. You can probably see a bit of a black inductor just under there, and this lug covers all that circuitry. So it's not like I can get down there easily, you know, in order to get onto things. And I don't want to short things out and blow things up and make things even worse than they currently are. But there's a amplifier transistors just down there. You might be able to just see it if I just try. It's so awkward because this board has to stand on its edge here, and then trying to obviously video it for the channel, it's difficult. So, but everything's down there underneath, and of course when I go onto there on that pin there, pin number 7 with my coax, I'm not getting much of a signal at all. So it suggests to me like as if the RF amplifier is not running. So, and if that ain't running, then the signal level coming into the PLL IC that sits under this module won't be high enough for it to see the signal that the oscillator's running at. So I've got to see a definite amplification, if you like, of that signal coming out on pin number 7 on there. So that's the issue. A lot of these components are under this lug here, so I'm going to have to try and do something to try and remedy that. Back shortly. Right, I think I might be getting somewhere now. Now if I touch this capacitor down there, we've got a massive signal now. So I just touch that capacitor on that side there, we're getting a huge signal. And I did see the oscillator's frequency move as well. So I'll just right, so let's just have a look at the marker level. Let's see what level we're getting. So we're getting +2 dBm, so that's good. That's the signal level that I'm hoping for. It's at 36 megahertz at the moment, which is not what I want. But I did find that when I was touching round there with the coax, it jumped frequency a little bit. So I'm just adjusting that trimmer capacitor again, and it's coming down there. Yeah, it's still off though. At 36 megahertz, it should be running between 31 and 32 megs roughly. But at least the level's there, so that proves the buffer amplifier is running. So basically what I've done, I've just taken the coax off. I've just gone on to the, what is this inductor capacitor there. So basically this C623 rather there, I've just been onto that, and that's the output. So this amplifier is definitely running because this oscillator wanted to produce +2 dBm. So there looks to be obviously a frequency error on here, and there might be something around this varactor diode, this vary cap, this inductor. I wonder if it's worth soldering around inside here, just in case any dry joints. Things don't look dry from what I've seen under the magnifying glass. Things look okay, but this tuning capacitor here, I'm tempted, if I find this package, to lift the leg up that connects here to see if that made any difference to the frequency, because even with the 4.8 volts I think it was, or 4.6 volts that's currently just on this tune line, it'd be interesting to see the frequency with this varactor in circuit versus the frequency when it's taken out. Because if this varactor's stuffed and it doesn't work properly, then there'll be no frequency change, because if that's open circuit, if you like, it won't have any effect on the current frequency of the oscillator, whether it's in circuit or out. Whereas if it is working as a varactor, then it's responding to the voltage which is on this line. So obviously the 4.6 volts or whatever that we currently find ourselves with on this line would then adjust the capacitance of that in relationship to 4.6 volts, and thus it would influence the oscillator's frequency running. So by lifting this pin here on this line, we would see a frequency shift, a difference in frequency. So that's something we can have a look at. So we can take a measurement of the frequency before and after and see what effect that package has, if we can find it on the schematic diagram, on the PCB layout rather, and then we just lift that pin and see what happens. Okay, so the varactor diode I've found is just there where this yellow things are touching, just that device there. So I'll lift this end closest to this coil, lift it up, and then let's see what frequency this oscillator is running at after. So if I just put the coax of truth, just loosely couple it into the oscillator chamber and see what frequency we are getting. I just want to have a look, and then we can make a note of that, write that down. This coax has got like metal with memory, it wants to keep moving. Right, so let's just take a note of the frequency, and let's just have a look here. Oop. Right, so move marker 1, and it is at that frequency there. Call it 36.360 megahertz. 36.360, so 36.360 megahertz. Right, now what I'm going to do is I'm going to switch the radio off, and then we'll just use a soldering iron now to lift this varactor that's down there up, and then let's see what frequency it's oscillating at there. Right, we've lifted it up. You might be able to see that down there now. It's lifted up, the end is pointing upwards. You can see the contact. It's off the PCB, so we'll just reintroduce the power and then the coax of truth, and then let's see if it's shifted frequency to test the theory for varactor diodes actually tuning. And if I can get this power lead to go on, there we go. Right, so we're powered up, and now we'll just drop this in, and as we can see now, let's have a look. Looks like it is having an influence then on it, because the frequency is totally not where it needs to be. It's not there anymore, the frequency. Let's just widen it up so it's right up here now. Is that right? 44.4 megahertz. So that varactor, that proves the fact that the varactor diode is actually having an effect on the oscillator's frequency with the current lock voltage on the tune volts line that we're currently getting. So if I just zoom in a little bit here, so basically we've now disconnected this top end from the circuit, and we've proved that this oscillator is now running at 44.4 megahertz. And obviously I can steer that frequency on the spectrum analyzer if I then try and tweak that variable capacitor that we've got here. And I'll just go onto the trimmer cap with my trimming tool and adjust it, and as you can see there, I can tune it way up there, and then I can also, let's see if I can bring it down. I can't bring it down below around about that frequency there that we've currently got at. So lowest frequency I can get to. So that proves that the varactor diodes themselves are having an effect, because they're currently getting supplied with about 4.6 volts, I think it was, on this line here, and thus it brought the frequency down to 36.360 megahertz. So that varactor is definitely tuning, it's got a frequency. So the oscillator is definitely oscillating, the output is definitely being buffered. That's then going off then to be read by what is the PLL IC down here. So is there a fault with the PLL IC? Is there a fault in this area? I suspect this IC is probably buried under the VCO module, but I'm going to have a look at that now to see if there's any issues around there. So we've definitely got a frequency coming out of here, although albeit wrong. We've got the varactors definitely tuning the oscillator to a frequency, but not the frequency we want. As we adjust this trimmer capacitor, the lock voltage line, which is on here, TP501, isn't adjusting. It's remaining continuous, constant. Now what will be interesting now is, because we've removed this varactor diode and we've left it hanging in the breeze, if I adjust that trimmer capacitor there to alter the frequency of oscillation, let's see whether the PLL IC is working, because if it is, I'd expect to see the voltage on here start to move as I move the frequency of the oscillator by turning this trimmer capacitor, because it's moving the frequency of the oscillator further away, and obviously it's going to try and control it. So if I go now back on here with the multimeter, and then we go essentially using that multimeter, and let's just see now whether it makes any difference. It may do, it may not. Right, so put that in the chassis, and then I need a trimmer tool, and then let's go on to what is TP 501, 502, thereabouts down here. It's that little, I'll just move the camera up here a second and see whether I can see it then with my little magnifier, so I can get on it without shorting anything out or disturbing anything. There we are, look. So it's currently at 4.8 volts, I can see the frequency on the, let's see if we can get it all in the shot. So we can see the frequency there, I think, and then I've just got to try and adjust this. Never rains, it pours, doesn't it? Right, 4.8 volts. So let's just adjust this trimmer capacitor then and see what happens. It's very difficult to try and do all this with just one pair of hands. So we can see the frequency of the output of the oscillators moving as I'm adjusting the trimmer cap, but the voltage, the PLL voltage, ain't moving. Oh, it is there. Hang on, no, that was just me, I think, on the, I'd slipped off the test point. Where is it? See if I can get back on the damn thing. There we are. I'll just come off the test point, I think. Oh, do you know? It all goes wrong, doesn't it, when you... Oh, what's gone wrong now? Let me just have a look under the magnifier, make sure I'm on it. Let's have a look here. These leads keep slipping off. Everything's really hard to see because of the voltage. Test point is so small to get on. It's just a tiny little island. And then let's just have a look and see whether this changes then. Yeah, so it is changing its voltage then. So it's going from 4.8 volts there. So it's trying to tune it. Now it's gone to nothing. I'm tuning the frequency that way, more closer, and then it's now disappearing off right up high. Now it's lost its lot voltage. Frequency of the oscillator's coming down now, and then it's 4.82. So it's either 0 or 4.82 volts. So that's strange. I wouldn't be expecting that. I'd expect a gradual change in voltage between two limits, a low voltage and a high voltage, because as the oscillator's moving away more and being more out of phase, it will need to try and adjust the varactor diodes for that. And as we can see, what it's doing is it's either nothing or 4.82 volts. There's nothing in between. So that does now look to me like there could be a PLL chip issue, potentially, because obviously we've been adjusting this capacitor here, and it's either all or nothing. Either we've got on this test point here, test point 501, either no volts, or we've straight to 4.odd volts, and there's no in between. There's no sort of happy medium. So there's definitely something going on down here. Now it could be that the reference input there on the OSC1 coming out of this is wrong, so it's nothing really stable to compare it against, and thus no matter what we do with the tuning of this oscillator, it won't pull it into net. It won't adjust the varactors with the right voltage. So I just need to investigate this circuit now, this part of this. We've obviously got, I think it's the 32 megs signal coming in here, and then whatever this chip does, we need to read about this and find out what signal should be on the output of that, and then have a look at doing some measurements if we can get onto them. The trouble is these chips are underneath the modules, the VCO modules, very difficult to get to. But at least we've proved the oscillator is running. We can tune it somewhat with the trimmer cap. The varactor's proven to be working somewhat, because when it's in circuit it's at 36 megahertz. When it's out of circuit it jumps up to 44.4 megahertz. So that proves the capacitance of those diodes is working. We've proved the buffer amplifier is working. It's giving a nice plus 2 dBm signal output, obviously into this IC, as well as going off to the other PLL chip. So the only problem I've got though is the fact that this tuning voltage on that test point is either all or nothing. There's no in between, which means to suggest to me there's something way out of phase on this reference line here coming in. So I think it's just a case now of reading up on the DDS chip. Right, we've managed to unsolder the HF reference VCO. As we can see, there's quite a lot of flux residue underneath, originally from manufacture, and we'll see when we look at this PLL IC around it that there's some solder debris still from the original manufacture, some solder slivers and other things that have got entrapped on the resin and fluxes. So again, not very good finishing at the factory, but we just thought we'd have a look at this in a little bit more detail, and then we can see some of the components that we couldn't see before. So what I'll do, I'll just put the camera down here, and let's just have a look. So, and we'll just have to try and get this thing to magnify and see if it'll pick out better. Okay then, so basically we've got that trimmer capacitor, which is on the top left hand side of the picture, and which is just this baby. Now the main oscillating transistor, I believe, is hidden under here. I think that's the main oscillating transistor there, that device. This is a varactor diode, which is in the bottom left hand corner. So that's what we unsoldered earlier, this, and lifted it up. So that's the varactor diode, that's the main oscillating transistor. And then with two other transistors as well, when we look in a little bit more in depth. I just need to try and get the light a little bit better if I can, just so that we can pick those out. But basically, there's a transistor which is a sneaky little devil. It's just hidden up in the top there. Now, this transistor at the top here, this one, I believe that to be the switch that grounds a path from the oscillating transistor. So that enables the VCO oscillator. And then also on the just under this lug here, around this area, there's also another transistor thereabouts, which is just there, look. Now that there is the output amplifier, that transistor there. So I might be able to see that a little bit better. Now the inductor and the capacitor for the decoupling of that amplifier are these devices here. And then you can see there's also a little bit of a solder sliver, which isn't causing any harm at the moment, but it's just there where the bottom of my screwdriver is. I'm just moving it there, look. Again, that's something that's contaminating the board, and we've just got it on the end of the screwdriver, so we'll just remove that. But I was hypothesizing earlier, when we went onto the gold pin, which is on the VCO, which is this pin number 7 there, we went in there with a coax of truth early, and we weren't getting a signal really of any significant amplitude. Anyway, I thought that there could be a dry joint between the track, which comes off the right side of that inductor there in the very top corner, and goes down. As you can see, it goes under, connects to that pin. But as we can see there, when we turn this round and we just try and zoom in a little, I'll put the magnifier on now, see if that can make things a bit better. But I'll just go in and see whether we can actually pick something up in there. And just trying to see if I can get this damn thing to focus. But basically, there is solder. It's not very good, that magnifier, but there is solder there under the pin on the far left. So that track from pin number 7 goes directly into that socket, if you like, goes directly off to those capacitors on the left. So to me, that looks okay. I can't see any evidence of any dry joints or anything like that in there. There's nothing of that nature I can see. So I'm not sure really. Again, underneath, having a look here, Can't see anything really evident that stands out. There's no sort of solder slivers or anything like that there. Nothing of any note that I could see. Nothing, you know, there's the odd little glitch like on that track there on the top. There's just some debris or something that's stuck to that track, which seems a bit crispy. I don't know what that is, but again, that's looks like this print might be damaged. I'll have to just wipe that off with a bit of isopropanol alcohol, but I think it's okay. But again, obviously not finished off properly from manufacture. Don't think it was causing a problem, but I'll have to look at this little island there just to make sure, that little veer, as to whether there's any corrosion in it. But goodness knows what that is. Looks like some kind of solder splatter. Again, the odd little solder sliver here or there. There's something which appears to be evident, which is just the amount of flux residue that there is around these pins and everywhere. So again, a little solder blob there, look, captured on the far right hand pin, which is obviously just there, that little solder blob. You can just see it there that I touched with the screwdriver, but again, that wouldn't be causing a problem. So I can't see anything there. Okay, so let's move on to the PCB then, and if I can find it, here we are. Look, this is where the thing was soldered. Again, bit of debris there, look, you can see. Obviously, again, where the hell that's come from, I have no idea, but that's floating around, obviously going to cause an issue, so that needs to be removed. If that gets under these pins of this IC, it'll short them out, so just seems a bit strange. This track here goes off to what is a different VCO, and again we've got the resistors there which are coupling it obviously straight to this PLL IC, and we have another chain of resistors there. A couple of them are 0 ohm link resistors. Capacitor looks okay, there's no cracks or lack of solder on one side of the pins. Again, a little bit more evidence of some solder debris. That's the test point there, TP501 on the island, which goes obviously to that pin. That's a lot volts line. Again, we've got that little electrolytic, that A106, which goes across the what is a loop filter and that RC network. And then we've got other components around. The pins on the IC look okay. There is one which might look a bit strange, but we can try and zoom in now using the magnifier, and let me see if I can get right in on that now. And I'll just back off with the zoom on this camera, and then let's just see whether we can get some light on it. But I can't see anything that would be wrong. It looks okay to me. There's that IC. It's just a shame I can't get this damn thing to focus properly. Yeah, there is a pin sort of 5 down on the left from the top that looks like it's not soldered as well as the other pins. You can see that there's a bit of let's see whether we can turn it round. There's some, although it depends how you look at it, you know, whether that just needs a re-solder. We may as well while we're down to this level. And it does look like as if it perhaps could do with a bit of a resolder, but nothing really evident that's standing out, you know. There's nothing shouting at me as such, so who knows. Those are the 3 lines obviously that go off as part of its supply and programming. And again, there's nothing really big that stands out at me here, apart from just that pin there, the 5th down. So I'm just trying to, so it's like 2, 4, 5, that one there, that IC pin. So I might have to just try and get a little pointer thing on it, try and get in closer level, see if we can see anything. But I was hoping I'd be able to magnify in with the little magnifying glass here and then go right in and try and get some detail. But the trouble is you have to go that far in that then the magnifier blocks out the light, so it's a waste of time. But yeah, nothing evident that I could just, you know, I were hoping it'd shout at me and say, oh, this is the definite fault. So again, another mystery. I suppose all we can do is just resolder, clean up and then reassess. Okay, so I just finished soldering this IC, so we'll have a look at that, and I've cleaned the board there. I've just removed the coil from this circuit board while I just do some resoldering on the other side as well as this side. But I've just sucked all the solder off these pins here, because these are through hole pins and they'll go through the board to what is connections on the top as well as the bottom here. So I've just removed all the solder from those and we've put some more flux on. So I'm just going to go and just resolder these using this Metcal soldering iron. So I just want the solder, just warm the pin up as well as the island, but I just want the solder to run down the pin through the via and then into what would be the solder the top part, like we did on the other VCO assembly with LO1, 2 and 3. I just want the solder just to run down, and then when we look at the connector on the top of the PCB, then we should be able to see that solder has effectively run down the pin and gone into the top part of the PCB. Now I don't think it's going to be a major thing, because the vias on these Kenwoods are quite good. They're like a copper tube that goes through the board, and they are in relatively good condition, most of them that I've seen on this radio. I haven't seen any corroded ones as yet, although, you know, time will tell. But it's always better just to try and make that solder connection straight through to the top of the board if we can from the bottom. So when we put it back in, then we've got an assurance that there's a connection through the board to the top. So I'm just seeing if that's going to be effective or not, because last thing I want is to go to all this extreme and then put it back together and find out if there's still no solder on the top bit. So I'm just going to have a look at the top. Yes, lovely. That looks to me like as if we've got some solder. I'm just going to hold it up to my little magnifier and I can see, yes, we've got solder to the top and the right down there. You can probably just see, if the light's right, between the PCB and that little gap in the white socket, there's solder there, I can see. So that's good. So this coil was obviously in there, and I'm just going to solder around inside here. Now obviously we're clutching at the straws because there's no obvious component failure. The DC conditions around these devices as per the voltage diagram for the VCO are correct, so it's not like as if a device has failed. I can't see any evidence of any broken capacitors or resistors or anything like that, any chips or any bits of residue in there other than what we saw on the back of this board, which I'm going to clean off shortly. So it's just a case of is there a dry joint? Maybe that's something that you know, I'm trying to rule out. We know the tuning cap works because obviously when we twiddle it, it alters the frequency. We know varactor works to some extent. There are two little varactors inside that one package down there, that little varactor diode package. It could be one of the varactor diodes has failed and the other one is working and it doesn't have enough capacitance to pull it down to frequency. So that's a potential failure. Maybe it's got tired over time, I don't know. Maybe it's broken down, but we'll talk about that sort of thing next when we move on to the next part of the video. Okay, so this is a final article, and as you can see, we've now cleaned all the debris off. If you remember, we had like a bit of like crusty stuff just on the track there at the top left hand corner, and when I cleaned it off with this screwdriver, it sort of looked initially to give first appearance that the track was damaged, but it isn't, and we're all okay there. Obviously I've washed all the, after resoldering, I've washed all the flux residue off. We've got rid of all those solder blobs and slithers and God knows what else that was all over it. We've put the coil back in, and everything looks nice and clean there, as you can see. So ready to put that back in. Resoldered in there as well, best I can. Done the usual, but yeah, nothing really that I could find stood out. This is the PCB, and as we can see, again, I've resoldered the components here. I had to put a bit more solder on the end of this capacitor because it was a bit dry, and just to make sure it got a bond down. It was a little bit sort of sketchy on the back of this capacitor, but the rest of the pins on this IC have all been resoldered, and all the other components all been refreshed. So we're ready to put it all back together again, and let's see what happens. Right, we're all back together now. We've got the module in, all nicely soldered, etc. back in. So we're ready to do any testing. Obviously, I looked at the block diagram earlier, and I sort of did my own little version of it, of less complex, because the block diagram's quite all over the place. But basically, just to explain this HF reference VCO that we've got here, this VCO that we've been working on just now is this HF reference VCO. This has its own PLL IC and loop filter. If you remember, underneath we got the IC that we resoldered, and then there was also some capacitors and resistors, which was part of the loop filter that we could clearly see going to the pins on the PLL. And then of course the output of this VCO is coupled out on pin 7 on that white socket, and that's then fed as a reference frequency then for another PLL IC, which we saw sat underneath this can. When we removed this earlier, if you remember, there's an IC under there. That's this PLL IC, and that PLL IC also gets its reference from the HF reference VCO. If you remember earlier, when we started, I think the alignment description said start at 30 kilohertz, then I think it was 10, 12 megs, something, 17, 18, 22, 30 something, and then ultimately ending at 50 megahertz. That was where it was switching in these VCOs. Each one of these VCOs within this module has a select line from the microprocessor. So obviously, as we enable different frequency bands on the radio for both transmit and receive, then these VCOs in the HF frequency range get switched on and off appropriately. So they all have limited bandwidths each. The output of that is fed back into the PLL IC, which again sat under this IC, and of course we were noticing that the voltages weren't correct on the tune volts line here, which we were measuring, which is this little test point down between these two cans, and the voltages in the alignment didn't match the voltages which we were getting on the VCO. So the alignment instructions differed somewhat, but when we did get the VCOs running and the radio was working to some extent, that didn't last long before it went out of lock, particularly when we went to transmit. So there's some weird problems going on, but anyway, the VCO, obviously this HF reference VCO, we proved was way off frequency in comparison to where it should be, because it should be between defined limits, and it was above those defined limits by some margin. And indeed as well, when we removed the reactor diode, it went up to 44 megahertz, and we couldn't net it down at a lower frequency. So I would have expected to see a sweep of not only the higher frequencies, but as we adjust that red trimmer capacitor down there, I would have expected the frequency to come quite low as well. So again, that's another consideration. What's preventing the oscillator from oscillating at lower frequencies? So obviously without the HF reference VCO running on the correct frequency, then ultimately the PLL is going to get the wrong reference frequency, and ultimately these VCOs as well are going to go out of lock. So earlier in the video we were looking in this area, and now we've obviously been looking in this area. Now elsewhere on the system we've obviously got other VCOs for the VHF, UHF. However, they too mix with the HF VCOs 1, 2 and 3 in a mixer, and both on for transmit and receive. So what's common on most radios, including LMR, amateur radio transceivers and other transceivers like marine, airband, things like that, is normally the VCO produces a fundamental for the transmit. However, on the Kenwood TS2000 that's not the case. What happens is that there are two VCOs, if you like, or more, which essentially mix together and produce what is either a down converted or unconverted frequency for producing the VHF and UHF transmit signal, as well as the receive local oscillator injection for the mixer on the receiver side. So this is where this sort of topology is a little different in design to other radio transceivers, because quite commonly you'd have a VCO that will produce both a transmit and the receive frequency. So obviously when you key up the radio to transmit, say at 145 megahertz, the VCO will produce 145 megahertz, and then when you unkey the transmit and it's the receiver, say it's 21.4 IF, it'll jump either high 21.4 or low 21.4, depending on its high side or low side injection, to then produce a local oscillator frequency for the first mixer. Whereas on this radio it works completely different. We've got other mixers after this which mix with other VCOs to produce both the receiver local oscillator injection frequency as well as a transmit fundamental. So this is where things can get quite complicated. It'll take then one of the VCOs to pack in and not oscillate properly, and then all the bands don't work in one respect or another, or most of them would. So this is where we're at now with this. So regard to this VCO here, this HF reference VCO, there is, I've read and also seen on eBay, a transistor kit for these radios, because apparently there's a blanket problem with transistors on the Kenwood TS2000, certain specific ones. Now I've had a look at these transistors, and one of them lives inside this VCO. Now the conundrum that I've got is obviously the DC conditions as part of the circuit diagram they're sort of annotated in red. So when we measure with the DVM, we're picking up the correct DC signals as opposed to incorrect signals or incorrect voltages. So everything looks okay around those transistors DC wise, but of course we have this weird situation where when we adjust that red trimmer capacitor, we're getting a frequency that's way above where it needs to be, and we can't pull it down below 38 megahertz or thereabouts. It stays up in near the 40 meg range, and we can't get it to come down anywhere near the defined bandwidth that this oscillator should run in. So that could be the varactor diodes got a problem, because there were two diodes within the single package straddled in parallel across the oscillator's tunable input. So naturally, is it the case that the varactor diodes have failed, or one of them, and that's why we are getting a slight change in frequency when we have the varactor diode in circuit versus out of circuit. But even so, with the varactor diode out the equation, as we did, we lifted it, by adjusting that red trimmer capacitor, I would have expected that oscillator to have gone really low in frequency, well lower than the frequency we desire, as well as higher. And so therefore I would have expected that to have occurred. Yes, we're removing some of the capacitance with the varactor diode, but just considering we've only got a small margin of a couple of megahertz in frequency difference, I would have expected that red trimmer cap to have taken the frequency well beyond the usable bandwidth of the oscillator, and that's not happening. So is it the case that the red trimmer has got a fault and its capacitance isn't the correct value, and thus it's not able to net the frequency of the oscillator? Is it the varactor diode that's got one of the two diodes popped? Is it the oscillator transistor? Does it have some weird problem with RF performance at certain frequencies. Certainly the case with some RF transistors, particularly power amplifier transistors. They can often work DC wise and measure correct with DC bias conditions and DC conditions insofar as measuring them, the diode junctions with a multimeter. But when it actually comes to RF performance, like gain for example, then there can often be low RF gain but perfectly fine with DC condition wise, and we've certainly had that in the past. So again, I'm sort of clutching at the straws. I don't really know what's wrong. It seems that there's so many different possibilities, but one of the things that we could do, if we can get hold of the transistors for this oscillator, the main oscillating transistor and the varactor diode, then obviously we can replace those. We might obviously replace the trimmer cap as well, and or we could remove a trimmer cap and measure it on my capacitance meter to check that the adjustable range is there, because again I've also read that these caps can go faulty, but normally when they go faulty they go completely faulty, as in the jitter, there's a massive change in such a small incremental turn, or they either have a fixed capacitance and you can't adjust the output, or some other weird problem where, you know, fraction of a turn 1 minute it's one capacitance and then it's all over the place and you adjust it a little bit more. But when you spray some isopropanol alcohol in it, that'll dry off quickly just to clean it up, then it sort of brings it back. I'm not seeing that sign here with that capacitor. It is adjusting, it's smooth in its adjustment. There's no clear indication that capacitor will be faulty. I generally don't suspect it, to be honest. But we're sort of clutching at the straws. Now, should I go and remove these 3 modules next while we've got the board out? I think that might be worth doing and having a look at those modules underneath. And we've seen so many cases with both these modules removed of the extraordinary amount of debris, solder flux residue, blobs of solder, slithers, little bits of what appears to be solder sort of strands that's not been finished off or washed off the board as part of the manufacturing process. So is it the case that, yeah, while we've got the board out, should we remove these 3? Obviously this has had that modification down there anyway. Again, these are critical oscillators because ultimately, depending on what frequency band we select, these two would mix with the signals coming from these HF VCOs to produce the fundamental frequencies that we need for other frequency bands. So again, where do we finish with this? Do we carry on and remove everything, all the cans, and have a look at them, considering the work that's involved in doing that, or do we stop? So this is where we're getting to the point now of, yeah, spend a little money perhaps replacing some of the components in there and trying that. If not, where do we go from there? So let's see. Okay, I just wanted to recap a little bit. Now that we've got more knowledge and more information and we've learned a bit and developed, we've obviously got this board ready to go back in. However, when we look at the VCO boards, there are 2 boards, obviously a smaller one and then a larger one. We've had this VCO LO1, HF VCO LO1 out, which consists of 3 separate VCOs. We knew we had issues with this. The voltages weren't quite right, the frequencies were in error. We had definitely got a problem with the HF reference VCO prior to resoldering and putting back in, and we still need to check that, but I think we're not out of the woods with that yet. And we also had another measurement which was concerning this LO2 right at the early part of the video when we were doing the alignments. You might remember we did this voltage diagram and I asterisked LO2's VCO, which is also a very important VCO because it mixes with LO1. So these 2 VCOs, in order to get the transmit carrier running and also other things, these 2 have got to mix together in order to produce the TX carrier on HF bands. And so also it mixes with the VHF and UHF oscillators as well in order to create the carrier. And we'll see that in a moment. We'll look at the block diagram. But as well as the reference VCO and the HF 1, 2 and 3 VCOs being out, which consist of the LO1, we've got discrepancies with voltages as per the diagram. But in particular, LO2 VCO had a major issue where when we measured it with the probe on that test point, it went out of lock, and then when you remove the probe, if you remember earlier in the video on the test point, the DVM, then the VCO fell back into lock again. So there's definitely an issue with LO2, which is this little VCO here. And this is on the board at the front. It's down there. It lives on a board there. So we're going to have to look at that again. If you remember earlier in the video, we were going to remove that VCO, and then I decided not to because we didn't have the knowledge at that time as to where the fault was and that it would be a difficult job to remove. But I'm definitely going to have to look at that one again. So let's just have a look at that and let's just understand that a little bit more on the circuit diagram. So if I just go to move this then back to the wiring diagram and the block diagram. So there's an exploded view, semiconductor data adjustment, terminal function. Let's just get rid of that, and then there should be a block diagram. There we are. Look. Right, so if I just zoom in on this block diagram, and as we can see here, and I'll just go in a bit further so we can see a little bit more. So we've got HFLO1, which is there. This is obviously buffered and comes out, goes to two mixers, one for the transmit path and obviously one for the receive. The transmit path is a lower section, the receive is the upper section coming in. So HFLO1 VCO, which is those three independent VCOs within that larger cam, they live in there. And then if we have a look here, we've got LO2. Now this is a little VCO that we're having problems with earlier when we were measuring with the DVM on the test point. This one went out of lock. Again, this has to mix again with a signal coming from this way, and ultimately the two signals from LO2 and HFLO1 mix together in these mixers and then come out with the correct frequency for transmit between 1.8 to 54 megahertz for transmit. So we know we have got an issue with the reference VCO, which is part of this HFLO1. It's not shown here on this diagram, the HF ref VCO, but the reference frequency for this HFLO1 comes from the HF reference VCO. So that's part of that, and we've got this issue with LO2 which we need to look at next as well. Now it's interesting to note that in addition to that, we've also got the signal which comes into the TX path also comes from another VCO down here, which I believe is called the T-car, and there's an FM modulator, and obviously this is a varactor modulated oscillator. So when we have our audio coming in, the frequency of this is deviated, and we haven't checked that yet, but that's something I will check as well. And there's the T-car there as well, which is this, again, another oscillator which comes in a mixer. So depending whether it's FM, AM, SSB, as we can see here with these modes, depends on what's switched in. I don't suspect that area, to be honest with you, but it will be a check that I'll probably do later on. The problem we've got is up here in the LO2 and LO1 circuitry. Now what isn't helped on this diagram is it doesn't show the reference VCO, the HF ref VCO for this, but we all know with the knowledge that we've picked up as we've gone along that HFLO1 is controlled by a HF reference VCO. And of course we've got coming off here taps as well, obviously for VHF and UHF that come down and then ultimately go to circuits down here for VHF and UHF inputs and outputs, etc. So there's some interaction going on between them, but mainly the issue we're getting is obviously in the HF range to 50 megs. So I need to look at this again, LO2, take this to bits and have a look at whether there's any solder splatters and problems like we found with the HF ref VCO, like we found with the HF LO1 VCO. They were all suffering with problems with solder splatter, resin, slivers, blobs, all sorts of things. So we just need to have a look at that LO2 again, and take that off that little board. Now what I also am going to do is, as we saw earlier, this oscillator was suspicious. It sort of ran when it wanted to and then didn't want to run. Now the varactor diode which lives down there on this circuit, I couldn't actually get, when I've looked online, the part number for that it's just no longer available anymore, and I can't find a source for that particular varactor diode. I've looked at the part number online, and it is I think it's a Toyo component, and so we can't get that anymore, the varactor diode. So it's possible that might be faulty, but we won't know until we replace the main oscillating transistor. Now these radios are known for having problems with the transistors, and that's why there's this kit available on eBay for blanket changing them, and there are all sorts of different transistors used in this radio which apparently have problems. Now the price of the transistors are about £4.80 a piece, so they're not exactly going to break the bank if we order them. So I might order sort of the same transistors used on all of the VCOs, from what I understand. So it's not like as if we, we're going to run out of transistors if we just replace them all. So I think what we'll do in the interim, while we're looking at this other board, which is this LO2 VCO that sits down here, I think I'm going to order the transistor for these VCOs, and then just replace them, because we're not going to lose anything, and we are sort of clutching at the straws. So if I just go to what would be the diagram for our VCOs again, and I think we've got a wiring diagram, and then I think if I just have a look at that PC board, circuit diagrams, and then I think it was a TXRX2 unit. I think it was down here somewhere. We had the schematic diagrams for the VCOs, which I believe is round here somewhere, and we can have a look at those again and have a look at the transistor. So I think it was there we are, TXRX unit, far side view, circuit diagram. Right, so if I just zoom in on this, and oops, and then just zoom in, and here we are. So this is the LO2 VCO, which we'll be looking at in a moment. So the LO2 VCO, when we zoom in a bit more, it uses a 2SK 508 November Victor. That's the transistor, and these are used commonly across all the VCOs. So ultimately my goal now is to buy these transistors and replace them, because I can't get the varactor diode anymore, and the varactor diode, this Mike Alpha 2S, I think it's 304, there's different types of diodes that are used on this. There's one, this is a single package if you like, this particular diode, and I can't get that MA2S304 anymore. So I've had a look. There might be somebody somewhere that has them, but I can't see anything coming out doing a Google search. So the chances of getting this varactor diode are pretty slim. Again, I don't really suspect the varactor diode to be an issue, because we've had so many problems with the other VCOs as well, more than one VCO using the same component. Potentially it could be that, but I haven't got a part to replace it with, so you know, we're stuffed. Of course, it could be a potential 10 picofarad trimmer capacitor might be on the blink. We might be able to get that, but I do want to replace this transistor. There's a lot of information that I've seen about these transistors failing to some degree. Now I have measured these DC conditions round one of the oscillating transistors, and the DC levels are indicated in red here, are more or less around this, not exactly this, but they're more or less around it. But again, I'm sort of, you know, I've hit the buffers. I don't really know there's nothing standing out that's obvious. And sometimes transistors break down when they get warm, and they have all kinds of weird issues and things, and or the capacitances of them, if they're breaking down, that affect the oscillator, and there's all sorts of issues that you can get with the RF conditions around them. But generally speaking, if a transistor's got good good DC conditions, then the RF conditions should follow suit. However, I do know from experience, particularly with RF power transistors, although they're a different construction to these, you do have problems sometimes with gain in them. Even though the DC conditions are reading correctly, the RF gains on some transistors are not as good as others, and that's down not just to the HFE value, but also internal structures which are either failing or weakened. So whether this is an issue, and bear in mind it's a known problem on the Kenwood TS2000s apparently, that some of these transistors are starting to fail or are failing, and that's why there's these kits available where you do blanket changes of transistors. So with nothing to lose, as I say, you can get these on eBay from a reliable source, not from China or anywhere like that, but a reliable source where you know, and I have other sources as well other than eBay obviously, but that's just so anybody who's interested in doing these repairs can get them from there too. So I'll order these transistors. They're only £4.80 a piece. I'll get you know, 2 or 3 of them, and then we'll drop them in and see whether we can get more success with it in both the HF ref VCO and the LO2 VCO. So for the price, I think that's definitely worth doing. It might help us a lot, and then we know at least we've got fresh transistors in there that are, you know, are new ones, and whether that will get the radio working, because again this fault is intermittent, as we've seen earlier in the video. We have had you know, this running, and then it doesn't run, then it runs, then it doesn't run. It's up and down. So, and I've not seen any evidence of dry joints or anything like that you would normally find. So I think the best thing to do, let's get the LO2 VCO out, get that board out, remove that module, have a look, see what's underneath. There's a load of splatter and solder bits and bobs underneath, like we found with the other VCOs. There's terrible condition of Kenwood not finishing the product off properly before it was shipped out. And let's see if we get anything on this board here, and then while we're doing that, the transistors will arrive that I've ordered today, and then hopefully, fingers crossed, we can put those in and see where we go from there. Okay, so advancing on in our knowledge and our endeavour to try and resolve this fault. Earlier in the video we discussed a lot about the VCO LO1 module, which is this, and this is the module we removed earlier. Within the VCO module LO1 are 3 individual VCOs, and we found that when we did our measurements earlier that all 3 VCOs were going out of lock. It didn't matter what frequency band you selected within the HF frequency range of 0 to 30 megahertz. because as we selected each individual VCO as per the frequency that we assigned to the radio, we found that no matter what frequency we went to, the VCO went out of lock. And so we ultimately started to look at the HF reference VCO, which plays an important part, as we've just described in the latter half of this video. Now, what I've done, obviously, we've dealt a lot exclusively with this PCB, which is essentially is this board here. And we've looked intently at the reference VCO, and we've proposed a solution to repair that, which I'm going to go into next. But in addition to that, the output frequencies from these three VCOs for the HF frequency spectrum get mixed, as we saw earlier in the video with the block diagram, with another oscillator called L02. Now L02 lives on this board, and this board is here, and this is L02. So L02 is a little module, which is this one, and that sits there. And then ultimately the sub VCO, which I've also removed for checking, is this VCO there, and they live on this board. The PLL ICs respectively for each VCO are these two ICs. So I've been checking this board here to make sure that there's no solder slivers, blobs or anything like that that we found on the other VCO assemblies when we removed those. So I've got a plan for this VCO, which is L02, as well as the reference VCO, which is here. Now, just to recap, if you remember earlier, I did this little diagram. We had L01, which is this module here with the three separate VCOs. That has its own PLL IC, which lives underneath the module on the circuit board. And then basically we found that no matter which one of these VCOs, because all three had a common test point, no matter what frequency was selected, because the switches that switch them on and off, the VCO was going out of lock. Now, with the other VCOs elsewhere on the board, the PLL, we noticed that the reference oscillator, which is this module here, provides either a doubled frequency or its single frequency output to each one of these PLL ICs, which controls all the different VCOs, other than this particular VCO. And so therefore all the other VCOs and PLLs get a direct frequency from this reference oscillator. So that explains why the other VCOs seem to be in lock, because it's getting a frequency directly from this. However, this VCO, which is L01, which consists of these three oscillators, gets its reference frequency not from this, but it gets it from this, which is the reference VCO, what's called the HF ref VCO. So this oscillator, which is this, sits outside generating a frequency. Again, it's programmed with data from the microcontroller, and it has its own PLL IC, so it has its own phase lock loop. And so when that's working and in lock, it provides a stable reference frequency to the PLL IC, which lives under this can here, where these three separate VCOs live. And ultimately what that means is that a couple of things really that might be going on. We know that this oscillator from previous tests was proved that it wasn't oscillating, it wasn't staying in lock. So thus the reference frequency provided to this PLL for all these three VCOs wouldn't be correct, and as we observed earlier with the output frequency on the RF connector from this VCO and also from this reference VCO, the frequency wasn't correct even when it was said to be in lock. Because this has moved off frequency, allegedly, has made this PLL go out of lock, or move in frequency so much that then it would go out of lock. And we've been fortunate earlier to be able to capture a frequency on the radio test set that didn't match the frequency on the front of the radio. So what that means is that it looks like this PLL for the reference VCO has wandered off frequency. And ultimately, when it gets too far off frequency, then it will become beyond the capture range of this PLL IC and this phase lock loop for these VCOs to remain stably locked, and thus it would then go off frequency. And just like this particular TCXO module that's used there as a reference oscillator for the other PLL circuit, if that was to wander off frequency, then these VCOs would also wander with it to such a point where the VCOs can no longer remain in lock and they'll go out of lock. So there's a capture range, obviously, as it wanders about, and so it's important that these remain on frequency. So in essence, in this radio, we actually have two hearts in this radio. We have the first heart of a radio, which is this TCXO, which provides a stable frequency to the PLLs elsewhere that's used on other VCOs. But in addition to that, on the HF side, we have a reference VCO, which doesn't use this. It just has its own VCO, which generates its own reference frequency, which can be changed depending on what we obviously program the radio with. And so therefore the frequency coming out of this to this PLL IC for these three VCOs, the reference comes from this, not that. So now we've dug a little deeper. It explains why these VCOs keep going out of lock, because the reference isn't there, or it's not the correct frequency, as we observed earlier with the tests. So we now move to HF LO2 VCO, which is this module here, which lives there. And this module is for the sub band. So when we've got the second frequency readout on the radio, this module generates the sub frequency bands. So therefore I believe this to be working. This isn't going out of lock or showing any signs of problems, but I just thought I'd remove it just to check the underside, and we've soldered and cleaned and, you know, and got rid of all the flux residue. But a close inspection of this circuit board and all the pins on the PLL ICs as well. So we haven't got any major size like we had with the other VCOs that were removed earlier in the video, of solder slivers and blobs and nasty things that are contaminating the board. So as we move on now with our knowledge, what I've done, each one of these VCOs uses the same transistor, which is this transistor, a 2SK508. Now there's the designation within the service manual says that they're called K2, so it'd be a 2SK508 K2 designation, and that means a lot because we've ordered some replacement parts which have come, and I have them here, and obviously they're only small, so they're inside this bag. I've ordered a couple of them, two 2SK508s, and the reason why I've ordered two, just for starters, because it's not terribly expensive, is so that I can replace the transistors that belong in the HF LO2 oscillator, which mixes with the signal from HF LO1 to then produce the HF carrier and other carriers on other frequencies as well. As we've seen in the block diagram, these VCOs are very important to the making up of other frequency bands as well. So it's important that these two VCOs and that reference VCO all run perfectly. So we know that when this oscillator is running, which it was earlier, albeit on the wrong frequency, it is stable on that frequency, even though it's an incorrect frequency, and its output level is maintained at the level that it should be. So I don't suspect the transistors for the VCO in there to be faulty. However, we did have problems with this VCO, and this is HF rest VCO, and this uses the 2SK508, and so does this, the HFLO2. That uses a 2SK508 transistor. Now, what I've done, I've been very careful to select the K2 because the K52 rather, the K52 designation on the end of a transistor, so 2SK508 K52 as it shows in the circuit diagram, is because of its capacitance, and so we have different capacitances and current rating depending on whether it's K51, K52, K53, etc. So it's quite important that we maintain that designation. So as per the service manual, I've ordered what would be the correct designation of transistor, which is the 2SK508 K52. So what I intend to do is I intend to put those two transistors that we've got into both these modules. HFLO2 and also the reference VCO. And I'm going to reassemble it all now and replace those two transistors, and then we're going to do testing to see whether it's sorted the issue out, because we've gone through everything else. Now there is one other option should that fail and I replace those two transistors, and that is that the data on the data bus that's coming to these ICs, these PLL ICs that live under the VCOs, the data bus is shared across all the PLL ICs. So the microcontroller will be the next port of call if the transistors fail to get the oscillators working, because we've then done as much as we can. We've gone as far as we can. We've explored as far as we can. We've gone in depth by removing the modules, doing testing, checking the solder connections, inspecting components carefully. We've then pinned it down to, obviously in this case, if you remember earlier, remove a varactor diode. We lifted it at one end to prove that its capacitance was working, and again the frequency shifted enormously when the VCO was running out of lock. We were still getting an output, but the varactor changed its frequency enormously as we connected or disconnected it. So we disproved the varactor, and then the only thing left really was the oscillator transistors. So that's where we're at now. So following this part of the video, we're going to re-establish all the boards back in the radio with all the modules back, replace the two transistors in both the reference VCO and the LO2 just for caution. And then what we're going to do, we're going to test. If we find it doesn't work after that, then we're going to have to look at the phase lock loop data lines which come from the microcontroller. And if you remember, the microcontroller at the front of the radio down here did have signs of corrosion on the connectors. If you remember earlier in the video, all gone green and corroded. So maybe when we remove the board and we look underneath, we might find other signs of corrosion. So that's something that we may have to look at. Because it could be that the data going to the phase lock loop is corrupt, and thus if the data get into these PLL ICs that live under the VCOs isn't correct in terms of data words and corruption of data on the serial bus, then basically if it's not losing its serial clock, the serial data line's going a bit skew with, or there's some issue with the data line not being the correct amplitude and it can't then program the PLL ICs, then ultimately what will happen is it'll not have the right data to lock the VCO, and thus no matter what you do with the VCOs you'll never get them to lock. So there's two options here. We're going to replace the first option, which is replace the transistors. The second option is to then examine the data that's going to the PLL ICs from the controller board if that fails to work. So it's a two-pronged approach is this one, and then from there really we're on, we have to make a decision one way or the other. Do we continue looking at the radio to try and find what could be a bottomless pit problem, or do we just write it off and pack it in, or do we get the thumbs up and everything works wonderful and the VCOs run and everything's back to how it should be, because technically it was some problems with the transistors? Who knows? Answers on a postcard. This is why, we're in uncharted territory really. We're going from one extreme to another. But we are backing ourselves into little corners, and then we're finding more information out about how it works, and then delving in deeper and deeper and deeper to component level, and then changing components and looking more in depth as we're doing here. So ultimately that may pay dividends later on, and it's quite a fruitful approach to look at this problem. So back soon after I replaced both of these transistors, reassembled the whole system back in the radio, and then let's do some more testing as per the alignments and see whether we can get these VCOs to run properly. Okay, well we've removed, this is LO2, we've removed the little transistor already, the oscillating transistor. I just got the new one to put in. I'm just going to see if we can get this out of its packet. I just want one to come out. There we are, like a little flea. So that's the old one. Just move that to there, then we'll just pick that up and put that in. So just stabilise it. Right, just get my soldering iron and let's see if we can solder it in good proportions. So just solder one leg on first. Let's see if we can manoeuvre this. The lug there gets in the way, this metal lug, so it's just a case of just trying your best, really, just to try and get it motivated. Get the damn thing on. So let's just see if we can just grab hold of it. Right. It looks easier than it actually is because of the way the transistor's orientated. You can't quite get onto it, and it's moving round where I don't want it to. I want it to play ball. Now it's turned upside down, so I'm going to have to manipulate it a bit more, perhaps move my magnifier a bit closer, because it's quite small, as you can appreciate. Right, so what I'd like to do is I'd just like to get it lined up. If I can stop it from flicking about, even though we've got some flux there. Right, I've got hold of it now, so it should that's it. And then just got to bend it round a bit, move it a bit more. That's it. So we've got the transistor in, and we just apply a bit more flux onto it, and then Bob's your uncle. Seeing if I can get a bit more light into it for you, but I know this camera's not very good at picking up some of the light sometimes. It might be a bit better. Okay, so we'll just put a bit more flux onto it, and there we go. And then just try and touch that down. That's it. There. Right, that's in. So I'll have a look at that under the magnifier now for a closer inspection, and then take it from there. Okay, so this is the finished article. It's all soldered in, as it should be. So that's the new transistor, and so that's good to go now. We can put that back inside the radio PCB. Right, it's all present and correct. All back in, screening cam, everything's, all the modules are back in, and we've done all the solder connections on the VCOs again, and all the earth points and everything for the VCO casing and everything's all back as it should be, cleaned up, ready to be put back in. Okay, so the other bit of final due diligence I want to do before we put this back in the radio is, if you remember, that's the reference VCO. This was the VCO that had the plastic underneath it, this one in this corner. So I just want to talk about this one. This VCO here is the known Kenwood problem, where a little 8-volt rail, which I'm about to show you, gets touched by the can on the VCO. So basically, when we look at the profile on this, you can see just right on the corner there's like a little standoff, a part of the can. So basically, this corner bit here is slightly proud of this side. As you can see, it's a bit longer where my fingernail is, that bit there. And what happens is when we look here on the PCB where the VCO goes in, you can just see there's a tiny little island, and it's just above the hole where the leg for the VCO would go. So I just point to it with a screwdriver. It's that tiny little island just there, look. I'm just touching there, that little eyelet. Now what happens is when we put that in, this bit of the VCO there, that standoff bit here, that's just on the very edge, this thing here, when that lug here goes into this hole, this flange part, it is chamfered up a little bit there, but it does actually on some of them touch that little eyelet, which carries 8 volts, and it shorts things out. So I'm just going to put some heat proof Captain tape on there, and then we're going to remove this plastic thing which was on it originally. But I just wanted to look at that because obviously you know, that was on there, fastened onto this sort of plastic lug, and then it went down to protect it. But it's a bit, you know, sort of how you're doing is that let's do a proper job and just put a little piece of tape in that corner there, so when the VCO goes back together and that goes on there, what was happening is that bottom corner there, you might just be able to see it, but that little corner, you see, lines up with that little island just there, you see. So I might be able to get a bit more light in there just to try and show that in a bit better. You can just see that little copper island just there. And of course when they were assembling them, it went like that, and then the metal can ultimately touched that little island. So let's just back it off again. You can just see it there. Now you see it, now you don't. Now you see it, now you don't. So that's what they were saying were causing these problems. So all we need to do is just put a little bit of tape there, just to protect it, and then reassemble it back. And providing we don't, you know, stand on it to try and, you know, push it against the board and solder it, it shouldn't be a problem. There aren't any other places where it can touch the board, obviously, unless it's near these lugs. So ultimately anything, any tracks or whatever that go underneath it or near those lugs potentially could get touched by it. But as you can see, they've done some work to prevent the tracks on the PCB from getting shorted when the module's pushed in. So that's that. So I wanted to do that. It was worth doing because ultimately this VCO has been removed by somebody else before me, and this modification carried out where all this plastic stuff's been added.
Kilo Oscar 6 Foxtrot Papa Lima on 30 Charlie.
So that issue would prevail if it touched any of the tracks or islands, but as we can see, there's not much else it can touch apart from in that corner. Now we do have something there which I'm going to look at a little bit further under the magnifier, that little island there. I just want to have a look at that because it does look a little bit corroded to me, does that? But I'm just going to observe that because ultimately that, I think, is one of the data lines which comes into the phase lock loop IC. So I've got a theory that's one of the serial clock serial data lines that are coming in. So I just want to double check that just to make sure. But obviously when that's sat there and that little lug's in like that, it's not going to touch that anyway. But I just want to have a look at that because on camera, to me, that does look to have a little bit of tarnishing. So I'll have a look at that in more detail in the magnifying glass. But at least you know now what the cause of the problem is. with that corner touching the PCB. Okay, so here we go again into the abyss. This one is the VCO that we've just done with the tape on the outside edge there. So the next job is to replace that 2SK508 K52 transistor that lay in here in this part of the VCO. So we'll just have a look at doing that. Just put a bit of flux on it and see if we can get it off the board. I'm not going to use hot air or anything on this because we'll just blow everything off the board around it because it's in such a confined space. So all we need on this is everybody to cross the fingers and toes, and hopefully it'll come off. Now I'm just going to do it the brutal way. I'm just going to lift it at one end, and then once it's lifted up, just run solder then on both connections then to remove it. So we've got it off, and then just put a bit more flux on it, and hopefully we can get the new one on easily without too much trouble. So right, so the next process is just about obviously getting the this one off. Now we've got to be careful it doesn't go boing and end up in the carpet here in the workshop and fly off somewhere. So we've just got to be really careful because these have got a habit of just flying off and ultimately getting into places we don't want them to get into. So I'm just going to drop that in there again. Bad positioning because of the lug, so I've just got to turn it round now, see if I can reposition that device where we want it to be. It's turned upside down, so we'll just flip it over and then drop it back on the board. It's not going too well, this, is it? That's the thing with these surface mount things, they can be a real pain. They have a habit of doing their own particular manoeuvres, and of course normally it would be a very easy process just to, you know, just to get onto it, but we've got this lug here, you see, which goes right over the top of the transistor we're wanting to get to. So it's not good, I'm afraid. And I'm looking at it from about 2 feet away, a feet, 1 foot, something like that. So I'm normally a lot closer. And that also has its challenges, obviously. Okay, so that's soldered back into a location where it should be. So we'll just have a close up on that if we can, and go right in onto that transistor there. So we're all nicely soldered in, and just see if I can get some more light in there so we can see what kind of work's being done. But as you can see there, yeah, we're okay. We're good to go. That transistor's in nicely. So that's the reference VCO done. So we've replaced the transistor in the reference VCO now, and we've obviously put some tape, reseated that. We've done the other board as well with the VCOs there. Everything's all nicely done. So ready to put everything back, and the moment of truth. Fingers crossed. Right, we're all back together now. All the connectors, plugs and screws and boards are all in place, so that's fantastic. We power the radio on. We're back to doing the alignment checks. As we can see earlier, there was different frequencies and measuring on certain test points to obtain different voltages that we checked. And as we could see in the table that I did earlier, there's widely big discrepancy there, so obviously we want to check these voltages again, and then if necessary tune these little tuning capacitors that are inside the VCOs to obtain the correct lot voltage. So what we've done, we've first tested to set up 2 megahertz FM, and then check on test point 501, which is the reference VCO, the HF reference VCO. This is a VCO where we replaced the transistor, and we're obtaining apparently 1.5 volts there, plus or minus 0.5 volts. So if we just whiz the radio around so we can see the front of the radio, I've set up the frequencies. It says there 2 megahertz on FM, which it is, so we've got that reading there on the radio, and we're just going to try and obtain 2 volts now on the TP501, which that's the HF reference VCO there, and TP501's right down in the middle there. So we've got the voltmeter as well in the picture, all being well, and we've got that frequency set up. So we are actually looking for, you know, 1.5 volts or thereabouts. Let's see if I can get on. It's difficult for me to see at this stage because I'm quite a way off. So it's 1.57 volts without any tuning up whatsoever. Now previously, according to that's good news is that, by the way, but previously it was 2.19 volts there. So that's bang on what it said it should be. Now we've got to change the frequency now to 12.990 megahertz, and observe that same test point, and we should get 4.6 volt or less, and we've got to observe that. So let's put the frequency now at 12.990 megahertz. Okay, so at 12.990 megahertz it says that it's got to be less than 4.6 volts. So it should be around the voltage that we had earlier, around about 1.5 volts, and it is. So that's at 12.990 megahertz, which we've got there, so that's good. And if we just look at the front of the radio just to check that everything's still in lock, and as you can see there, it's still in lock, so that's good, no dashes, which is good. So we'll move on to the next measurement now, which according to this is moving on to 30 kilohertz. This time we're measuring TP502, so that's the HF1 or the HF main PLL. So we're basically checking what is the 3 VCOs, because when we look at the diagram here, this is what we've just checked. This is like VCO 1, 2, 3, and if you remember, we had the 3 alignment holes, if you remember, on this. This is the main HF VCO. So let's check those now and see what we get. Right, so off camera I've gone through the alignment diagram, and I've gone through all the alignments and test points, etc. And basically I've managed to find out that the 2 VCOs that we replaced the transistors on, which were the HF reference VCO and the HF LO2 VCO, their voltages are superb. They're bang on as per the manual textbook, no problem. Now what I've done off camera is I've then started to go through the alignment procedure for the rest of the VCOs. I'm starting with HF LO1 VCO, which comprises of 3 separate VCOs which covers sort of 3 parts of the HF band, the HF frequency band between 0 to 60 megahertz. So basically what I've done, I started to measure the output of this, and I started to get weird things. The voltage I could not get to where the manual said it should be. Even when tuning the capacitors under these holes here, you just couldn't get it. Now, although I'm not getting any out of lock condition, and I haven't seen that on the display since I've reassembled this radio, so that's good news. I'm not getting any dashes. What I was noticing is the frequency readout on here. When I transmitted on the radio on a given frequency, like at the moment I've got it tuned the radio to 29.0 110 megahertz. It's off frequencies, you can see there. Now I couldn't get the tuning voltage to be where it should be. Now what happens is you just try and tune the capacitors. The voltages are quite high, but then you can suddenly get it to go onto frequency. And so ultimately what happens is as you try and tune the capacitor, it does have an effect, and it's right on the edge of the VCO lock or capture range. So basically the PLL lock line is still in lock, but it's not quite there. It's sort of a bit noisy, and occasionally on transmit I hear some noise on this radio, and you can see that on the spectrum analyzer when I look at that. Now it looks to me like as if what's happening is these VCOs are just right on the edge of a lock, and when you mess about with the tuning capacitor you can get the radio to transmit bang on frequency correctly at that particular frequency, but when you change the frequency and try again, the lock voltage is still way high and the tuning's then affected, and you have to then retune the capacitor. So that's exhibiting the same problem that we had with the HF reference VCO and the LO2 VCO that we were looking at earlier. So what I've done, I made a decision that rather than mess about, I'm going to replace all the transistors in all of the remaining VCOs that we haven't replaced. So basically 3 transistors in there, 4, 5, 6, and I think there's 2 in the sub VCO, which is 7, 8. So I think I need about 8 transistors. Now according to the circuit diagram, the VHF VCO, the UHF VCO, all the other VCOs all use this 2SK508 MVK52, so there aren't different part numbers for different VCOs. So I'm going to blanket change them because I've proved that by changing 2 transistors on the other 2 VCOs has brought those spot on to the correct voltages that are indicated in the manual, and they weren't that before, they were way off. So that proves to me that there's some issue around these transistors, and so what I'm going to do is I'm going to just blanket change them, and then we're going to go from there. Now at the moment the radio hasn't shown any dashes or any out of lock condition whatsoever, so it's that's a marked improvement on before. But there is a VHF reference VCO as well, which is this VCO. Just like there's a HF reference VCO, there's a VHF reference VCO, and ultimately no doubt there'll be a UHF, well this is a UHF VCO there that has the same transistor, but there'll probably be no doubt a UHF reference VCO as well. So there's a HF reference VCO, a UHF reference VCO, and then ultimately there's a VHF VCO, UHF VCO. So I think the best thing to do is just change the transistors so we know we're starting from a clean slate now that we've proved the other 2 VCOs are working. Now these are the 3 VCOs that live under that can with the 3 holes in, and ultimately when I tune these trimmer caps I can't get the lock voltage which is on that test point 502 there, which is on this lock line. So no matter which frequency I select, because each one of these VCOs is responsible for a certain frequency range. One's responsible for the lower part of the HF frequency range from like 30 kilohertz to something like 10 megahertz or something, and then we've got another sort of 10 megs done by the next VCO, and another 10 megahertz up to about 30-40 megahertz that's dealt with by the other. So they're switched on as we looked at earlier, so as you move the frequency about. So because we've now got the HF reference VCO working, which we were having problems with earlier, and that ultimately then had an issue where it wasn't providing the right reference frequency. So this HF reference VCO, we replaced that transistor, now that's working. We're not seeing the out of lock condition now, we're just seeing a bit of instability, because the VCO lock voltage is right on the edge, you know, just about to fall off into an out of lock condition on these 3 VCOs. So we're not quite out of lock, but we're not sort of at the optimum in lock either. So yeah, I'm going to change these, so next time we come back I'll have got the transistors and we'll be installing them. Okay, so while we wait for the transistors to arrive in the post, I just thought we'd look into another issue that we've got on this radio, which is, if you remember earlier in the video, we sort of proved that the receiver worked on both VHF and UHF on the 140 to sort of 150 megahertz range, on the 430 to 440 megahertz range. Receiver seemed to work, so we're just going to verify that again. However, we didn't have any transmit at all on either VHF or UHF. There was nothing there. So we can have a look at that in the diagram and learn a little bit more about how that works. But first of all, let's just do a quick test. So I've got the SIGGEN connected into the VHF port down there. We've got the radio set up to 150 megahertz on receiver test. So we've got the external speaker connected as well. So if I turn the RF gen on, we've got receive signal, and the RF level is well within spec, and sensitivity is good. And you're looking at 0.1 microvolt for the mute finally closes. So there's nothing wrong with that. So that's okay. Right, so what I'm going to do now is I'm going to change the band on the radio to 431 megahertz, which I think is there now. And we'll just change the RF gen frequency to 431 megahertz. We will then move the connector to UHF connector, which is this type N, and then go back, turn the RF gen on, and there we are, UHF. So that's receiving. Again, very good sensitivity. Nothing wrong with that. So we proved there that both VHF and UHF receive work fine. So the VCO for providing the receiver local oscillator injection for both UHF and VHF has got to be working, otherwise we wouldn't be receiving. However, if I go to transmit, so we're still on receive, if I select transmit now, and I'll just turn the spectrum analyzer off, and then I'll just leave it to auto tune the test set. Now if I key up, which I'm doing now on UHF, I'm seeing on the current meter a couple hundred milliamps higher current taker when I press the transmit button down, but as we can see there's no TX frequency and there's nothing appearing on the spectrum analyzer here. And if I open up the spectrum analyzer to a wider bandwidth, and let's say for example we put it on a few hundred megahertz, or around about 50 megahertz bandwidth, so that's like 100 megahertz per division, so that's basically the whole of the RS spectrum. If I unkey, we are getting something. So this here is the start frequency, if you like, of a radio test set. So I can introduce marker 1, which I've got there, and marker 1, as we can see there, with the frequency in the top middle is at 0 megahertz, and ultimately we've now got it 248 megahertz. So if I key the transmitter and then we go along here, we're getting a transmission frequency of around about 424 megahertz, 426. So if I just split that off a bit and go TX frequency 426, so just narrow the bandwidth down on there, so we've got something there at 426 megahertz. And so let's go to center that frequency. Let's have a look, and let's alter the marker again to get higher frequency accuracy. So again, this is on 425 megahertz, 425.4. Let's just widen it in again. Let's just narrow it down a bit more, and we can see the spectral shape's not exactly good, but anyway, so let's go TX frequency and let's just get that to center frequency if we can, so we see it's right center of a display. And we can see there that, of course, if I move a marker again, we're not actually getting at the peak the frequency we want. We are actually transmitting, or should be transmitting, on 431 megahertz. So again, it's, you know, it's not good. And now we're 5. So I think it's picking up my voice as well. Now we're there. It's a bit dithering about as well, as we can see, but the frequency accuracy is way off. So if I just adjust that to the top there, 425 megahertz, and as you can see, it's dithering as well, it's dithering. So then it'll come back in a minute, I think. As you can see with that marker, it's jumping up and down, but it's moving frequency all the time. It's not staying accurate. And its level as well is very, very low. It's not transmitting at any significant power level there at all. I mean, you're talking, you know, 1 milliwatt, thereabout, 0 dBm is the RF output from the TXPA. So it would appear that I think the RF level coming into the UHF power amplifier is way too low for it to amplify properly anyway. And as well as that, the mixing of the frequencies must not be occurring properly as well, which is one of the reasons why I'm waiting for those transistors for the VCO. But I thought it'd be interesting to take a look at that anyway. Now if I unkey the transmitter, and then we sort of repeat this test again but on VHF. So if we just move the antenna connector now from the UHF connector to the VHF, and we select the the VHF band on the radio, so I'll press that down. Now then, if I go to queue up the radio now, and we are actually getting a lot more current, between 2 to 6 amps being drawn. So on receive we get the quiescent current of 2 amps, but now we're getting 6 amps on transmit. And if I go to what is the transmitter frequency, 150 megahertz, we seem to be getting something. That when I unkey the transmitter, then the squelch on the test set breaks. So let's just increase the spectrum analyzer and see what we're getting. So there's something there, whatever it is, it's wide banded, so I've unkeyed, just keep going. So there's something there. Now then, so just expand on that a second. This looks like again another mixing problem, because if I put marker 1 on, now just for visuality, if I unkey the transmitter like now in receive mode, you can see there's nothing there, there's no amplitude. Key the transmitter up, we're getting something. Now if I go to marker 1, which I'm on now, and we look at the frequency where this noise all starts from, it's round about there, 114 megahertz. However, the frequency we should be transmitting is 150 megahertz, which is about here. And if I can just get it, so that's the frequency we should be transmitting on, which is dead center of the screen, that vertical line. However, as you can see, we're actually getting something. There's a little bit of a peak again, although it's low level. So we're looking at 161 megahertz, roughly 0.6, right the way down to 114 megahertz bandwidth. So that just shows you that that entire chunk of radio spectrum is just RF noise in this case that's coming out this radio. So if I unkey the transmitter, again that proves that the radio itself is not mixing properly. Now most radio equipment like PMI, LMR, aircraft radio equipment, marine, general business PMR type business radio use, there'd normally be one VCO in the radio that would say, if it's a VHF radio operating between 136 to 174 megahertz, one VCO would do both the transmit and the receive. So in other words, the VCO would operate at the fundamental frequency minus the IF. So, you know, if it was a 10.7 megahertz IF, for example, on the receiver, the VCO would either generate high side, in other words, high side above 10.7 megahertz higher than the frequency wanting to receive, or low side 10.7 megahertz below the frequency wanting to receive. Either way, both would produce an IF, no matter whether it's high side or low side injection into the received local oscillators mixer. And it would then, obviously the difference between the VCO and the incoming frequency mixed together would produce an IF of the frequency we're wanting to receive. So when we then flick to transmit, then the VCO will produce a transmit frequency as a fundamental. So the output of the VCO will be at the frequency we're wanting to transmit at, and then it would just be buffered up through an exciter for amplification, and then through a final PA output before going off to the antenna. And obviously when we switch between transmit and receive by keying up the microphone or unkeying when we're wanting to receive, the synthesiser and VCO and the PLL and the prescales would all be programmed with different data. Every time we went to transmit and receive, be different data words written, and thus then it would tune to different frequencies instantaneously as we went from transmit to receive. Now on a duplex radio, obviously where it transmits and receives at the same time, you'd have two VCOs, one for transmit, one for receive, because it needs to do both at the same time simultaneously, so that goes without saying. But however, on this radio it operates completely different, as we'll have a look next on the block diagram. But basically this radio works through mixing signals for the transmitter. So at no point do any of the VCOs on this board or the other one produce a transmit frequency in terms of fundamental. It doesn't produce the frequency in which we wanted to transmit at from any of these VCOs. Instead, as we'll see shortly, it uses two or more VCOs to mix together in mixers to then produce an output frequency, which is what we want to transmit on as a fundamental. So that's how this radio works through all the frequency bands, with its HF, VHF, UHF, all the same. And that's where things can get complicated, because you only need one VCO to be off and the other one could be working perfectly okay, but it needs both of them to be working perfectly for the mixer to produce the right output frequency, and thus obviously get the amplifiers to amplify that frequency and ultimately pass that out to the antenna. So what we'll look at next is a diagram which will explain more of how this sort of works. Okay, so our transmission starts live here. We get audio coming in from the microphone amplifier circuit. It's coming in this way and it hits a mode switch. Now that mode switch can select different modes of transmission, being FM for frequency modulation, or it can be SSB as in LSB and USB, CW, AM and FSK modes. So depending on what mode we select depends on these switches and how they're arranged. But either way, for example, if we're doing an AM, for example, we have what's called a TCAR, transmit carrier oscillator, and that oscillator then produces a 10.595 megahertz frequency, which gets mixed in this mixer with the audio signal coming in from the right. Now obviously, because it's AM, it's amplitude modulated, then ultimately the signal leaving here will be amplitude modulated, and likewise for SSB modes, lower sideband, upper sideband, the frequency of this oscillator will be shifted slightly to produce the lower sideband and upper sideband, and that would ultimately then mix with the audio signal to then produce what will be a sideband modulated signal coming out the mixer at 10.595 megahertz. So likewise, if we look at the FM side, we've got the audio signal coming in there into what would be the FM modulator. Now the audio signal coming in would modulate the varactor diode within the VCO, and that then, this modulator VCO, yet again, also produces a 10.595 megahertz if we're on FM. And the frequency modulation of the VCO, the deviation of the VCO would then be outputted on this left side at 10.595 megahertz. So basically the audio will modulate this VCO, and then we have a frequency modulated output at 10.595 megahertz. We've got diodes again, which pin diodes, which switch on or off the relevant path from these two modulators. Ultimately, so the FM modulation will go through again an attenuator. We've got an ALC for the AM SSB modes as well, and other gain controls to prevent over modding and other clever things that are going on in just this little area here to prevent over modulation, pre-emphasis, de-emphasis, AGC, etc. This then comes out of this buffer amp and comes this way, also branches south, which we'll look at in a moment. But as we saw earlier, again we hit a mixer. Now LO2 VCO is the one that replaced the transistor in. That produces a frequency which mixes with the 10.595, and the difference then mixed output, the IF if you like, from that first mixer lays in this frequency range. So we have a tunable bandpass filter with a reactor diode, which is tuned from the microcontroller to only allow these frequencies to come through this filter, which then hits this second mixer. Again, we've got the good old HFLO1 VCO. If you remember, this one had 3 separate VCOs within it, which produced 3 different frequency bandwidths to cover the whole HF spectrum from basically 1.8 up to 54 megs on transmit, for example. That again mixes with the incoming signal that we've got from the first mixer, and then the fundamental frequency for transmit on the HF band from 1.8 to 54 megs is outputted from the mixer number 2. Now these filters here are bidirectional filters, which means they can be used in receive mode as well as in transmit, and they're controlled by pin diode switches. As we can see, all these pin diodes that are all over the place, they all basically route the signals depending on whether they're transmitting or receiving, and so therefore TX signals can make it through the appropriate filter depending on what frequency band we select, and then output from that come this way, gets buffered on transmit. Obviously this is a buffer for the TX signal, comes along here again with another diode switch there, and it comes down and it hits this power amplifier. Now this is on the other side of the radio that we're looking at the beginning of the video, where we had the dual power amplifier transistors and all the transformers and everything else. That's all in this area, and the final output power amplifier then for HF is this amplifier, which are two 2SC5125 FET transistors that allow then the RF 100 watts up to RF power to come this way. Again, we've got more filtering and ATU circuits here that the TX signal passes through, and again these are switched in depending on what frequency band we're on, and then we've got a detector for VSWR and such things, and then it hits the TX relay, and then ultimately it goes out to the antenna, and we've got different antenna selections we can have. So that's a HF path. And as we can see as well, these oscillators not only produce the signals for the transmit mixers, which are these 2 mixers, but they also produce a signal for the receiver. So basically the received signal that's coming in from the antennas, be it antenna 1, antenna 2, or the received separate antenna for all these switches, ultimately they end up in an attenuate on receive mode. The received signal gets filtered again, depending on what band we select. Again, they'll pass through the relevant bandpass filters and ultimately come in to what would be the receive front end amplifier, what's known as the preamp. Hit the first mixer, and of course HFLO1, our good old oscillator with the 3 VCOs in it, again will mix with the incoming RF signal, and obviously the output of that mixer will be an IF, which will then go through to bandpass filters, ultimately buffered again through an AGC control amplifier for modes like AM, SSB, so the gain can be controlled there, and then into what is the second mixer. And again, our good old HFLO2, the one we replaced the transistor in initially, that will also produce a signal into there, and so the second IF frequency is outputted here, and ultimately then we have a noise blanker for different modes of reception, an AGC amplifier, and then we've obviously got different filters, and then we've got what would be a third mixer, where again we've got a local oscillator which operates at 11.150 megahertz, which is called LO3, and that produces a third mixer frequency in here, and the output then is what is a 455 kilohertz IF. So if you like, we've got it's a triple super heterodyne receiver, and so therefore then the 455 kilohertz signals filtered again by selectable filters for different bandwidths of 15, 9 and 2.7 kilohertz respectively. That then comes in to what is the discriminator, the demodulator, and ultimately we've got an FM, RSSI for signal strength, etc. Likewise as well, we've got another path this way, again via another IF filter, another mixer for T-car, the transmit carrier, or what would be a carrier representation oscillator coming in, and that ultimately then will be detected and sent out as in AF, obviously for AM modes, and obviously SSB modes, etc. We've obviously got signals that come down here this way, and therefore we've basically got DSPs as well for audio and everything. So that's the receiver side. Now if we come right the way back again to where we were, and we've obviously got where the transmit signal starts, okay, we've dealt with the HF transmit side and receive side already, but we'll notice as the transmit carrier, whether it's FM, AM, SSB, it's all on 10.595 megahertz, all gets fed through here, and then we hit this point where it branched south, because we discussed the point there, all this area to the left, but we didn't discuss what happens when the signal goes south. So this signal, this 10.595 megahertz signal, gets split off and comes this way as well. It comes down as per this arrow all the way down here, and if I don't lose it, it comes all the way along and it hits this mixer. So as we can see here, we've got the 10.595 megahertz signal. Now then, what happens is there's another diode switch there, and it essentially allows that 10.595 megahertz signal to come down to here and ultimately then mixes here. So there's quite a bit going on, and I'll explain what happens there. But what we've got down here for VHF and UHF is we've got a transmit VCO, and we've got what would be a receive VCO. Now for the transmit VCO, the 10.595 megahertz or 10.695, whatever it is, comes into here. It gets mixed, okay, and we've got LO3, which is a 31.2 megahertz signal, mixes with the 10.695, and then again it's mixed here with the TX local oscillator 1 frequency, and the product of these three frequencies, the 31.2 megahertz, the 10.695, and whatever the frequency of this local oscillator will be, this VCO, which moves depending on what frequency we want the transmit and receive to, or the transmit to work on. This ultimately then produces an output then for the fundamental frequency. And so we've got two paths, two switches. We've got a UHF switch and a VHF switch. So ultimately, if it's VHF frequencies that we're generating, they come up here, get filtered, buffered, again passed out, and it can at this point branch two ways. So if it's VHF, it needs to go upwards. If it's UHF, it goes downwards. Same here, we've got a UHF amplifier, so when we're operating on UHF, the VHF diode gets switched off, the UHF gets switched on, and ultimately it gets buffered up and filtered and comes out, buffered again, and the VHF switch going north is switched off, and the UHF switch going south is switched on. So ultimately that's UHF signal gets passed into the PA board, to the TX relay switch if you like, and then out to the antenna. The VHF signal, ultimately for transmit, comes out this way, goes up here, and then comes into what is the same driver circuitry the HF shares with it, but there's a little relay which flicks over and connects what will be the VHF high band signal to the final amplifier, the final PAs, which again are two transistors which work together to produce an output, and ultimately then off through a bandpass filter to the transmit antenna for the 144 megahertz band. So we know that the receive VCO must be working, because obviously we're receiving both VHF and UHF, and this VCO is responsible for that. And so we've got two paths. We've got essentially a UHF antenna input and a VHF antenna input coming in for the receiver, a preamplifier, and then ultimately then more IF amplification, and then a mixer. Basically this is a mixer. We've got local oscillator coming in, so we get the first IF, and then we've got another mixer which is this LO3 LO31, which produces this 31.2, mixes again to produce what will be the second IF coming out, and that ultimately goes off then for audio processing. Now we've also got, if we look right down here, we've got what is a tap coming off here going this way, and we've another tap coming off here coming this way, and these are the receiver RF inputs from the front end, if you like, the receiver input from the antenna for VHF and UHF respectively, and they're fed along outside through again more bandpass filtering and buffering, and then they're mixed again, and then there's what is the sub-band oscillator, the SL01, which lives on that separate board, and that is again another VCO assembly with two VCOs in it, one that produces VHF frequency, one that produces UHF, and ultimately this oscillator here, this VCO, again changes its frequency depending on what frequency you want to receive. Again, diode switches to switch on the appropriate oscillator. This then gets mixed in the first mixer to produce an IF of this frequency, pass through a filter, AGC amplified and controlled, and then it goes into what was the receiver detector. So this is a multi-mode receiver detector. So ultimately then we've got the different RSSI outputs, a signal meter, the squelch detect, what will be the Schmidt trigger for the squelch circuitry, and also then we've got different audio AF switches for the detector for AM detector or the FM output discriminator, audio output. So that is the sub-band, that's the second receiver, that secondary display that we get on the front of the radio when we select the sub-band. This is an independent receiver to this receiver here, which is a VHF UHF receiver in this top section here. And this is the main receiver, if you like, for VHF and UHF. So the transmit signal, this TX, must be faulty. There's got to be a fault round here somewhere, either in the transmit VCO TX LO1 is not oscillating at the right frequency. It could also be the LO31, this 31.2 MHz signal isn't there. It could also be the 10.695 MHz signal that's coming in from the FM modulator, or the AM or SSB modulator isn't present, and thus that can't mix. And so any one of these three signals, either the 10.695, the TXLO1, or indeed this oscillator here, LO31, any of those three don't work properly, we're not going to get the right frequency output going for either VHF or UHF. And I suspect we've got something going on round here. So let's have a look further at where these are and where they're physically located, so we can have a look at that. So that's the 1.2 gigahertz optional thing that can be added. Again, that taps in. Obviously we've gone through the HF receive side, so we need to find the location of these two mixers, if you like, and these oscillators, and see whether they're doing. So we need to check that 10.695's there, we need to check that TXLO1, which is probably one of those VCOs that we need the transistor for, and also LO31, that 31.2 megs. Is that working? Let's just check those and have a look and see what we can ascertain. Dig deeper into this area, which will explain why we can't transmit on VHF or UHF. Okay, so I put my thinking cap on a little here, and if we just use logic for a moment. Now, as we described earlier and we saw in the video, that we know the receive section for both VHF and UHF, which is here, the mixer section, works because obviously we're receiving both VHF and UHF perfectly well, so we know that the RXLO1's working. Therefore LO31 here must be running, because if it wasn't we wouldn't get the second mixer working on the receiver. So as we can see, it's also buffered off for the transmit as well. So this must be running, so otherwise we wouldn't get a receive. But as well as that, we were asking the question, as we saw in this video, whether this 10.695 megahertz signal's actually there. And I think it must be, because when we look at the FM and obviously the modulator circuit here for SSB, for AM, FM, LSB, USB, CW modes, that must be running, because we were getting transmit on HF bands. So we'd already seen that since we replaced the transistor in LO2 and the HF reference VCO, that we were suddenly now getting a transmit signal. So I would surmise that this oscillator must be running. In other words, that must be there, otherwise we wouldn't be getting this mixer signal coming out. So I'm now narrowing it down even further, because we know this oscillator must be working. We know the signal coming in here, this 10.695 megahertz, must be there. I think this TXL01 is going to be the issue. I think that's not running, and there's a problem with it. What I've also noticed as well, I'm not sure if I commented about this earlier in the video, but that says 10.695 megahertz there. If I just zoom in, just so I'm not looking at my eyes being the cause of the problem, yeah, it says 10.695 megahertz from that FM modulator. And if we follow it up all the way up here, which is that down arrow, it then branches right, which is this, and then branches north, arrives there. So it's the correct line, but when we look at the frequency, it says 10.595. so yeah, we'll have a look at that, but I don't think I need to worry too much about that at the moment. But again, you know, something else that can throw you off. But yeah, so I think genuinely, I think this TXL01, I think that's not running this. So I can sort of discount that. I can sort of discount this coming in, this 10 point whatever it is meant to be. But we've not got this, I don't think. So again, you further focus down even more and drill down deeper and deeper and deeper, and we arrive at something that could be suspect. Okay, just done a little bit more digging around this TXL01, thinking this was a separate oscillator all on its own, which lives somewhere on another board, but in actual fact it isn't. I found out that the TXL01 is an input socket. It's a socket which is on the receiver transmitter board, and it actually comes in on CN11, which connects to a coaxial cable connection to the VCO assembly, the VCO board that we've been working on all through this video. And I found in the block diagram we were looking at earlier, Q34 is an amplifier on the input chain to the mixer, and obviously that then goes off to what is going to be a VHF UHF switch basically. So there's a UHF and then there's a VHF as we saw earlier. So depending on, of course, you know, what frequency is coming in here mixing, then obviously produces that. Now the LO3 one as well, I found out where that is, and we'll look at that. Again, that's one of the other VCOs as well on the VCO board. But CN11 here is the input connector to the what would be the middle board on this radio, which is this board here in the middle. And there's a coaxial connection that goes along. And so when we look at CN11, the input on the circuit diagram, we've got that here, and as we can see, CN11 is the what would be the to the TXRX unit 2, which is the module that had the VCOs on it. That comes in, goes up here, goes into Q34, which again is that that amplifier that's referenced on the block diagram. Then it comes down to a mixer, and ultimately then we've got the output of that coming along through switching into VHF or UHF paths. Ultimately then there's two more amplifiers with the outputs again connecting via this way, and then we've got ultimately this chain comes back this way to join. So that's again those two amplifier chains that we saw in the block diagram. We have then a broadband amplifier whose output then splits again, switched by two diodes, pin diodes, comes down here, goes all the way along, right the way to the end here, and then outputs then. These are then the coaxial outputs that we can see down here at the beginning of the board that link these. There's a coax there, look, that goes to the UHF board. There's another coax leaves here to go to the VHF PA on the other side. So when we were looking at the diagram earlier, the block diagram, it seemed to indicate there was another local oscillator called TXL01 which is separate to the VCO assembly, and that's not the case. Now if we look at what would be the input connector into this board, which is CN11, if we reference that here, this is CN11, Charlie November 11. If we zoom in just so we get a bit more detail, we can see that this goes off to the TXRX unit CN504. So if we remember CN504, now if we go to the TXRX unit diagram, which I can sort of remember where that is now, it's down here somewhere, and I remember it's got two halves to it, and we'll find it in a second. And the TXRX unit, I could probably get to it a bit quick if I could expand on that, but I don't think I can. Let's just get to it. The TXRX unit, here we are, this is it. So CN504 is the output which is going into, so basically that TXL01 is a socket on this board, on the board we were just looking at earlier on CN11. So that's basically a socket, but on the block diagram it's referred to as TXL01, and it misled me into believing that it was a separate oscillator on a different board. It isn't. It's actually on this board here, and it derives from CN504. So if we find CN504, and it's down here somewhere, let's just zoom in. Right, so that's CN504 there, look, right at the bottom. That's CN504, and that is the TXR units 2, and that goes off to CN11. And if we double back again, we've got this switching and broadband amplifier, etc. And then we've got some more shenanigans this way. We've got an RF circuit this way, an RF output. And where does it end up? Would you believe it? It ends up at the UHF VCO. Okay, now the UHF VCO is this module here. That's the UHF VCO. That's a VHF VCO. That's a VHF reference VCO. So I've got a funny feeling that again, it's just the way the diagram's drawn, that's all. And then up here, this is the VHF reference VCO, and then above that we've got the VHF VCO. So again, we've ordered transistors for all these, but these all output and all get, well, two of them anyway, get fed all the way down ultimately through to here, which is this CN504, and that goes off then to what is the little mixer. Now if I zoom in on here again, as we were earlier, and we have a look down here, so that TXL01 is a socket which is actually CN11 on the PCB, and it derives from CN504, which is on the VCO board. That comes in, and it's the same as well with the RXL01. That again comes from the VCO board and comes in. Now, it would have helped if I'd have put down on there CN11 and CN12, whatever it is, but they haven't done that. So it confused me. I believe that to be a separate oscillator on a different board, and it isn't. It's actually coming from the VHF UHF oscillators on the VCO board. Now, yeah, so that's another thing. That's very strange, but anyway. As well as that, I believe this oscillator is the VHF reference VCO, and that's the input from there. Again, another different connector. So there's 3 RF plugs, if you like, connectors on the board that take these inputs from the VCO assembly, and that's where that is. And if we looked, we had Q34, which we found, which was there. That's Q34. So we sort of, I know from revealing that we're in the right location, and then ultimately that's when we go out. So just a bit misleading, that's all. That's called TXL01, and ultimately that's RXL01. You seem to think that they're like local oscillators. They're actually on the board separate to the VCOs, but they're not. They're not at all. So that describes that. So it brings us back then, straight back to where we left off earlier, which is again replacing the transistors in these. So at least I now know that there aren't any other oscillators somewhere else, if you like, that's impeding us. So it will be down to replacing the transistors in those VCOs in order to get TXL01 back, because we know that the RX local oscillator is working. That's doing okay. It's just the TX local oscillator. So yeah, that's something else. But I just need to look a bit further at this LO2 thing. But to be honest, it's a bit misleading, all this, because these local oscillators, these frequencies that it's referring to on this particular oscillator, don't match up with what I'd seen on the other diagram. So I'll just need to double check to make sure that's not a separate oscillator on its own. So it still could be the T-car up here, which I'm going to check next. So this these need checking, these oscillators, to make sure that these are running. Now I am getting a HF carrier obviously on FM when I transmit, so I do suspect these to be running, but just seems a bit strange, that's all. Anyway, we'll see how we go on, but it is a bit complicated based on the fact that the diagram leads us all over the place with different terminology describing TXL01. It would have been much better if it had just shown a pointer to CN11, and then that would have said then to UHF VCO, VHF VCO, whatever. But it doesn't say that. It just says, you know, TXL01. So it's a signal that's derived from TXL01, and it's not coming. This isn't an oscillator on the board that's on the same board as the receiver and the transmitter circuitry. It's on a different board. It would have been better if it had written TXL01 there, and then put, like, for example, CN11 underneath it, so you know it's a connector coming, effectively coupling a signal from another board into this board. But I do just need to check that out anyway, because it says 31.2 megahertz, and although it says 31.2 megahertz, when we look back at the wiring diagram and we have a look at the VCO again, I I can't see a 31.2 megahertz oscillator on there. I can see a VHF reference VCO, but not a 31.2 megahertz VCO on its own. So I'm just a bit concerned about that, and I just need to look. I do suspect it to be running, as I say, because it'd have to run to get the the receivers to work. So if we have a look on here and we zoom in, there's only like a VHF reference VCO, HF reference VCO. So we've got here obviously the VHF VCO and the UHF VCO as well. We've got the VHF reference VCO, and that's a 36 to 37, 36 to 36. It's not a 31.2 megahertz oscillator. And then this is the UHF VCO, and as we can see then we've got something here. So I'm not sure, to be honest with you. This produces a reference on its output, so I'm not sure. Oscillator, there's another thing there. I just need to check into that. It's very complicated, is that, but yeah, very strange, very strange. So I've got a VHF reference VCO there that supplies an output, comes out, goes into this divider, comes up to there for that PLL. So it also provides a reference, obviously for what is the VHF VCO, and also the UHF VCO as well, because I think it does, or does it? No, I think it only supplies a reference for the VHF reference VCO. So this is a PLL IC to keep this VHF reference VCO in lock, like we had with the HF one, and then there's a reference in there from that VCO. This VCO comes up and feeds the oscillator one input to that PLL, and this PLL is for the VHF VCO, which then buffered signalling on F in, and that's fine. We've obviously got the output of that as well fed this way, which comes down and obviously then goes off to what is the CN11 ultimately on the other board, which is to provide that. So I'm just trying to understand how the receiver bit works but the transmitter bit doesn't, because if it's using the same VCO for receive, for generating the receive frequency, then why isn't it generating the transmit frequency? That's my concern. Unless it's the fact that frequency shifting between the transmit and receive frequencies is causing the transmit frequency to go almost out of lock, or it's not stable. So yeah, it does seem a bit strange. Again, we've got UHF VCO, the output of that comes this way, gets into frequency in for comparison, but also comes this way along here, goes up and ultimately ends up. There's two paths for it, there's this path and that path depending, there's a switch, and then it comes up, yeah, comes up there, joins this. So you've got your VHF and your UHF VCOs connecting here at this junction before it goes through what will be a broadband amplifier, fed out again through two different bandpass filters via two pin diodes, and then it goes off then to CN503. So yeah, and that's that. So there's a receive local oscillator output, which is at RXL01 there, you see, because the connectors reveal what's on them. So that's the RXL01, and then further down you've got the TXL01, you see there. So they're the references that we used on that block diagram, but so that confirms without a doubt that it's the actual oscillators which are providing the TX and RXL01. But what I'm trying to understand is both the UHF VCO and the VHF VCO must be running in order to generate the receiver local oscillator injection, which is coming out on this, which is obviously RXL01, which is this. So that's got to be giving an output. However, the output on the TX-L01 can't be right because we're not getting any transmit on VHF or UHF. So is there a problem with the output? Is there an issue? I don't know. But there again, you see the mixers for all this is on the other board, not this. So this output here could be correct, which ultimately means then the fault may lay on another board. So that's what I'm looking at. So it's not like there's a separate VCO for transmit and a separate VCO for receive. So it looks like to me then those VHF and UHF VCOs are probably running, which they must be in order to, you know, get the receiver to work, and it uses the same RF output path in order to achieve that for the TX as well. So I now need to look at then going back to that wiring diagram that we were just at, where CN11 inputs a signal, and see what it mixes with there as well, because I've got to still try and find that 32.1 megahertz, 31.2 megahertz local oscillator LO31. I've got to find that, and I can't find any designation that says LO31 on these connectors here, so I'm just looking at HFLO1, but I can't see anything that says LO31. So is LO31 derived on another board? Possibly. That's different. Have a look. Keep going down here. I can't see anything there that says LO31. There's nothing along the bottom from what I can see as well. So no. So I need to find out where LO31's derived from now, and then look at it further. Okay, so now we're going to examine this LO31 more closely. Now on the block diagram it showed that on the output of this LO31 there is 3 buffer amplifiers, and we just need to track down these on the schematic diagram so I can then find the circuit around it. So Q44, Q65 and Q50 are the amplifiers. So once we find those, and we can trace back to find the origins of LO31, which I've already managed to find on the diagram just here. So we've got CN7 here, which I've traced back, which then goes off to the TXRX2 unit W503. So I've got that information now, which I didn't have before. But if we just follow this a moment, there's this LO31 signal comes in here, which is this so-called 31.2 megahertz. And what happens is this signal comes along, and basically it travels across here as per the arrow, comes along and then comes down. Now then, it comes down to what is Q65. So that's one of the 3 amplifiers. It also then comes to here and goes along, and then also goes down here, and that's connects to Q50, which is another one of those 3 amplifiers. So that's 2 out of the 3 we've found. It also splits this way and then goes off to what is Q44. So that's all 3 amplifiers. So we now know that the signal that's for LO31 is derived on the VCO board, because ultimately it all goes back to this connector here, which is W503 socket on the TXRX2 unit. So we now know that that 31.2 megahertz signal is meant to derive from there. Now obviously after it's gone through this amplifier here, which is Q65, that then goes off to what will be the 1200 megahertz option, and then the other amplifier down here is the Q44, which then goes through what would be this transformer and then up into this amplifier, and ultimately then that would mix in this mixer, because this is the mixer, and then that ultimately then would give an output here which goes along, and then if we follow it down right the way down here, then that goes out to the TX-RX1 unit, which is the HF or VHF output for that. Now the TX-RX1 unit is the board in the middle of the transceiver, and that is where obviously it goes off and for final signal processing before it's sent off to transmitter receiver circuits. Now what I have noticed as well, obviously, because every indication seems to indicate that the VHF and UHF VCOs are running, because obviously we're getting the receiver, is it possible that, if you remember down here, we had a socket leaving this board which were the final signals for the 430 megahertz and obviously the VHF. So these are the signals that go out. Now if we zoom in really intently, then we can see more detail. So we can see 43TX stands for 430 megahertz TX, 140X stands for 144 megahertz. Now you've not to get confused with that terminology HF, because to me HF is 0 to 30 megs, or in this or 0 to 50 megs if it's a 6 meter transceiver as well. But what it is this HF unit here deals with both VHF 144 megahertz as well as the HF as well. So, but because its designation is HF, it can mislead you to believe that there's just the HF 0 to 30 megs or 0 to 50 megs that's dealt with by this. It's not true. It deals with both the HF and the VHF. So you need to look at this terminology here that's on the CN connectors. So what also could have happened, which does happen from time to time, especially when somebody else had a look at the radio and maybe they've been rushing and not put things back right, is they can get these connectors in the wrong socket. So in other words, the VHF frequencies feed can be actually feeding the UHF, and the UHF output can be feeding the VHF amplifier. Obviously when that happens, then neither amplifier will be able to amplify that signal, because you've got a VHF amplifier for VHF signals and a UHF amplifier for UHF signals. That's why they're separate boards. So it could be whoever's put this back together, and this is what I need to check now, is CN3 and CN4 connections on the board in the middle, which is, I believe, this board here in the middle, this one. There's some connectors right at the front which go off to the input there for the UHF PA. That's one connector there, and then there's another connector at the front of this board just under here, which then goes through to the other side, because laying here on this side underneath is the VHF PA. So I just need to check that out, because it's interesting how the VHF and UHF receivers are working okay, and they work off the same VCOs that also provide the transmit frequencies. So I believe there's a possibility these two connectors could be incorrectly connected. In other words, are swapped. That is a possibility that I need to rule out. It may not be the case, but I need to rule it out one way or the other, and then we can also start to work back. But what I'd like to also do now is, if we just step back a bit, where we were looking at the input to what would be LO31, which is a so-called 31.2 megahertz signal that's coming in, and I just need to zoom out a bit more so I can see where I am. So right the way over here, Oh, it's a long diagram this, isn't it? Right, so this is it here. So that goes off to our friend the PLL board, the transmit and receive VCO assembly on W503. So let's go back to the wiring diagram. Let's go and find the VCO assembly again, which is down here somewhere when I can find it. Just bear with me a second, and ultimately when we get there, now then, let's have a look here. Near it now, I think. Yeah, that's it. Right, so let's have a zoom in here and let's see if we can find W503. So that's CN530. W503, there we are. So that is this so-called 31.2 megahertz output. So let's trace this back, and it goes obviously from an amplifier. Looks like we've got multiple, pass here, doubler circuit. Ah, right. Now I understand. Now I understand. Yes. It's all become clear. If I remember, really early in the video, we had a reference oscillator that worked at 15.6 megahertz, I think it was, and it was, where was it now? Let's have a look. Let me just zoom in, see if I can find it. There we are, look, there we are. So, where am I now? W503, where the hell's W503? Right, W503 is there, yep, that's it. It gets its signal from up here, and this amplifier, which comes from CN530, jumps across obviously to W501. And we've got a signal coming in, you see, and this originates from, if we remember a long time ago, right at the beginning of the video, we were tracing what was our little friend, the 15.6 megahertz reference oscillator, which is a heart of the radio, one of the many hearts this radio seems to have. Anyway, this 15.6 megahertz reference oscillator outputs its 15.6 megahertz up here, and then it spits it out onto this on this connector, then goes in, gets amplified and doubled, because this is a doubler circuit, and that frequency then is 31.2 megahertz, because that's a double of the frequency of a reference oscillator. So it gets doubled, passed down, amplified, and then passed back on W503. So that explains where that 31.2 megahertz comes from. It comes from the reference oscillator, and it's a fixed frequency that doesn't change. So that proves that is the reference oscillator, doubled frequency. So I'm just writing that down so I don't forget. So that is where that comes from. So we'll need to check that on that input to that other board, the board in the middle, is getting that frequency, which I suspect it will be, because we did measure it earlier on in the video and it did seem to be there. So that proves that. So I had wondered, because I was looking all over the board to see whether we had a VCO called LO31, and we didn't find anything that related to 31.2 megahertz. So if we go back to the block diagram here, and we zoom in again on the block diagram, and I do have some more information on another diagram as well that I've seen. we can see then that this LO321 here, this is actually now the doubled frequency of the reference oscillator that's fed in. And we found these amplifiers. So we proved where that's coming from. We know where that's coming from. So that's good. Now, I've got a funny feeling, and I'm going to check that next now, that the output at the end here, after these diodes, 144 and 430, there's a socket for that output and a socket for this output. And it could be that they've sort of got crossed, where somebody's plugged in the socket for 144 and 430 megs that way around, and thus then the output signals for 430 megs are being fed into 144 meg board, and likewise the 430, you know, the 144s into 430. And obviously these amplifiers for 430 will not amplify the 144 megahertz signal, and nor will the UHF one either, and the VHF respectively. So it's going to be interesting to check that out. Now if we also look a bit further down on this block diagram as well, and we've got some more information on here that's quite helpful. So here it tells us about the way each one of these modules works. So we've effectively got the UHF VCO, we've got the sub VCO that we know about for the sub, and the VHF, and as we can see both the VHF and UHF are amplified, and essentially the crossover to the other side, you see, and so ultimately then they're amplified up and switched and filtered. So then basically you've just got what would be the RXLO1 output and the TXLO1 output respectively, and it's very important to reference that as well. And we've got CN7, if we can find that somewhere as well. I'd like to be able to find CN7. I'm not sure where CN7 is on this. CN506, there's CN502 up there. I'm trying to find CN7 for that 31.2 megahertz signal which comes in, so it might be around here somewhere. HFLO2 15.6 megahertz, so it shows that, and then it comes in and there's a ×2, you see, and then it shows that, and ultimately comes up to there. So it doesn't give you much information, you see, about the connectors once it's gone through that, because between this X400, this 15.6 megahertz reference oscillator, and here are connectors W503 and CN7, but it's not labelled on here. Some of the sockets are labelled, some aren't, because after all it's just a block diagram level. But you can see then that that's where the reference frequency, after it's been ×2, comes in, and then ultimately it can go off then to provide reference signals for all the different VCOs and all that malarkey, and mixers and goodness knows what else. So yeah, very interesting indeed. Very complicated, very messy, unfortunately. So what I'm now going to do, because I'm fairly confident that 31.2 megahertz is there, but we will measure it just for continuity. And I want to look at that output that comes out, these sockets here, the signal once it's fed off and it's gone back into switching for VHF UHF paths, it will then get split off to the two different connectors that go off to the final amplifiers, the transmit amplifier for UHF and the transmit amplifier for VHF. and I'm absolutely got to rule out now that the transmit and the two transmitter outputs, one for VHF, one for UHF, are in the right place, because I don't know what the person beforehand has done, you know, that maybe I'm not aware of, because I wasn't obviously party to whoever it was that had been in it before. But these two here, I've got to check those, so that's what we'll do next together. We'll have a look and find CN3, we'll have a look at CN4. Are they in the right place? They may be, or they may be not. Let's see. Okay, so the plot thickens. We have found CN3 and CN4, which go off obviously to the different feeds. So ultimately this is the UHF PA board. This is a UHF input that feeds the drive signal, and that then goes, it's just a grey cable on its own, and it goes down to here. Now when we look at that more intently, you might be able to see, depending on how good I can zoom in on it, there is a reference that says CN4 and CN3. Now it says CN4 there, which is this cable with a yellow thing on, and then CN3 is the other. Now according to the circuit diagram, CN3 is the UHF feed, which is this one down here, and that's correct, because that's just a grey cable on its own which loops round and then obviously goes to here, which is the UHF drive. The yellow banded one is for 144 megahertz, and that goes off to the other side of the radio where the VHF PA. So these are connected in the right place. Had they been reversed, obviously that would have, you know, resolved that, but they're not. They're in the correct place. So we've now checked that, and we know that to be okay. So the next thing we're going to do now is we're going to go on to what is the doubled frequency output of the doubler circuit, and we're going to check that 31.2 megahertz signal is there. That's what we're going to do on this board. And then we did check that earlier, but we'll check it again and just make sure that's present for that frequency being LO31, which turns out to be the doubled reference oscillator frequency. Then I think what I'm going to do is I'm going to get the coax of truth. We're going to put it on UHF or whatever, and we're going to connect the coax of truth to here. And I've also got one of these leads with a BNC on the end of it that can plug in here as well, and we can measure the drive to see if there's any drive signal, and measure that. Hopefully, yeah, could be that there's an issue with the amplifiers maybe that give the output drive, possibly. Who knows. Let's see if we get a frequency coming out. Let's see if we can measure something anyway, and that'll determine whether it's an amplitude problem or a frequency issue. Obviously if we're getting some signal but low amplitude, that needs to be investigated as well. If it's a very high amplitude and we're not getting an output, then it could be a fault on this UHF board as well as on the VHF, but I doubt that both would have the same problem, both VHF and UHF. Now obviously as far as the schematic's concerned, that's the connectors there that we've just been looking at, these two on the board. So when we go back and look at the detail about that, are they fed with common amplifiers, which they are. This broadband amplifier here, this IC3, this obviously has a supply to it as well, which obviously comes from here, the inductor feeding power onto here from this line. We need to check if that's the case, if this has got a supply voltage, is it amplifying? So we might need to be able to do some tests around this as well. That's ultimately if we find that you know, we're getting an input. So again, there's lots to check. There's mixers, there's all sorts of things as well, tuning capacitors as well that may have been tweaked by somebody before me, who knows. But we just got to see whether this amplifier is amplifying, and ultimately then it could be a problem with the pin diodes even. Maybe they're not getting the switching, the DC lines going to them to switch them on and off. So there's a few things to check here, and then we can trace back from there. Okay, so when we check this other signal now, this, what was this LO331, this 31.2 megahertz signal. If you remember, we got the 15.6 megahertz coming in on W501. It leaps across on a cable loom, then to CN530. So we've got an interboard link before it gets to the doubler circuit. So W501 is actually down here on this board. So I'll just point to W501. The reference oscillator's there, and W501 is here, and that cable comes off, goes round, and as we can see, so W501's there, it comes round, connects here, and that there is CN530. Then it goes into the doubler circuit, which is on this board, probably is under this cam, and then it comes out then on W503, which as we can see is this is W503 designation, and you can see the W503 label on it. Then it leaps across, so W503 then is essentially this connector here, that one, and then it leaps across, and as we can see then connects to CN7. So now we're looking to see that this lead here goes to CN7 on the board, which is obviously down there. So if we just have a look a bit closer, and maybe we can see CN7 down there. So this is CN7, and it connects there. So on this connector I should be getting 31.2 megahertz, because this is where it enters that board, this middle board here with all the mixers and everything like that on it. Now I did try and find the IC, the broadband amplifier IC on this, and I thought it might live round this vicinity somewhere, because these connectors here are the ones that are for VHF, UHF drive outputs for the power amplifiers, but I couldn't find it. I think it must be under the board rather than above the board. So again, you know, that's a bit unfortunate, but we're going to have to just verify on that connector CN7 that we're getting 31.2 megahertz, and then we know that's arriving on this board and there isn't a fault with this lead or whatever. And then from there I think it's just a case of looking at some voltages and levels that are on here as well, and looking at that drive signal. So that's where we're going now. Right, we're ready to do a measurement now of the UHF drive. We've got the coaxial cable connected. We have a special cable made up for testing Kenwood radios with the connector at the end. Obviously the jumper cable that was in situ prior, which connects the middle board to the UHF PA board. This jumper's been removed, and we've now connected this cable in place of the original jumper. So we're now measuring the TX drive that's coming off this board to the PA board, and so we've got this connector here arrangement, and then it goes off to the high sensitivity port, the 1 watt port on the Marconi test set. So we set the radio up to do 431 megahertz on transmit dead. I'll just set the TX frequency up now, so we'll turn that off, 431 megahertz there. And now what I'm going to do is I'm going to press the transmit button, and let's see what drive we get. We should be getting quite a few hundred milliwatts drive. Well, 431 megahertz is dead center in the screen, and if I just turn that off there, move that. So 431 megahertz is dead center of the screen. We see we've got a signal here very small in amplitude, and yet that's exceptionally small in amplitude. Is that very bad? It should be a lot higher than that. So let's see what frequency that is. So let's select the spectrum analyzer, and let's see whether we can go to that frequency. So we'll move marker 1 now, to that frequency, and it's on 426.080 megahertz roughly. So yeah, that's a bit not what I was expecting. Obviously if I unkey the transmitter the signal goes, but its amplitude is very low. Look at neg 45 dBm, neg 46ish, so it's very weak, nowhere near enough to be able to drive the the RF amp. So that explains why that's not working. We can check the VHF one as well to see what output that gives, but I would have expected, if the VCO is running correctly on frequency and the mixing process was to take place properly, even the wrong level to be right in the centre of the screen, which is at 431 megahertz, I would have expected to see a very small signal, but it just shows that we're not getting any stable frequency at that, and the level is extremely low as well. So we've got two things going on there: frequency inaccuracy and level too low. So something strange going on, something strange. Right, so let's have a look now at the VHF drive. Okay, so now we move a cable over, we disconnected the VHF drive, which is this yellow one, and connected in now into what were the VHF output. So what we'll do now, we'll just observe that again on the thing. We've set a frequency on the radio to 150 megahertz, and I'm now going to transmit, and because we've enabled the test set to that frequency as well, and keying up now. The radio's drawing about 6-7 amps, which is obviously due to the bias conditions on the VHF amplifier, and as we can see there is absolutely nothing there. That's at 2 meg per division. So let me just open that up and see whether we can get anything at all. So let's just unkey, key back up, unkey. Let's have a look at reference level. So now we're getting a signal when I increase the sensitivity of a test set. We'll put the expand on, and we've got a few frequencies there. The one on the left, if I unkey the transmitter now, that's just the start frequency, because if I put the marker 1 on, you can see there we've got sort of 0 megahertz there, marker 1 at the top middle. So if I rekey the transmitter and then we go right the way up, obviously we've got something there at 145 megahertz. We've also got something at 383 megahertz. So I think some of the mixer frequency, or the frequency that's going in on one of the inputs of the mix, is making it through, because if you remember earlier on the diagram, there is a 300 and something megahertz signal that mixes with another signal to get the right frequency that we need. So, but there's nothing at 150 megahertz. We've got a minus, again, very low level, minus 52 dBm at 382 megahertz there. So that's totally wrong. That shouldn't be present. So unkey the transmitter. So we prove there that the TX drive for both UHF and VHF is totally and utterly, out of spec, which is unfortunate. So yeah, I think ultimately it looks like as if we might have to do some work around that. But before I start taking this board out, because it could be the level that's coming out of these VCOs. We've already proved that there's 2 VCOs that had the transistor failure, because obviously the output level wasn't right. The capacitance of them had changed, or something had happened to those semiconductors that prevented them from working properly, because when we replaced them, that got the VCOs running for the HF ref VCO and LO2 VCO, the HF LO2. So I think by replacing the transistors in the others, let's see whether that rectifies this issue. It might be that the RF levels that are coming out are too low, and thus the signal is enough coming out of them in order to make the local oscillator injection for the receive mixer to work to some extent, but may not be right for the transmit. And I want to avoid taking that board out as much as we can, because then we're bending the flexes at the end and disconnecting, connecting, disconnecting. They've already been under a lot of duress with the boards being in and out already. I don't want to exacerbate that problem any further. We can access these VCOs to replace the transistors very easily. I'd like to do that first. Let's get the VCOs set up properly, including the HF LO1, 2 and 3. Get all those transistors replaced. Let's get back to square one with that, and then if we still don't get enough drive then coming from this board in the middle, then it's time to whip that out and do some more measurements around that and have a look and see what we can find. It's going to be more difficult to fault find on this board because the circuit we're interested in is underneath this PCB. So again, you know, when you start removing flexes and things, it weakens flexi circuits because you're removing things all the time, and it causes a lot of strain on flexi circuits, and you can get a lot of damage and things like that that can occur from constant removal and reattachment of these. And we've got one down there as well, and two flexes, so I want to try and avoid taking that out if I can. Just concentrate on getting this VC up and running, and that might solve the problem anyway, because the output levels of these have come back up to where they should be. Again, they might not be operating properly at the frequencies are meant to, so that's another consideration, because obviously the frequency shifts between the what would be necessary to mix with the transmitter versus the receiver local oscillator injection. The frequencies will move about, so it could be that, you know, certain frequencies are okay, other frequencies the levels reduced, or it's noisy, or it can't produce an output at that. So yeah, I'm hypothesizing at the moment, so let's wait for them to arrive, those transistors, and then go from there. Okay, so our new transistors have turned up today, and we had 8 ordered, and we just used the first one in the UHF VCO down there. So as you can see, we've got that nice K52 logo on top of it, and that itself then should, as you can see there, K52 on that transistor. And the new ones have got really clear legends on them. When I took the old one out, it actually broke up a little bit, which is unusual. But we got a few little bits. I can just zoom in on this a bit, but we got like one of the corners broke off it, and sort of the plastic housing on it, you know, the lead stayed on it, but the actual plastic housing broke on it. So I don't know, just seems a bit like poor construction or something like that. Wasn't putting too much heat on, and I have snapped the lead off now, but the corner on one side had fractured, and that's the corner there, this little black chip. So there's something going on with it. I weren't using particularly high temperatures to remove it either, or too much physical stress. Anyway, so that's the UHF one done. We'll put the lid back on and put a little mark on the top of the lid to signify we've replaced that, and now we'll move to the VHF one. Okay, so that's the VHF transistor replaced with a nice new one. So ready to rock and roll with the next one now, which is the VHF reference VCO, which is this cam. Onwards and upwards. Okay, so reference VCO transistors being replaced now, so we'll move on to what is the 3 VCOs that are contained in HF LO1. Okay, so as far as the VCO LO1 is concerned, the HF LO1, I've had to bend this lug up here that would normally be over this area, so I can get to that transistor down there and replace it, which I've done. Tried replacing it with this lug down, but it's just impossible. It's you know, even with the thinnest soldering tips going in, just trying to get the old solder off and then manoeuvring there without burning anything or messing something else up's difficult. So it's better just to bend this out the way, and you can always bend it back. I've got a funny feeling after we replace the net transistor on the list, which is this one, and we move on to this one which is under this tag, again another tag there in front. Now when you look directly over it, you can see that it's very difficult to get down there to try and replace it. It's not in as bad a location as this one is when that tag's down, because of this corner here. But nevertheless, I think I'm going to have to bend this tag up so that we can get to it without causing any damage, to get the old one off and the new one on. So, and we'll just bend it back when we've finished. Okay, so we've got the last transistor in down there, and this transistor is in now. So all three are being replaced in there. We'll just bend these lugs down and then move on to the subband VCO. Now the subband VCO lives under this module over here on this other board, which means having to disconnect this flexi, and I don't like doing that because this flexi is actually quite starting to get damaged with the amount of times that it's been removed or bent about. So I'm going to try and, if I can, replace those transistors in there just by moving this out of the way a little bit without having to unplug it if I can. But there's two transistors in there for the subband VCO, so we've already replaced the transistor in this unit here, which was the HF ref VCO, I think it was, or was it? Let's just have a look. Just double check on my diagram which VCO that. Oh, that was the LO2 VCO. We've already replaced the transistor in there because they've got a little black mark there. So it's just the two transistors that live in the sub VCO now, and I've only got two transistors left on my my little shrink pack thing there. I've only got two inside, so we'll be using those last two transistors in order to get the sub VCO done, and then let's go back to the alignment procedure and see whether we can get these VCOs to behave themselves. Okay, so we replaced the sub-band VCO transistors. So there's a transistor down here, which is that one, and then the other one up here. So both of those have been replaced now. So we'll put the sub-band VCO back together. This now completes all the VCO transistor replacements on all the modules that's in the radio. So this is a moment of truth then, whether the fault's on this board. If you remember earlier, we had a broadband amplifier on this board which produces both the VHF and UHF drive signals out of the connectors at the bottom here, these two, the yellow one and the grey, and they then go off to, you know, the respective power amplifier boards. And if you remember, we were not getting any RF drive coming out of there, so replacing the transistors on here, making sure the VCOs are all in lock and alignment, then rules out a possibility with this, and then we can look at this board if we're not getting any TX drive coming out, because, you know, we needed to rule this out anyway, and we had problems with a lot of voltages on the transistors we didn't, on the VCOs with the transistors we didn't replace, whereas the VCOs that we did replace the transistors on, the lot voltage was back to normal as per the manual, the specification laid out in the manual. So right, reassemble now, and then let's come back after the alignment procedure. Okay, so the moment of truth has arrived. What I've done just off camera, I've just connected this up to the test point down here, and it's a devil to get onto, is this one, I'll tell you that. Okay, so we need what we've basically got the radio tuned to 30 kilohertz, and we should be getting a voltage of 1.45 volts now at 30 kilohertz. It's just slightly high. I've had to adjust the trimmer cap off camera to get it down because it's about 3.5 volts. So I'm just going to go back onto it again. Just got to be ever so gentle, because obviously you only got to breathe on it and it can change. So we'll just get that down to 1.45 volts because the tolerance is 0.05 volts. So that's good. We certainly couldn't get that before. So that is that done. Now the next frequency we need to go to is 17 megahertz, which is the HF2, so that will be the second hole there. The second oscillator will get switched on, and we need to adjust that to 1.45 volts. As a matter of fact, the third one's the same, yet again on a different frequency of 37 megahertz. So let's do that then, move to 17 megahertz. Okay, so we're on 17 megahertz now. I've just got to be very careful not to short things out on that PCB that stood up. We had a voltage there of 1.05 volts, so just need to get right onto that capacitor if I can. And it's really difficult to try and get this trimmer tool to settle on that capacitor because it's in such a very difficult location to get to. It really is. And it's a tiny little screwdriver. Right, let's see whether we can just get on. Very difficult is this one. There we are, look. Right, let's just adjust this then for 1.45 volts, since we're on that frequency, and just try and settle it down as much as we can. Very gently do it, because as I say, no sharp movements on this, otherwise that's it. So there we are. Remove a screwdriver and it's dropped down below its tolerance. It's again, I've messed it up now. I'm going to do it again. Right, 1 point. I'll just take it a bit above then to say 1.48. Ooh, nearly. It's when you remove a screwdriver, it drops down to 1.43. Oh, bloody hell. Just trying to get this damn thing in. Oh, messed it up. It's magnetic screwdriver as well, so it likes sticking to the actual can of the sticking to the actual can. Right, let's see if we can get it to just shift again. It's very sensitive, is this. Right, I'm going to leave it at 1.50. Now it's not been too badly affected. Let's go back in after we composed the self a little bit, because I've slipped off the test point now. It's difficult trying to get the test point. We're doing a non-metallic screwdriver on it actually. There we are, look, right. It's such a tiny little thing, so let's see. There we are, look, that'll do it. 1.46 volts, I'm not going to faff about. So that's okay. So the next frequency now will be for the third oscillator, and that is 37 megahertz. So let's do that. Okay, we're on 37 megahertz, back on that test point again, and now it's the third hole. We're getting 1.24 volts, which is certainly a lot better than we were getting before, because according to this sheet we were getting silly voltage before. So let's just adjust it then, see if we can get onto it without causing any damage to that PCB that's next to it. It's very difficult to get onto these capacitors because of the magnetic flux on the screwdriver is trying to get it to stick to the actual can, the screening can. Right, so let's get that to 1.45 volts as per the manual. See if we can get it to just settle. There we are. Leave it at 1.46. Not going to argue about that. That's on okay now, and now we can move to the VHF reference oscillators and the UHF ones, which are these. So let's move on to those. Okay, we've set the frequency of the radio to 142 megahertz. We're now going to the VHF reference VCO, which is this, and test point 512, which is immediately next to it, right in the middle of those two cans, so it's down there. So if we just get onto that again, the voltage on this, it says needs to be tuned for 2 volts. Now this one's a slightly different capacitor than the other one, and I'll need my yellow trimming tool. This has got more of a purchase on it as this capacitor, so let's just go in, and we need to tune that for 2 volts, bang on. So we'll get it to 2 volts. So that's okay. And that's that then. Now we'll move on to the next measurement then on the list. So we'll see if we can find that. I've got it here somewhere. And carry on with that. Right, so the next measurement is on the VHF PLL, which I believe is this. Yeah, that's right, the VHF phase lock loop. VCO is that one, and we need to again use the same frequency of 142 megahertz FM, and this time we're going to TP503. Now TP503 is actually on the this side of the VCO. We need to attain 1 volt on there, TP503. So we'll go on to that TP503, which I think is, I'll just have a look at my magnifier. Yeah, it's just there, look. TP503, and we need to adjust that capacitor in there for 1 volt at that frequency. So we'll just go down to the trimmer cap, and I can't remember if this one, oh, I think this has got the other type of capacitor in it like we had before, where we need this, and we should be able to get onto it. There we are, look. So we need to tune this then for 1 volt. So just very carefully, now we're climbing in voltage, just need to come down. You just settle it down very carefully, very gently. As soon as you remove the screwdriver, of course, it leaps a bit. It's the frequency of oscillation and the weight of the screwdriver on the trimmer and various other bits. So it's nearly there. Just got to settle it a bit more. Ooh, so close, yet so far away. And let's just, I don't want to take it too high, because if I do, it'll maybe out 1.02 and then it'll settle at 1. Still going down to 9899. Might have to try 1.04 then. Let's see if we can get it to around about 1.04 if I can. Maybe there. There we are. Ah, still going down to 99. Can't win with this. Now I've knocked it way off. Right, let's see if I can just get it. Very difficult is this one. Sort of either got... There we are, look. Wonderful. But we're never going to get there. Right, so that's that. That's the VHF VCO. Now we'll move on to the UHF PLL, which is this one here. And we need to set a frequency according to this of 449.990, is it? Yeah, 449.990. So let's check that. Okay, so we set the radio now to UHF frequency of 449.990 megahertz, and it then says go on to what will be TP 504, and we should be getting a voltage according to this, or need to attain a voltage on TP 504 of 6 volts DC, 6 volts DC. So let's just see what we get then. So let's just go on that test point. There it is, and we're getting 6.8 volts, and I just need to go on this trimmer cap then and then adjust it. Just give it a little wipe, the trimmer cap, because sometimes I get a bit tetchy, and just carefully tune it to 6 volts if we can get that. It would be nice. It'll probably be on a very difficult to attain 6 volts. Let's see if we can get 6 volts. I'm probably affecting it quite badly. Let's just have a look here. It's more difficult on this one actually to try and get 6 volts. Oh, very sharp, that, very sharp. Let's try it the other way then. Ooh, yeah, very sensitive. Only got a breif on this one. Difficult when you get to UHF. Right, let's just see if we can back it just ever so slightly the other way. 6.05. Oh, it's not bad, but I've come off the trimmer cap now, and it's always difficult when you come off a trimmer cap trying to get back on it again. And now buggered it up altogether, so I'm going to have to start again. Let's see whether we can get it to bang on 6 volts. It's so difficult, this one. But let's stay with it, let's see what happens, because we're not rushing. Ooh, you've only got to breathe on this one very carefully. Ooh, 6.01, 6.02. That'll do. Near enough is good enough. So that's that done then. So the next one is a sub VCO, which is down here. So that'll be more difficult to get to. Let's work out how we can measure that. There's 2 VCOs for the subband PLL, subband 1 and subband 2. So one we check on 154.495 megahertz, and the other one we check on 173.995 megahertz. So let's see whether we can adjust those. Fortunately, the capacitors in those are the larger ones that take this size trimmer tool, so be easier to get onto, but it's just trying to get down there between all these wires and things like that, and past these wiring looms. And so let's turn the radio off, peel back that foil, and then see whether we can get onto the measurement point, which no doubt will be practically inaccessible somewhere down there. Let's have a look at that next. So far so good. Obviously it's proved the point that replacing the transistors has resolved the issue of the lock voltages being out of spec. And what I'm looking forward to after we've measured and adjusted the sub VCO is to see whether the damn thing transmits on VHF or UHF, because we know it transmits on HF, but we're just not getting any TX output on VHF UHF. So let's see whether this all sorts that out. Otherwise it's back to the drawing board, and the fault may be on that middle board. Fingers crossed. Okay, so we're on the sub VCO now, sub VCO 1, and it said we've got to achieve 5 volts at 154.495 megahertz. So we'll just turn this now to 5 volts, which is sub 1 oscillator. So there we are, 5 volts. So that's that. So the next frequency it says that we should check is sub 2, which is a second hole then at 173.995 megahertz. So let's do that next. Right, so we're on 173.990 megahertz. We've just got to get this 5 volts. I think it says 5 volts again. 173.990 megahertz, 995. 5.5 volts we've got to adjust this one for. So that's the second hole along, and we've somehow got to try and get on the trimmer cap for it, but I think I'm just gonna have to have another look at this, because I think that the trimmer hole for this was actually towards the end of it rather than, yeah, it's right in the corner, right up there in the corner down there. There's a few holes in it actually, but there's another hole which is just right up at the other top corner. I've somehow got to try and get a trimming tool in there, just backing them out. Right, very difficult is this one, because the hole's right down the middle there, right at the very edge, and it's very difficult to get onto it. We adjust this for 5.5 volts. Let's see if we can get on it and get the damn thing to adjust. And it says 5.5 volts on the manual, so there we are. So that's the sub 1 and sub 2, yeah, 5.5 volts. So, and again 5.5 volts for the other. So we've done that. There's nothing wrong there with that. Let's see whether it transmits now on UHF and VHF. Back soon. Anyway, after all that, we've finally got the VCOs running. Lovely, beautifully done. I expected it to transmit on UHF and VHF, but nothing. Back to square one, I'm afraid. But at least we've ironed out all the problems with the VCOs now. They're in lock. There's no problem with any of the bands with the dashes on the display. Everything seems to be okay. So I do want to now focus on other areas of the radio that we've not yet looked at. Now, a couple of things here. I noticed that when I've been disconnecting these flexes earlier in the video, we disconnected them here on the control board, and we noticed huge levels of corrosion to the tinned contact surfaces on these flexes. But likewise, where they connect also to the PCB, the fingers on the end, the contact area which connects into the sockets themselves on the actual PCBs, the VCO PCB assembly, the main radio board receiver assembly and exciter, plus this board on the top here. Some of the fingers, they're actually bonded to like what appears to be a piece of card. It's almost like a plastic card they're stuck to. And what's happening is, with the amount of times being connected, reconnected before it's come to me, what it's done, it's resulted in the fingers lifting like that and coming away. So you get like one, miss one, then another one starting to lift. And I've had a job to keep them down like that so that I can plug them back in. So every now and then one of these fingers comes up like that, and I have to be very careful to settle it down, then we can plug it back in. And that's what I've been doing throughout the course of this video. But it's evident with the marks on the board that we've had, particularly on this PCB, there's a felt marker on this board, which is on the other side, and it's just down here. There's a felt marker there. There's other marks as well, which we'll see in a moment on the front. These flexes have been on and off more times than you could possibly imagine. And faced with the fact that we've got severe corrosion on some of these pins, as you can see there, particularly with that one, and the terrible corrosion on them, which we've done as best to clean up, and the other flexes that are on there as well, like this, really severely corroded on the far right. We might end up having to go down the route of trying to procure replacement flexes, so then we know we're starting with a known good flexi. Now, I haven't found, or there again, I haven't deliberately tested all the flexes from end to end to make sure that each contact is working. But on these creases where they bend over and they connect to different sockets, and they've got sharp creases in some of them, and this ultimately can break the connection. So that's been an issue right from square one, but we try to work with it and work around it. Now, the other thing that does concern me a little bit as well is the amount of corrosion that might be on this board, which we're going to remove a control board. But just looking, if we look a bit more closely there, you can see again there's some felt markers. Again, some felt marker pen has been connected, on these connectors, being wiped on. So I don't know what that's about. I don't know why that would be, but there's definitely something going on where somebody's got to this level before, perhaps suspected the flexes to be an issue, DC voltages, etc. Now, we know from the circuit diagram that the broadband amplifier IC, which is on the board under this one in the middle, that amplifies both the VHF and the UHF RF signal that leaves the VCO, that's amplified by that wideband amplifier, and then it's passed out via diode pin switches to what is the VHF or UHF drive signal cables, which then go off to the power amplifiers. And as we saw earlier on the spectrum analyzer, there was no output at all, no RF output from those sockets either. So it would appear to me that when I looked at the circuit diagram, they get their actual 8 volt supplies, the transmit 144 megahertz band gets its transmit supply from this control board via a flex that goes over to the board in the middle, and also the transmit for the UHF 8 volt rail, which goes to the amplifier as well. That goes via this flex that connects to the middle board from the control board, which is, I think, this one that's got the corrosion on it. So I've now got to look at that. I can't obviously rule that out, but we've got to then do some testing around those supplies. Now obviously on the other board in the middle, the components themselves are mounted under the board, so it's impossible to be able to test on the IC while it's powered up, because you need the board in situ for it to work. So I've got to try and find the voltage on here and also on the other board somehow. I've got to be able to test on the actual connector, the socket where this ribbon cable connects to, and get on a pin and verify the voltage that leaves this board also gets to that board, because if it doesn't, then it's ultimately going to be the flex. Now when we looked at these connectors earlier in the video, not only did we have problems with the flexes having corrosion on the contact surfaces, but also the receptacle pins in the socket were corroded, and we had this green sort of copper corrosion. And if you remember, we went with a diamond edge file and some contact cleaner lubricant, and we went in there and cleaned all those up, or the best that we could, and then washed them out with isopropanol alcohol just to get that part working. And I noticed as well that the display on the front here, the LCD display backlights, some of them were working before we did that, and then afterwards they all started to come on. And throughout this video I've noticed that the backlight for the display sometimes is intermittent. Some LEDs are on and some are off, and you know, there's still an issue there. So that's a minor problem really in comparison, but I think it indicates a more serious problems deep within the control board. Now because of the amount of corrosion on this board that we cleaned off the sockets, and the flexes are still potentially, there's a question mark about those, I need to remove this control board and have a look behind it to see what's wrong there. Now it could be there's a load of corrosion on this board as well that we're going to have to look at. And then at that point we've got to make a decision. Do we try and procure these flexes, assuming they're still available, and they might be cheap to buy, they might be expensive, I don't know. So we'll need to look at that, and we'll need to evaluate this control board. But with these felt marks on these sockets, there's definitely somebody been into this level before and obviously marked this this board for some reason. So maybe there's a reason behind it. Back soon. Okay, so I'm just looking at this board a bit more intently, and I can see a few areas of concern on it. But one of the things is we've got some more writing here. There's something written there. I don't know what that is, but there's something there anyway. And then on top of that as well, when we turn the board over, we've got another blue marker just here by this resistor. Something's been marked on the board, but it doesn't look too bad on the back, funnily enough, at this stage. I've just got to go over it with an eyeglass just to make sure that the PCB itself's not corroded in particular places, considering we do have a lot of corrosion obviously on these flexes, as you can see with that one and this one. You know, these are particularly bad that need to be replaced. So that's the one that goes off to the control head, is that one, because this is the control head, the back of it. So that explains why we might have issues with the display. But insofar as the logic board's concerned on this particular radio, there's definitely something been going off for these connectors to be marked, and for some language to be written there, something about something there. With these connectors, might have to look at those again, see what condition they're in. But yeah, I think there's a couple of things really. Just a visual inspection of this first, and then let's have a look at what we can do about the flexes and see whether they can be replaced. Yeah, so this is the only thing. I know this particular flex here, I had issues with that on the other side as well. It doesn't look too bad here, this, but on the other side where it connects to the VCO assembly, there's some quite tight nips in it, and some of these little pins were starting to come up in places. So again, you know, the other flexi that's down here, this one, that's the one that carries all the supplies like the transmit 8-volt rails and the supplies that we're concerned with at the moment, with the power amplifier exciter circuit, plus other things on this. And on both sides of this flexi, we were witness damage to these pins both on the board that plugs in down there and here, and I've had to be very careful with this. So there's a few things here. We've got too many things that could potentially cause all these problems. These flexes that have got broken, bad connections, shorter connections. We've got a control head flexi that's got another issue there. So we could really do, before we proceed any further in trying to get these flexes. The other flexes like this one aren't too bad. That one, I don't think there was a problem with that one. That one's okay. So it's just these wider ones that have got these wider pins on them, like that. So if we can get some of those, some replacement ones, then at least we know where we're starting from is going to be good. But I think the next thing to do is just going to have a look around with the magnifier on this board. Have a look at those sockets more carefully, really scrutinise this board and try and see what's been going off on it. Why is this all this little writing on the board and all these marks and other things? What's that all about? Okay, so I've discovered some more issues now on this radio to do with these flexes, these corroded ones and the ones that have got all the dodgy mess on them. But more importantly, this connector down here, the one that connects to these flexes, is still quite corroded. It's still got the green corrosion down it when you look inside there, and I've tried to clean it up again with a diamond file, but as you can see, it's not particularly good at all, is that. But the problem is that I've now found another fault, which is to do with the TX supplies for the VHF and UHF, which leave this board and then go on this flexi then to the other board, and ultimately then supply these two supply rails, which we'll look at a moment on the circuit diagram. But this flexi appears to be damaged, or there's a break in it, because these have been in and out quite a lot, obviously before I've had a look at it as well. And this water damage that's on them, I think's finally, you know, seen them to the end. But bearing in mind the condition of this radio, as we've seen throughout this video, we've had the VCOs unlock on HF, we've had the loudspeaker, which you can see here, and the loudspeaker, the actual wire that you can see here on this side is totally broken off now and just disappeared, because that was all crusty. At the beginning of the video, if you remember, we showed that wire being crusty and that these coils open circuit, and we've got this rust that's on the inside of the speaker. Now it's very unusual to get that, because normally I've seen cones that have been smashed in, coils that are burned out because of, you know, a DC applied to them or something like that through a electrolytic cap going. But this sort of damage I've not seen on a Kenwood TS2000 as bad. Plus, when you combine that with all the other damage that we've found in the radio as well, we've got all these little marks on the connectors as well, and writing on the board, which is a clear indication that somebody else has been working on it. And likewise the other board as well, that was inside the radio, the holes that are used for the cables to come through had marks on them. So, you know, we've got clear pen marks to show where cables should come through and protrude, etc. But basically the supply that needs to get to this radio for the transmit supply for VHF and UHF, for that broadband amplifier we're looking at, comes in on a connector down here, which is this flexi, and this is the flexi that's got the corrosion on it. Now, in addition to that, on the other side, these little pins that you can see on there, the profile on them, they're starting to ping up like that and come away from the backing plastic. So being very careful to make sure that when those connectors go back in these flexes, but it's evident they've been bent quite a lot prior to this radio getting to me, and they've obviously sustained this water damage and this corrosion. And as we can see here, we've got rusty parts on the unit, and we've got some clear evidence there of corrosion, as well as, you know, obviously on the flexi itself. So that's causing problems with the control head. But more importantly, the top of the radio as well, all the paint's all speckled and everything, as we saw right at the beginning, and there's clear signs that this radio's obviously had some kind of liquid damage at some stage. And you know, we can we can see that. So what I want to now share is the fact that it looks like before we can go any further, I'm going to need to get some flexes for this radio. And prior to getting to this part of the video, I've been reaching out to known suppliers that I use in amateur radio spares that do stock parts for all models of radios, as many as they can, and they do supply these on the internet. Now, what's interesting about it is that I reached out to the guy who owns this radio, asking some questions, because as we've been filming this video, and we've noticed all these problems that you've seen clearly evidenced on the video right from the start, with the VCO going out of look on HF. There was no TX on HF as well, apart from on certain bands where the VCO was behaving itself, and even then it was off frequency, as we saw in the video, and at random frequencies, and then it didn't transmit on VHF UHF, but it received okay. So we went through all this sort of diagnostic earlier in the video, and we've obviously found the speaker wasn't working. It was open circuit, so I had to put one of mine on just to try and get it going, you know, so we could hear some audio coming out of it. So this is how it was presented to me. This is how it came to me. So I reached out to this guy and I basically put all this to him and said, look, you know, this will all be in the video, you'll be able to see it for yourself, and this is, you know, clear evidence of what we found. And I asked numerous questions, one of which is, you know, who else has had a go at this radio before me, and have you used it in a boat, you know, in the ocean, have you had it side of a swimming pool, you know, have you had it outside where it's going to get rained on or wet, because this looks like saltwater corrosion to me rather than freshwater corrosion. But anyway, and he come back and he said, hi, he says, apart from the isolation plastic sheet under the PLL board, nothing has been touched here in, I don't know what this means, 3BB, whatever that means. My brother bought this radio brand new from a company in the UK, out of the box. It stayed on my desk and never left my house. I am very surprised to know the state of the radio. For example, just before sending it to you, I was using it on HF. It was working perfectly well and the loudspeaker was good. The only issue was VHF UHF not working. Even with the the burnt part at the HF side was still working. It's as if you are describing issues of another radio to my radio. I hope you can repair it without spending too much, because it's already quite old now and maybe it's not worth spending much to repair it. So this seems a bit at odds with the what we've discovered in the video, the fact that the speaker was open circuit, that the wire on the speaker was corroded, as clearly documented in the video. The VCOs on HF were all out of lock, and that's the condition that we found it to have, with the dashes on the display. And he says that he's the only person that's been in it. So where have all these blue marks come from, I wonder. Now I wonder if this guy, maybe not aware, and he will be, so obviously when he watches this video, that perhaps this radio that may have been bought brand new, his brother bought it brand new from a place in the UK, it may not have been new. It may have been that it's had numerous faults on it and it's been put right initially. Hence the reason why there's all these marks and writing and all that sort of stuff all over it, in order to then resell it as being new. And perhaps, you know, this guy's bought it believing, his brother has bought it believing it to be new. It's being sold that way when in actual fact it isn't new. In addition to that, that's a possibility, obviously, you know, I don't know for certain, but it's certainly, you know, the radio fairies haven't been in, you know, putting those crayon marks all over the boards and writing on things, and, you know, that doesn't happen in the factory in Japan. I tell you now, I've been repairing Kenwood TS2000s for donkey's years. You can see on my channel I've done repairs on other radios. You don't get that sort of thing going on at a factory. It's somebody's been in this before, whether they've bought this radio in good faith believing it to be new, and in actual fact it's been faulted before and pre-owned, and that's the reason why all these marks and things have come on inside. Now also it says he's been using it on HF. Well, we weren't able to use it on HF to transmit, certainly, because obviously the VCOs were going out of lock. And when we were transmitting on HF, it was way off frequency as well. That was the other issue, which is now resolved. You know, all the VCOs are back in lock after we replace those transistors. We've got this heavy water damage inside, severe corrosion, which is very, very bad on these flexis. So what I've done some more testing, as I say, and I have been and looked into the supplies further, and I have managed to find on the service manual, which we'll look at now, where the issue currently lay. And this is on the socket on the middle board, which is one of the RF boards right in the middle of the radio we were looking at earlier when we were doing the VCO repairs, its neighbouring board, where I described this broadband amplifier. So we'll have a look at that now. So with two lines, basically, there's a socket on the motherboard, the RF board, what's called the TXRX1 unit. Now the flexi strip that plugs into this connector also had damage on the radio board end. In other words, the little fingers which are on the connector just are coming up like that at random, so we have to stick them back down again. But the trouble is, because they're coming away from the backing plate, they might not have a gaps, and then one might be touching, you know, because if they can move this way, they can move that way as well. So we have a problem with this flexi, and what it is, I've measured on the control board on the front panel, and we are getting these supplies, this TXB, UTXB is for UHF, VTXB is for VHF. So we're getting this voltage, there's a link through as well via this inductor to the final unit as well, and that's where I went to actually measure the voltage, because the components that I'm going to show you are actually on the underside of the TXRX1 unit board. So the only way I could measure this voltage was to find this inductor, which is actually on top of the board. But anyway, we went and traced these obviously back. They come down here, and after they've gone all the way and sunk down here, they hang a left and come along here. And basically what happens is as we remember earlier, we had a broadband amplifier, and so the one line goes this way and up, and that goes off to what is the UHF. This line comes this way, and if we just briefly follow it a second, it comes along here, and we've got a line coming in this way to enable this pin diode for UHF, and that line there at the top comes in to enable VHF pin diode. So the RF path can get directed two different ways, either VHF or UHF. Likewise, the other line comes in here and supplies power to this broadband amplifier from that inductor. But if we just go back a little bit more here, and we can see we've got a line coming up which connects to this inductor through this diode, and then ultimately that then supplies power to this switch. The hot side of this transistor, this PNP, is brought down to ground on the base, so then it conducts, and on TX, on VHF or UHF TX, we get 4.8 volts. That in turn comes down along here, right the way along, comes along, and it's the second line down, comes here and supplies this broadband amplifier. Now we've got here, we've got the main VHF preamps that provide the VHF signals to the broadband amp, and then up here we've got the UHF, main UHF preamp, if you like, that then sort of provides an output, comes back, and then it joins with the VHF input here at this junction and then comes into the broadband amplifier. So we have two lots of supplies, if you like, which come directly from the VTX line and the UTX lines, which we're looking at on that socket, which provide power to these preamplifier transistors, and also the other line there supplies power to these two preamplifier transistors, which are for the UHF side. So all these power supplies are derived from those two lines, which are called, obviously, what we were looking at earlier. I can get back to them because I've lost them a second. UTXB and VTXB. Well, I'm not getting them power supplies here. So the flexes themselves are actually open circuit, and I know we tried to repair them early because of the bad water damage, and they are badly corroded, just like the one for the control head is as well. That's really bad. But the thing is that you sort of try your best, you know. I weren't expecting this kind of damage. So what I've done, I've reached out to a friend of mine that supplies parts for these radios online, and I basically found a set of flexis that are for a Kenwood TS450, but that's a different model of radio to this. This is a Kenwood TS2000. The flexis are different lengths, the pinouts are slightly different. It could be the pictures on the pins are different as well. So I asked the question, are they compatible with the Kenwood TS2000? The answer was not sure. They're very expensive as well to buy. We're already spent quite a bit of money on this in terms of the transistors and the other work that we've done on it. So I think it's time now we just stop the repair. I go back to the person who owns the radio and basically say, well, this is where we're at now. Do you want to proceed? Because we're just going to spend more and more money on trying to repair this. And what's beyond these flexes, you know, if there's any more issues as well. So, but I do find it very strange though how the owner of the radio says that no one else has been in it, which could be true. Obviously, I'm not saying that person is fabricating the truth. It could be that they genuinely believe the radio was new when they bought it, that there wasn't this water damage inside, as we've clearly seen with the corrosion all over it, and the damage to the speaker. You know, that's very unusual for that level of damage, and that wire to have gone so hard that it's dropped off and the coil's open circuit. There's clearly corrosion got into that to do the coiling. So yeah, that's something entirely different. The screws are rusty as well, which we found on the board. There's been some evidence as well, obviously, writing on the board and marks on all sorts of different boards, and other things being done to the radio, as we've found on the way. And there's even a bod resistor there with a mark there. There's some weird stuff being going on with this radio. Can't quite, you know, understand what's actually gone on with it, but somebody else has definitely been in this radio, and up to me getting that email from the owner, I genuinely thought that I might be the last of a long line of people who have you know, been working on this radio before me, but this guy says not. So my only suspicion there would be is that this gentleman's brother, who believed to have bought this radio brand new, I don't think it was new when they bought it. It was probably second hand in good condition and sold as new maybe, and I think it had a fault on it, and that's why there's all these marks all over it that show somebody else has been in it, you know, and mark things to show where cables should go. It looked to me like somebody who was inexperienced had worked on the radio, and they needed to mark things to show where things connect. So that's a typical scenario that you tend to see. But with all this deep corrosion and water damage and everything else, and the fact that he said it worked on HF, and we've clearly seen in this video it does not work on HF until we did the transistor swaps, because the dashes were coming on the display on the HF frequencies as well. It just seems rather strange to me. And so yeah, I think it's time we stop the repair, go back to him. At least he can see this now and see what he wants to do. Obviously, yeah, the cost of this repair now is running up quite a big bill. We don't particularly want to keep going if the guy just thinks, right, you know, call it quits. But I must say though, this is by far the worst example of a Kenwood TS2000 I have ever had on the bench, in terms of what's wrong with it and the corrosion and everything else. And as you've seen on the channel already, this isn't the first Kenwood TS2000 we've done a repair on, It's very unusual to see such damage on a radio, and obviously when you look at the you know, as we looked at before, this surface on the case and what's gone on there, I have no idea what can bring this. This is like salt water blistering to me. So that's why I had to go back to this guy and ask the question, you know, has this been used in a boat on an ocean going liner or something like that, you know? Because to be honest, I mean, I used to work on radios for HM Coast Guard and the Royal National Lifeboat Institution, the RNLI, and those radios did used to end up in the sea occasionally, and they get fished out and then they get sent in for repair. And I know saltwater corrosion when I see it versus freshwater corrosion. So I believe this has been used in those kind of environments. But this guy says it's not being used outside, it's not being used, not got wet, you know, it's not been on a boat, it's not been used in a beach hut or something like that, or on a ship. It's been used in his own home, and he said he's not near the coast. He's actually quite inland. So yeah, again, it's a bit like that Marconi 2967 radio test set we had on the bench here. Again, the guy there said nobody's been in it, but then when we went in it, we found clear evidence of pins being bent over in the sockets. There was damage inside, screws missing, things not put back in the right place, all sorts of evidence. That I went back to the owner and basically said, look, this is what I found. You said nobody's been in it, but clearly somebody has, because pins don't bend themselves over by themselves. And then he came back and said, well, we haven't been in it, but perhaps somebody else might have been in it, you know. So you dig a little deeper, and this seems to be the case with this, you know. This gentleman says nobody's been in it, but we can clearly say that yeah, somebody has been in it, and I don't think there's just been one person being in it either. I think there's been quite a few, and I'm obviously further down the line. It's just a shame really that if he has bought this radio, his brother's bought this radio new and believed it to be brand new, then I don't think it was brand new. Clearly, you know, you've seen yourself with your own eyes, you know, and it's definitely, you know, the camera doesn't lie. So there you go. So what we'll do, we'll stop this video here, go back to the user who might be shocked at the evidence that we found in this radio. As I say, they weren't aware of all this, so maybe it will be a big shock, a big surprise to them when they've seen this, and then they can make a decision. What do we do? Do we carry on going and spending more money on it, or do we just call it quits and write the radio off? So if the customer decides they want to go ahead and spend even more money and get it, you know, to £200-300 worth of repairs to get this going, ultimately, you know, I might have to wait with this radio quite a long time before I can get spares for it, and even then the prices are going to be very high. So I think it's fair to say this radio is going to be beyond economical repair. But as I say, I'll go back to the user of the radio, the owner, and basically explain, see the video and make your decision what you want to do. But it's such a shame really, it's such a bad condition, you know, the corrosion all over it, and it's not very good, I'm afraid. It's the worst repair I've had on the bench in a while, was in terms of other things being done and corrosion. There's so many problems to bottom out on it before we can even get close to getting it going, I think. So what a shame, but you can't win them all, you see, you can't win them all. But obviously don't let this sort of thing put you off if you are into considering repairing radios. You know, these things happen. You don't know what you're going to get till you whip the lid off and have a look inside. And believe me, there are repairers that wouldn't have even gone this far, you know, because this guy lives in Mauritius and he sent it all the way halfway across the world for me to look at. I didn't want to dismiss it out of hand and just, you know, write it off and send it back, because believe me, there are people that as soon as I took the lid off and seen the corrosion, they would have just said no, BAR straight away. Wouldn't even attempted to go in any further than I've got in here. So it's just unfortunate that, you know, that's the case. But I always like to progress if I can and just try and push on and see whether we can, we can get something going rather than just throw the baby out with the bathwater and just abandon it for this guy. I wanted to try and get it going for him, but there definitely needs to be more money spent on flexis, replacing those and then drilling down a bit deeper. We've still got a lot of corrosion on these connectors here, and I'm not happy about that as well. Whether we can get those connectors is another thing. Parts for these radios are very difficult to come by. I did see on eBay somebody selling a genuine Kenwood TS2000 speaker, which we would have may have needed for this, and it was £75 just for that on its own. So, that's the sort of prices you're looking at for spare parts for these things. So yeah, with that, thank you for watching the video, and as I say, if there is an update to this video and we do progress on with the repair, then I'll do an update to it in due course, and ultimately try and get the radio repaired if a customer decides they want to do that. But anyway, for now, thank you for watching, and hope you've enjoyed the video. If you learned something new about the radio and fault finding and what the likely causes are of some of the VCO faults, etc. And if you like the video, please subscribe. It helps the channel. And once again, thank you for watching, and we'll catch you in the next one. Bye for now. Okay, so just to prove that it's all fully working, now it's all been put back together again. Turn it on and we'll go through all the bands. So there's a 430 megahertz band there, obviously, the 144 145 megahertz band, the 50-52 meg band, 6 meters obviously, 10 meters, then keep going through the bands. So I'm not getting any dashes or anything, obviously, because we've resolved that problem, so at least that's all working. And there we go. So there we are, back to square one. At least everything's working so far as the VCOs are concerned, and all the different modes, etc. So but yeah, just a shame really we can't sort of sort the other issue out with the transmit on 2 meters and 70 sems, because obviously we've got this issue with the flexes inside which need to be replaced. If the user can get those and then perhaps wants to replace them themselves, probably get the radio working straight away, so that's a possibility. Anyway, bye for now.